Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Quickly let me know in the chats with some fire emojis. Yes? Let me know quickly in the chats if all of you can hear me, if I'm perfectly audible, visible to everyone. I think yes, I am perfectly audible, visible, yeah? Yes, perfect. All right, people. So as you all must be knowing, today we are starting our NEET 2025 journey, right? With the most awaited series, that is your Game of NEET 2.0. And the ones who have no idea about this Game of NEET, my dear students, in this particular series, which is going to happen on this particular channel, absolutely free of cost, let me tell you, we are going to cover 75 chapters in just 75 days, right? Every single session will be there for 7 to 10 hours, right? All the concepts, all the problem patterns, all the PYQs, every single thing will be covered in the session itself. And once we are done with the session, we shall be sharing the handwritten PDFs of the session on the Telegram group as well, right? And I'm pretty much sure all of you are already there in the Telegram group. Perfect. So you need not to worry about the session notes, session PDFs. Every single thing will be shared in detail, right? And right after every session, once we are done with the chapter, I shall be giving you the DPPs of the chapter as well. My dear students, it is just, we would want you guys to be consistent throughout this journey. Whether your preparation is not up to the mark, whether if you have not started the preparation yet, or if you have just completed some 10%, 20%, 30% of the syllabus, does not matter at all. We shall be starting each and every chapter exactly from the basics, from the scratch, right? It is just, we want you guys to be with us till the end, because the content which you will be getting in this particular series, my dear students, it is definitely going to be unmatchable. Trust me on that. Because all the concepts, all the theory, all the problem patterns, exactly from the basics, from the scratch, shall be discussed with all of you, right? So are you all ready for this particular session then? Well, it is going to be day one today, yeah? Today it's going to be day one, wherein we shall be starting with the first chapter of your chemistry, that is the epic mole concept. The epic mole concept. This is the chapter which we shall be starting today, and we shall be finishing this chapter in the today's session itself in detail with 100% efficiency. And my dear students, I promise you one thing. If you are attending this particular session from starting till the end, right after the session, take any book, take any material, whatever you have, I'm 100% sure you should be able to solve each and every problem of any material, any book on your own after attending this particular session. Yeah? So are you all ready for the session then? I would want some fire emojis in the chats. I want you guys to light up the chats. I want you guys to light up the chats, quick. I want you guys to light up the chats, people. Everyone. Yeah? I want you guys to light up the chats quickly. Perfect, perfect, amazing, 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 guys. This is the Josh which I would want you guys to have till the end. Okay, it should not be that you'll be consistent for 3 days, 4 days, 5 days. No, you have to be there till we complete all the 75 chapters, right? And that's how, my dear students, your syllabus is going to get completed once. And once we complete this particular series, right after that, we'll be coming up with one more series, which is going to be the quick revision series as well. But this is not the time for the revision. This is the time to go for the syllabus completion in the detailed manner. That's something which we have kept in our mind. And that's how we are going to cover each and every chapter in depth, in detail. Okay? Perfect. So let the day one begin. And as I told you, the complete chapter, which is your epic mole concept, it will be done and dusted. Number one, all the standard questions that will be asked from the chapter mole concept will be covered in detail. And at the same time, all the PYQs which have been asked from this particular chapter, that will be covered in detail too. Okay? So before starting this particular chapter, I would want to let you know exactly what all topics are there in the chapter, which we shall be covering in this particular session. And I would want you guys to take a note of these topics, which I'll write on the screen. Okay? So my dear students, first of all, this chapter we shall be starting with some basic terminologies. This chapter we shall be starting with some basic terminologies. And those basic terminologies, they include atomic mass, molecular mass, as well as the molar mass. These are three basic terminologies which we shall be covering in the beginning in this chapter, right? Followed by their questions. Number one. Number two, we shall be talking about the average atomic mass of an isotopic mixture. Average atomic mass of an isotopic mixture. This is going to be one more important topic. Once we are done with the average atomic mass of isotopic mixture, then there will be basic calculation of moles. There will be basic calculation of moles and different types of questions which can be asked, right? My dear students, once we are done with the calculation of moles, we shall be discussing about the calculation of atoms, electrons, protons, neutrons, ions, valence electrons, etc. This is going to be one more topic which we shall be covering. And right after this, let me tell you, right after this, we shall be discussing about the calculation of moles of atoms and molecules. Calculation of moles of atoms and molecules. This is going to be one more topic that will be covered. Once we are done with this particular one, we shall be discussing about the average molar mass, of a gaseous mixture. This is one more amazing topic, right? And after this, average molar mass of the gaseous mixture, then we shall be discussing about stoichiometry. Stoichiometry in detail, right? In stoichiometry, we shall be discussing about the principle of atomic conservation as well. Principle of atomic conservation will be also discussed in the today's session, right? And we shall be involving the stoichiometry in the sequential reactions as well. In the sequential reactions. Stoichiometry involved in the sequential reactions. This is again one more important topic which shall be covered. Okay? Right after doing the sequential reactions, we shall be doing the problems based on mixture analysis. We shall be doing the problems based on mixture analysis. And my dear students, once this mixture analysis is done, then we shall be doing a term, we shall be discussing a term which all of you must have heard, that is your limiting reagent. And after limiting reagent, it is going to be percentage yield. Once we are done with percentage yield, then we shall be discussing about percentage purity. Percentage purity. And after percentage purity, my dear students, after percentage purity, we shall be discussing about the percentage composition. The percentage composition. Followed by vapor density. Followed by vapor density. And then we shall be discussing about the empirical formula, molecular formula, and questions from, or I can say calculation of empirical molecular formula from combustion. From combustion. Well, this is going to be the flow of the today's session. Okay? This is going to be the flow of the today's session. One topic which you would have maybe studied in mole concept, that is concentration terms. Well, let me tell you, concentration terms, I won't be discussing here in this chapter. Concentration terms will be discussed in the chapter solution. Okay? So, here, this is going to be the end of the chapter mole concept. Okay? So, my dear students, are you all ready now? Should we start? Should we start? I would again want you guys to light up the chats with the fire emojis. Quick. Well, there are a lot of standard questions as well as the new questions which I have added in the today's session. So, in depth, we are going to cover this particular chapter. In depth, we are going to cover this particular chapter. So, let me know in the chats if you all are ready now. Let me know in the chats if you all are ready now. The chats should not stop today, guys. The chats should not stop today. Because it's going to be a long marathon. It might take 7 hours, 8 hours, 9 hours, 10 hours. I have no idea. Till we complete each and every concept from the beginning, from the start. I'll be standing here in front of you and you will be with me till the end as well. And after every 3.5 hours, I'll be giving you the breaks as well. You need not to worry about that. Okay? You need not to worry about that. Absolutely, all the JE aspirants can also watch this particular session. Yes, all the JE aspirants can also watch this particular session. And the ones who have not shared this particular session with other people, do share this session with everyone, whosoever is preparing for NEET 2025 or even 2026 or even JE Mains 2025. My dear students, this particular session is going to be for everyone because every single thing will be done and dusted in detail from the basics, from the scratch. Okay? And there must be one question in your mind. All those students who have already made the notes of this particular chapter, do they have to make the notes again? My dear students, the ones who have covered this particular chapter from me already, okay? You need not to make the new notes. Just be ready with your rough notebook. Whatever questions I'll be mentioning here, give it a try and try to solve those questions, okay, with me. And all the new questions which I'll be solving here, you can add those new questions in your notes which you have already made, right? I'm talking to those students who have already covered this particular chapter with me. Perfect. So let's get going then. Let's get started with the first topic of the today's session. And you know, I start this particular chapter with the basic terminology, which is the atomic mass. Okay, let's start the chapter from the term atomic mass. Perfect. So my dear students, first of all, how do we define the term atomic mass? Let me write its simplest definition first of all. And what is its simplest definition? My dear students, atomic mass is basically defined as the mass of a single atom of an element. Atomic mass is defined as the mass of a single atom of an element. You know, in your periodic table, there are almost, 118 elements, right? You know, in your periodic table, there are 118 elements. And my dear students, every element in the periodic table has got the atomic mass, right? Every element in the periodic table has got what? Has got atomic mass. What atomic mass exactly is? It is simply defined as the mass of one atom of an element. The mass of one atom of an element is something which you call as atomic mass. For example, if I ask you, what is the atomic mass of oxygen? First of all, you should know what exactly am I asking you. I'm asking you atomic mass of oxygen. That means I'm asking you, what is the mass of one atom of oxygen? If I ask you, what is the atomic mass of fluorine? What exactly am I asking you? I'm asking you, what is the mass of one atom of fluorine? Atomic mass of sodium. That means I'm asking you, what is the mass of one atom of sodium? So in short, in simple words, what is atomic mass exactly? Atomic mass is defined as the mass of single atom of an element. The mass of one atom of an element is what you will be calling as the atomic mass. If I ask you, what is the atomic mass of silicon? What does that mean? That means I'm asking you, what is the mass of one atom of silicon? So my dear students, in short, what is atomic mass? Atomic mass is nothing but it is defined as the mass of one atom of an element. Point number one. Point number two, my dear students. In order to understand its actual definition, there are a few basic terminologies which I would want to tell you right now so that you'll get the real feel of the term atomic mass. Understand properly what exactly I'm going to say. My dear students, for example, imagine that over here, I'm taking certain objects. Imagine I have taken two objects over here. This is object number 1 and this is object number 2. These are the two objects which I have taken into consideration right now. For example, I'm saying the weight of this object is 5 kilograms. For example, weight of this particular object is 20 kilograms. The two objects which I have taken over here, I'm telling you in simple words. For example, weight of this object is 5 kilograms. Weight of this particular object is 20 kilograms, right? Now, this 5 kilogram which I have mentioned over here, can I break this 5 kilogram as 5 multiplied by 1 kilogram? Absolutely, I can do that. 5 multiplied by 1 kg comes out to be 5 kg. Similarly, this 20 kg, can I break it as 20 multiplied by 1 kg? Yes, I can break it as 20 multiplied by 1 kg. Now, my dear students, why did I break this 5 kg as 5 multiplied by 1 kg? Why did I break this 20 kg as 20 multiplied by 1 kg? Why did I do that? Understand. See guys, the object which I have taken over here, I have told you its weight is 5 kilograms, right? Can I say this particular object which I have taken over here, can I say this object is 5 times heavier than 1 kilogram? Absolutely, I can say that. I can say this particular object, it is 5 times heavier than 1 kilogram. I can say this particular object is 20 times heavier than what? 20 times heavier than 1 kilogram. For example, my weight is 75 kilograms. What does that mean? That means I am 75 times heavier than 1 kilogram. Right? So, my dear students, can I say I am comparing the weights of different objects? I'm comparing the weights of different objects with this 1 kilogram over here. Yes, because I told you this particular object, it is 5 times heavier than 1 kilogram. This particular object, it is 20 times heavier than 1 kilogram. I am 75 times heavier than 1 kilogram. So I can say I am comparing weights of different objects with 1 kilogram. So this 1 kilogram with which I am comparing weights of different objects, with this 1 kilogram with which I am comparing weights of different objects, I'll be calling this 1 kilogram as the reference. I'll be calling this as the reference. Okay, this 1 kilogram is my reference here with which I'm comparing weights of different objects. Okay. Now, my dear students, if you talk about chemistry, in chemistry, we deal with atoms, we deal with molecules, we deal with ions. My dear students, don't you think in chemistry, we should have the reference like this 1 kilogram with which we can compare the weights of different atoms or molecules or ions? Yes. Like we have 1 kg over here with which I'm comparing weights of different objects. My dear students, in chemistry, we also need a reference. We also need a standard like this 1 kg so that we can compare the weights of different atoms or molecules with that standard, with that reference. Okay? Now, what is that standard in chemistry? What is that standard in chemistry with which we are going to compare the weights of different atoms or molecules? So, my dear students, it is the time to make that standard. It is the time to make that reference in chemistry with which we shall be comparing the weights of different atoms or molecules. Okay? Now, in order to make that standard, what exactly I'll be doing? I will be taking a carbon 12 atom. My dear students, imagine this is your carbon 12 atom. Okay? Imagine this is your carbon 12 atom. What exactly am I going to do? I'm going to divide this carbon 12 atom into 12 equal parts. I divided the carbon 12 atom into 12 equal parts. Well, after dividing this carbon 12 atom into 12 equal parts, if I take this smaller part over here, can I say the weight of the smaller part, the mass of the smaller part, it is just going to be 1 by 12th of, it is going to be 1 by 12th of the mass of carbon 12 atom? Absolutely. The mass of this shaded part, the mass of the smaller part, it is just going to be 1 by 12th of the mass of the whole carbon 12 atom. Right? What exactly I did? I am going to make a standard in chemistry with which we are going to compare the masses of different atoms or molecules. In order to make that standard, I took a carbon 12 atom. I divided a carbon 12 atom into 12 equal parts. After dividing the carbon 12 atom into 12 equal parts, I just took one smaller part, right? And I'm telling you, the mass of this smaller part is nothing but 1 by 12th of the mass of carbon 12 atom, right? And my dear students, let me tell you, this 1 by 12th of mass of carbon 12 atom, from now onwards, this 1 by 12th of mass of carbon 12 atom, this is something which I'll be calling as 1 AMU, or I will be calling it as 1U, or I will be calling it as 1D. Okay? And let me tell you, this AMU, it stands for the atomic mass unit. This U stands for the unified mass. And this D over here, it stands for Dalton. It stands for Dalton, right? Now, let me tell you, by using a technique called as mass spectrometry, what scientists exactly did, they calculated the mass of entire carbon 12 atom. And let me tell you, the mass of entire carbon 12 atom came out to be 1.99 into 10 raised power minus 23 grams. What scientists exactly did? They used a technique called as mass spectrometry, with the help of which they calculated the mass of entire carbon 12 atom. And my dear students, let me tell you, the mass of entire carbon 12 atom, it came out to be how much? 1.99 into 10 raised power minus 23 grams. Okay? Now just tell me one thing. If you know the mass of entire carbon 12 atom, can you tell me what will be the mass of this shaded part? Absolutely. Absolutely. What exactly I'll be doing? Since I know the mass of entire carbon 12 atom, so I can easily calculate the mass of this shaded part. I'll say the mass of the shaded part is going to be 1 by 12th of the mass of entire carbon 12 atom, which is nothing but 1.99 into 10 raised power minus 23 grams. Okay? And my dear students, when you solve this particular term, it will come out to be 1.66 into 10 raised power minus 24 grams. So if I ask you, what is this 1.66 into 10 raised power minus 24 grams? Is it the mass of entire carbon 12 atom? No, this is not the mass of entire carbon 12 atom. This is the mass of the 1/12th part of the carbon 12 atom. This is the mass of the shaded part over here. Okay? Perfect. One more thing, my dear students. Just try to understand. See, let me first of all tell you, this 1.66 into 10 raised power minus 24 grams, it is also expressed it is also expressed in terms of Avogadro's number as well. And let me tell you, this 1.66 into 10 raised power minus 24 grams, it is equal to 1 divided by Avogadro's number. 1 divided by Na. 1 divided by Na. When you divide 1 with the Avogadro's number, when you divide 1 with 6.022 into 10 raised power 23, you exactly get the same value, 1.66 into 10 raised power minus 24, right? Perfect. Guys, it's simple. See, for example, sometimes I write 1.5. If I write 1.5, can't I say 1.5 is nothing but 3 by 2? 1.5 is nothing but 3 by 2. Similarly, this particular term is nothing but 1 by Na. When you divide 1 with the Avogadro's number, when you divide 1 with 6.022 into 10 raised power 23, you get the value exactly as 1.66 into 10 raised power minus 24 grams. Now, people, let me quickly summarize all these things. Let me quickly summarize all these things and try to understand what exactly I'm going to do over here. Try to understand what exactly I'm going to do over here. I'm going to write one statement now, which you are going to remember from now onwards. 1 AMU, 1 AMU, 1 AMU, which is going to be my standard from now onwards. 1 AMU, which is going to be my reference from now onwards, right? And I'll be comparing the masses of different atoms or molecules with 1 AMU from now onwards. You'll understand it clearly in some time. Just have a look. 1 AMU. As I told you, this is also what we call as 1U. We call it as 1D as well. And how do we define it? It is defined as I told you, 1/12 of the mass of carbon-12 atom. 1/12 of the mass of carbon-12 atom. And as I told you already, its value in grams is nothing but 1.66 into 10 raised power minus 24 grams. Or you can write it in terms of Avogadro's number as well. It is 1 divided by Na grams. Okay. So this is one clear-cut statement which I would want every one of you to remember from now onwards. This is one clear-cut statement which I would want every one of you to remember from now onwards. 1 AMU is going to be our standard. 1 AMU is going to be our reference with which we shall be comparing the masses of different atoms or molecules. As simple as that. Yes? Now, my dear students, if I write a statement over here, a simple statement I'm writing. For example, I'm writing atomic mass of oxygen. Atomic mass of oxygen. First of all, what is the meaning of this particular term? Atomic mass of oxygen. What does it mean? It means that I'm talking about the mass of one atom of oxygen. It means that I'm talking about the mass of one atom of oxygen. And I believe every one of you would be knowing its value, right? What is the atomic mass of oxygen? You should know it. How much it is? It is 16 AMU. It is 16 AMU, right? Now people try to understand. Clearly try to understand. Can I break this 16 AMU as 16 multiplied by 1 AMU? Yes, I can do that. My dear students, instead of 1 AMU, can't I write 1 by 12th of mass of carbon-12 atom? Yes, I can do that. My dear students, instead of 1 AMU, can't I write 1.66 into 10 raised power minus 24 grams? Yes, I can do that. My dear students, instead of 1 AMU, can't I write 1 divided by Avogadro's number in grams? Yes, I can do that as well. Now, can you let me know the meaning of all these things? You should be in a position to let me know the meaning of all these things. Try to understand. I wanted to calculate atomic mass of oxygen. I wanted to calculate the mass of one atom of oxygen. And that came out to be how much? 16 AMU. What does that mean? That means one atom of oxygen is 16 times heavier than what? 16 times heavier than 1 AMU. Yes, I can say one atom of oxygen is 16 times heavier than what? 1/12 of the mass of carbon-12 atom. Yes, my dear students, if I ask you what is the meaning of this term, you will say this is the mass of one oxygen atom in grams. This is the mass of one oxygen atom in grams. Even you can say this is also This is also what you will be calling as the mass of one oxygen atom in what? In grams. Yes, I believe this is clear to everyone. My dear students, it's pretty much simple. See, this is the mass of one oxygen atom in AMU. Okay, this is the mass of one oxygen atom in AMU. It means that one oxygen atom is 16 times heavier than one AMU. One oxygen atom is 16 times heavier than 1/12 of mass of carbon-12 atom. I can say this is the mass of one oxygen atom in grams. Or I can say this is also the mass of one oxygen atom in grams. I believe this is clear. I believe this is clear. Let me write one more statement so that it becomes like properly clear to you. Okay? Let me write one more statement. For example, I'm writing atomic mass of some element. Right? Let's say I'm talking about nitrogen. Atomic mass of nitrogen. Now, my dear students, tell me what is the meaning of atomic mass of nitrogen? Let me tell you, atomic mass of nitrogen means nothing. It means that we are talking about the mass of one atom of nitrogen. It means that we are talking about the mass of one atom of nitrogen. Now you tell me, what is the mass of one atom of nitrogen in AMU? You should know it. It is 14 AMU. What this 14 AMU means? Right? What this 14 AMU means? Let me break this 14 AMU as 14 multiplied by 1 AMU. Yes, I can do that. Now, instead of 1 AMU, we can write 1/12 of mass of carbon-12 atom. Yes, we can do that. Instead of 1 AMU, we can write 1.66 into 10 raised power minus 24 grams. We can do that too. And instead of same 1 AMU, we can write 1 divided by Na grams. Okay. Now tell me the meaning of all these things. My dear students, we are talking about the atomic mass of nitrogen. We are talking about the mass of one atom of nitrogen, which came out to be 14 AMU. What does it mean? It means that one nitrogen atom. It means that one nitrogen atom is 14 times heavier than what? Heavier than 1 AMU. It means that one nitrogen atom is 14 times heavier than 1/12 of mass of carbon-12 atom. Right? Can I say this is the mass of one nitrogen atom in grams? Yes. Can I say this is also the mass of one nitrogen atom in grams? Yes. Perfect. I believe you got the exact meaning, you got the exact significance of the term atomic mass. Say yes or no in the chats quickly. Say yes or no in the chats quickly, people. Say yes or no in the chats quickly. Say yes or no in the chats quickly. Yeah, perfect. Amazing, guys. Amazing. Let me write one statement and just tell me whether you got the meaning of this statement or not. Just tell me whether you got the meaning of this particular statement or not. I can say atomic mass. I can say atomic mass of an element. Atomic mass of an element gives an idea. Atomic mass of an element gives an idea about atomic mass of an element gives an idea about how many times gives an idea about how many times an atom of an element is heavier than an atom of an element is heavier than what? Heavier than 1 AMU. Let me know in the chats if this particular statement is clear to you. Let me know in the chats if this particular statement is clear to you. Atomic mass of an element, it gives me an idea about how many times an atom of an element is heavier than 1 AMU. I believe this is super clear to everyone. And my dear students, if this is super clear to everyone, there are a few more things which I would want to tell you over here. What are those things? Understand properly. For example, I am taking the element nitrogen. Let's say this is nitrogen. I'm just writing N. I'm not writing N2. I just wrote N. That means I have taken nitrogen in which form? That means I have taken nitrogen in atomic form. I have taken nitrogen in atomic form. Now, my dear students, I am going to write few terminologies. I'm going to write few terminologies related to nitrogen. Understand? The first term which I'm writing is 14 AMU. The second term which I'm writing is just 14 without any units. Just 14. The third term which I'm writing is 14 multiplied by 1 AMU. And instead of 1 AMU, I'm writing 1.66 into 10 raised power minus 24 grams. I've written three terminologies with respect to nitrogen over here. 14 AMU, 14 AMU. The second one is just 14. And the third one is 14 multiplied by something. Right? Now, if I ask you what is this 14 AMU, you will say this is the mass of one nitrogen atom in AMU. This is the mass of one nitrogen atom in AMU, right? Or I can clearly say this is basically the atomic mass of nitrogen. This is the atomic mass of nitrogen. In what? In AMU. So this is the mass of one atom of nitrogen in AMU. Or I can say one atom of nitrogen is 14 times heavier than one AMU, right? Now people, this 14 without any units, I'll be calling this 14 as the relative, I'll be calling this as the relative atomic mass of nitrogen. I'll be calling this as the relative atomic mass of nitrogen. Okay, this is the relative atomic mass of nitrogen. Perfect. This 14 into something. This is something which I'll be calling as, actual mass of nitrogen. This is something I'll be calling as actual mass of nitrogen. Or what is the meaning of this? This is basically the mass of one atom of nitrogen in grams. As simple as that. Okay, perfect. So in general, let me see if you got this particular point or not. In general, for example, imagine that you have got the element X. Let's say you have got the element X. And this X I'm taking, for example, in atomic form. In atomic form. Perfect. Now people, I'm writing few things about this X. The first thing, I'm writing M AMU. The second thing, I'm just writing M. The third thing, I'm writing M multiplied by 1.66 into 10 raised power minus 24 grams. Can you let me know the meaning of all these terms over here? You should be in a position to let me know the meaning of all these things. This M AMU, this is something which you'll be calling as atomic mass of X. Atomic mass of X. That means mass of one atom of X in what? In AMU. This M over here, you'll be calling this as the relative atomic mass of X. Relative atomic mass of X. And this particular thing, you'll be calling this as the actual mass of X. Actual mass of X. That means this is this particular term. It gives me the mass of one atom of X in grams. Right? Is it clear, people? Is it clear? Is it clear? Is it clear? Quickly, let me know in the chats. Everyone. My dear students, one statement which I would want you guys to remember from now onwards. One statement which I would want you guys to remember from now onwards. If I ask you, what is the scale which I've chosen over here? What is my scale? My scale was, I have chosen the scale as 1 AMU is equal to 1 by 12th of mass of carbon to atom. That is my scale. That is my scale, right? The scale which I have chosen, 1 AMU, is equal to 1 by 12th of mass of carbon to atom. If I change the scale, let's say I'm calling 1 AMU as 1/6 of mass of carbon to atom. I'm calling 1 AMU as 1/24th of the mass of carbon to atom. If I change the scale, what happens? What happens? One statement which I'm going to write over here, and I would want you guys to remember it directly, right? My dear students, on changing the scale, remember on changing the scale, actual mass does not change. On changing the scale, it is the actual mass which does not change. When you change the scale, actual mass does not change. Okay, so these are few things which I would want you guys to remember over here. If atomic mass terminology is clear, let me know once in the chats, then I'll move on to one more terminology. Quick, people. Quick. Everybody, quick. Everybody, quick. All clear? I hope all the things are clear. Guys, as I told you already, I'll be starting from the basics, from the scratch. Everything will be done from the scratch, from the basics. All right. Before discussing about the molecular mass, let me just ask you one simple question so that you can apply all the things, whatever we have discussed till now, so that you can apply it in the questions as well. For example, I'm asking you to calculate the mass of 10 oxygen atoms. Calculate the mass of 10 oxygen atoms in, number 1, in AMU. Number 2, in grams. Simple question. Yeah? Don't tell me you cannot solve this question. It's a simple and basic one. Don't tell me you cannot solve this one. Calculate the mass of 10 oxygen atoms in AMU, then in grams. You're not going to say that you cannot solve this question. It's simple, guys. See, if I first of all talk about the atomic mass of oxygen, what is the atomic mass of oxygen? Atomic mass of oxygen means mass of one atom of oxygen. Mass of one atom of oxygen. In AMU, it is equal to 16 AMU. In AMU, it is going to be 16 AMU. In grams, it's going to be 16 multiplied by 1.66 into 10 raised power minus 24 grams. Or in grams, you can write it in terms of Avogadro's number as well. So 16 multiplied by 1 upon Na grams. Correct? This is the data which I have written for one atom of oxygen. But am I given with one atom of oxygen or 10 atoms of oxygen? We have to calculate the mass of 10 atoms of oxygen, right? So if the mass of one atom of oxygen is 16 AMU, what do you think will be the mass of 10 atoms of oxygen? What do you think will be the mass of 10 atoms of oxygen? I would say the mass of 10 atoms of oxygen will be 16 multiplied by 10, which is going to be 160 AMU, right? This is the mass of one atom of oxygen in grams. If this is the mass of one atom of oxygen in grams, multiply it with 10, you will be getting the mass of 10 oxygen atoms in grams. So when you multiply this term with 10, you get 16 multiplied by 1.66 into. This was 10 raised power minus 24 into 10. It becomes 10 raised power minus 23 grams. This is the mass of what? This is the mass of 10 oxygen atoms in grams. Or you can write it in this format as well. This is the mass of one oxygen atom in grams. Therefore, mass of 10 oxygen atoms will be multiplied by 10. So it's going to be 160 divided by Na, and it's going to be grams, right? So this is the mass of 10 oxygen atoms in AMU. This is the mass of 10 oxygen atoms in grams. Or you can say, this is the mass of 10 oxygen atoms in grams. Am I clear with this? Say yes or no in the chats quick. Everybody? Everybody in the chats? Yeah? I believe this is super clear. I believe this is super clear. Yes? Quick, people, quick. Let me know in the chats quickly. Quick, everybody. Amazing. Moving on. Moving on to the term that is your molecular mass. My dear students, what was atomic mass? Atomic mass was mass of one atom of an element. So what do you think molecular mass will be? In simple words, what do you think molecular mass will be? Molecular mass will be simply the mass of one molecule. Right? Mass of one atom used to be called as atomic mass. Therefore, mass of one molecule will be called as molecular mass. Or you can say it like this. The sum of atomic masses. The sum of atomic masses of all the atoms. Of all the atoms present in the molecule. What is exact meaning of all this stuff? What is exact meaning of all this stuff? Understand what exactly I'm going to say. My dear students, for example, I am taking water into consideration. Water. Do you know the formula of water? Molecular formula? Absolutely. What is the molecular formula of water? It is H2O. This is the molecular formula of water, H2O. For example, I am asking you to calculate the mass of one molecule of water. Let's say I'm asking you to calculate the mass of one water molecule. I'm asking you to calculate the mass of one water molecule. So technically, I'm asking you to calculate the molecular mass of water. Technically, I'm asking you to calculate the molecular mass of water. Right? If I want to calculate the mass of one water molecule, if I want to calculate the mass of one molecule of water, so what does that mean? What do I want to calculate? I technically, as per the definition, want to calculate the molecular mass of water. How do you calculate the molecular mass of water? How do you calculate the molecular mass of water? The sum of atomic masses of all the elements over here. The sum of atomic masses of all the elements over here. So how many elements are here? We have got two elements. One is hydrogen, one is oxygen, right? What is the atomic mass of hydrogen? You know it, 1 AMU. How many hydrogen atoms are there? 2 hydrogen atoms. Plus, what is the atomic mass of oxygen? 16 AMU. How many oxygen atoms do we have? 1. When you solve this, the value comes out to be 16 plus 2. It comes out to be 18. Now, whether you want to write AMU or U or D, choice is all yours. But preferably, we write U. You can write AMU as well. You can write D as well. Right? Preferably, we write U. Now, my dear students, if you think logically, 18U, I can break it as 18 multiplied by 1U. Right? Instead of 1U, we can write 1/12 of the mass of carbon-12 atom. Yes? And instead of 1U, we can write 1.66 into 10 raised power minus 24 grams. Yes? Instead of the same 1U, we can write 1 divided by Na grams. Can you let me know the meaning of all these things over here? Can you let me know the meaning of all these things over here? I just wanted to calculate what? I just wanted to calculate molecular mass of water. I just wanted to calculate the mass of one molecule of water, which came out to be 18U. That means one water molecule is 18 times heavier than what? 1U. One water molecule is 18 times heavier than 1/12 of the mass of carbon-12 atom. Yes? Can I say this is the mass of one water molecule in grams? Absolutely. Can I say this is also the mass of one water molecule in what? In grams. Right? Perfect. This is the mass of one water molecule in U. This is the mass of one water molecule in grams, or even this is the mass of one water molecule in grams. As simple as that. Done and dusted. Nothing to do. Very simple and basic. Yeah? Now, people, tell me one more thing. For example, I'm taking the molecule as glucose, C6H12O6. For example, I want to calculate molecular mass of glucose. Imagine that I want to calculate the molecular mass of glucose. So what do I want actually? I want to calculate the mass of one molecule of glucose. How do I calculate the mass of one molecule of glucose? How do I calculate the mass of one molecule of glucose? How do I do that? Simple. Sum of atomic masses. How many elements do you have over here? We have got 3 elements. Carbon, hydrogen, oxygen. Now, my dear students, be careful. Simple. What is the atomic mass of oxygen? 12 AMU. What is the atomic mass of carbon? 12. How many carbon atoms? 6. So multiply it with 6. Plus atomic mass of hydrogen, 1. How many hydrogen atoms? 12. Right? Similarly, atomic mass of oxygen, 16. How many oxygen atoms? 6. When you solve this, the value comes out to be what? When you solve this, the value comes out to be 180 and you'll be writing U with it. Okay, now, you know, what do we do with this? 180U means you can write it as 180 multiplied by 1U. Okay, instead of 1U, you can write the same thing, 1/12 of the mass of carbon-12 atom. Instead of 1U, you can write 1.66 into 10 raised power minus 24 grams. Instead of 1U, you can write 1 divided by Avogadro's number in grams. Yes, now tell me the meaning of all these things. Tell me the meaning of all these things, people. Tell me the meaning of all these things over here. I wanted to calculate the molecular mass of glucose. I wanted to calculate the mass of one molecule of glucose, which came out to be how much? 180U. That means one glucose molecule is 180 times heavier than 1U. One glucose molecule is 180 times heavier than 1/12 of mass of carbon-12 atom. This is the mass of one glucose molecule in grams. Even this is the mass of one glucose molecule in grams. If you got this, let me know once in the chats quickly. Let me know once in the chats quickly if you got the meaning of all the things which I told you over here. Quick, people, quickly. Quickly, people. Is it clear? Is it clear? If this is clear, then comes a statement which I believe everyone should get now. I believe everyone should get this particular statement which I'm going to write on the screen. The statement is simple. I'll say molecular mass. Molecular mass gives an idea. Molecular mass gives an idea about how many times a molecule is heavier than. A molecule is heavier than what? Heavier than 1U or 1 AMU or 1D. If this particular statement is clear, let me know once in the chat quickly. Everybody, people. Let me know once in the chats if this particular statement is clear. Perfect. Now, if this is perfect, then comes one more thing. If this is perfect, then comes one more thing. My dear students, for example, if I write O2 over here, O2, what does it mean? Have I written oxygen in atomic form or molecular form? Just tell me that. Have I written oxygen in atomic form or molecular form? I would say I have written oxygen in molecular form. I would say I have written oxygen in molecular form, right? Now, related to this particular oxygen which is there in molecular form, let me write few terminologies. And you are going to let me know the meaning of all those terminologies. Understand. The first terminology which I'm writing, 16 multiplied by 2 is 32. So first I'm writing 32U. Then I'm just writing 32. Third thing, I'm writing 32 multiplied by 1U. And instead of 1U, I'm writing 1.66 into 10 raised power minus 24 grams. Tell me the meaning of all these things. Tell me the meaning of all these things, people. This 32U, should I be calling this as atomic mass of oxygen? No. I will be calling this as molecular mass of oxygen. This is something which I'm calling as molecular mass of oxygen. Molecular mass of oxygen. This is the mass of one molecule of oxygen in U. In U. Okay? What do I call this as? Should I be calling this as a relative atomic mass of oxygen? No way. You'll be calling this as a relative molecular mass of oxygen. A relative molecular mass of oxygen. And what about this particular term? This is going to be the actual mass. This is going to be the actual mass. Actual mass of what? Actual mass of O or O2. This is the actual mass of O2. I hope all these three terminologies are absolutely clear. If these three terminologies are clear, let me write one more thing. And with that, I believe this particular thing will be absolutely clear. See guys, right here I'm writing N and right here I'm writing N2. What is the difference? What is the difference, people? Here I'm taking nitrogen in which form? Here I'm taking nitrogen in atomic form. And here if you look, nitrogen I'm taking in which form? Molecular form. One is the atomic form of nitrogen and one is the molecular form of nitrogen, right? So tell me just one thing. First term, that is 14 AMU. Second term, that is 14. Third term, 14 multiplied by 1.66 into 10 raised power minus 24 grams. Similarly, 14 into 2, 28 U. Second term, just 28. Third term, 28 multiplied by 1.66 into 10 raised power minus 24 grams. Tell me the meaning of all these things over here. Tell me the meaning of all these things over here. Since this is the atomic form, so this is going to be my atomic mass of nitrogen in AMU, right? Mass of one atom of nitrogen in AMU. One atom of nitrogen is 14 times heavier than one AMU, right? One atom of nitrogen is 14 times heavier than 1/12 of mass of carbon to atom. This 14, this is what you'll be calling as, the relative atomic mass of nitrogen. Relative atomic mass of nitrogen. This is something which you call as the actual mass of nitrogen. The actual mass of N, basically. Right? Actual mass of N. Now, what about these terms? 28U. What do I call this as? Atomic mass or molecular mass? This is the molecular mass of nitrogen. This is the molecular mass of nitrogen in U. This is what I'll be calling as a relative molecular mass. A relative molecular mass of nitrogen. This is something which I'll be calling as the actual mass of N2. Actual mass of N2. If all these terms are clear, if you can differentiate all these terms over here, give me thumbs ups in the chats quickly. Give me thumbs ups in the chats quickly. Everyone. Quick, people, quick. Quick. All clear? All clear, all clear. Quick, quick, everybody. Perfecto. Amazing. I think every single thing is being cleared. And this is the manner we are going to cover all the chapters from the basics, from the scratch. Okay? This is the manner we are going to cover each and everything in detail, from the scratch, from the basics. Perfect, guys. Perfect. The chat should not stop. We have got a long way to go, guys. We have got a long way to go. The ones who are going to withstand this challenge, trust me, they are the ones who are going to fall into the category of 680 plus. Trust me on that. Perfect. Perfect, people. So let's move on then. And let's exactly see what kind of questions can we solve. Let's see what, see, there are some basic types, since we have covered two terminologies. So from these two terminologies, certain basic things will be asked. What are those basic things? Let's try to cover those basic things. Look at the question, guys. Look at the question. And I believe you should be in a position to solve this question already. The question is, if 1U is defined as, 1/24th of the mass of carbon to atom, calculate the molecular mass of carbon dioxide on Nev scale and calculate the actual mass of carbon dioxide on Nev scale. That is the question. Understand how exactly you guys are going to tackle these sort of questions. My dear students, just tell me one thing. How did we define 1U? How did we define 1U? We defined 1U as 1 by 12th of the mass of carbon-12 atom. This is how we defined 1U, right? And as per the question, how they are defining 1U? They are changing the scale basically, right? Since as per the question, they are defining 1U as 1/24th. So let me call this as 1U dash. They are defining it as 1 by 24th of the mass of carbon-12 atom. Right? Okay. So people, if you look carefully, this is the scale which we have chosen. I'll be calling this as old scale, which we have chosen. Conventional scale. Right? This is the new scale that is given to me as per the question. Okay. We need to calculate the molecular mass of carbon dioxide as per this particular scale. As per this particular scale. Now, how do you approach to these sort of questions? How do you approach these sort of questions? Someone is asking, sir, what about Dalton's atomic theory? Dalton's atomic theory you get in boards, not in NEET. Okay? Dalton's atomic theory you get in board examination. Perfect. That is not asked in NEET. Whatever I'm teaching you right now, this is asked in NEET, and understand each and everything properly. Okay? Look here now. Look here now. Look here now. So my dear students, whenever you see this sort of a question, the first thing which you'll be always doing, call this as equation 1, call this as equation 2. Call this as equation 2. If I divide these two equations, equation 1 divided by equation 2, I'm dividing these two equations. Equation 1 by equation 2. What does it become? It becomes U divided by U dash. U divided by U dash is equal to mass of carbon-12, cancelled. In the numerator, 1 by 12. In the denominator, 1 by 24. So I get U divided by U dash is nothing but, it comes out to be 2. So my U is equal to 2 times U dash. So whenever you get this sort of equation, the first thing which you'll be doing always, you will be getting the relation between U and U dash. You'll be getting the relation between U and U dash. And we got the relation between U and U dash. Now people, after getting the relation between U and U dash, tell me one thing. Tell me one thing. What is the molecular mass of carbon dioxide as per our scale? What is the molecular mass of carbon dioxide as per our scale? How do we calculate molecular mass of carbon dioxide as per our scale? Carbon has got 12 AMU multiplied by 1. Oxygen has got 16 AMU multiplied by 2. The value comes out to be 44 U. This is the molecular mass of carbon dioxide as per our scale which we have chosen. This is the molecular mass of carbon dioxide as per our scale. Right? But do we have to write the answer in terms of U or U dash? We have to write the answer in terms of U dash. We have to write the answer in terms of U dash. So this 44U, you can break it as 44 multiplied by 1U. And my dear students, already 1U is nothing but 2 times U dash. 1U is nothing but 2 times U dash. The value comes out to be 88 U dash. So what is this particular thing? This is basically the molecular mass of carbon dioxide as per new scale which is mentioned in the question. Yes. This is the molecular mass of carbon dioxide as per the new scale which is mentioned in the question. Now, the second part of the question. Calculate the actual mass of carbon dioxide. My dear students, tell me one thing. On changing the scale, does the actual mass change? You have taken already a note of a statement which I gave you already. On changing the scale, nothing happens to actual mass. So if I ask you, what is the actual mass of carbon dioxide? What used to be the actual mass of carbon dioxide? Actual mass of carbon dioxide used to be 44 multiplied by 1.66 into 10 raised power minus 24 grams. This was the actual mass of carbon dioxide, which is never going to change. Whatever scale you want to choose any scale. Actual mass of carbon dioxide is going to remain the same. 44 into 1.66 into 10 raised power minus 24 grams. Nothing is going to happen to this. Am I absolutely clear to this? If yes, then let's try to solve one more question. Similar type of question which you guys are going to solve. The question is, if 1U is defined as 1/6 of mass of carbon-12 atom, calculate the molecular mass of NH3 as per new scale. Simple. People, tell me one thing. How did we define 1U? We have defined 1U as 1 by 12th. We have defined 1u as 1 by 12th of what? 1 by 12th of the mass of carbon-12 atom. This is how we have defined 1u. This is our scale. This is old scale. This is conventional scale, right? Calling this equation number 1. As per the question, how they are defining 1u? They are defining 1u as, which I'm writing as 1u dash, is nothing but 1/6. 1/6 of what? 1/6 of the mass of carbon-12 atom. 1/6 of the mass of carbon-12 atom, right? This is the old scale, this is the new scale. What is my first thing? I'll be dividing two equations to get the relation between u and u dash. That's my first step. So divide equation 1 with equation 2. So it becomes u divided by u dash. U divided by u dash is equal. This term cancels out. This is 1 by 12. And over here, I'll be getting 1 by 6. So I'll be getting u divided by u dash is nothing but 1 upon 2. Or I can say u is equal to u dash by 2. So this is the relation between u and u dash, which I got. If you got the relation between u and u dash, my dear students, tell me one thing. What is the molecular mass of NH3 as per our scale? How we calculate it? 14 into 1? 14 into 1 plus 1 multiplied by 3. 1 multiplied by 3. The value comes out to be 17u. This is the molecular mass of NH3 as per u. But do we have to calculate the molecular mass of NH3 as per u or u dash? We have to calculate it as per u dash. And people, we are done with this. So 17u, I'll be writing as 17 multiplied by 1u. And my dear students, 1u is nothing but u dash divided by 2. It is u dash divided by 2. So the value comes out to be 8.5 u dash. So this is going to be the molecular mass of NH3 as per which scale? As per the new scale. Yeah? Right? If I ask you, what is the actual mass of NH3 now? Actual mass of NH3, it is not going to change. Actual mass of NH3, let me write it like this. Actual mass of what? Of NH3. Of NH3 is not going to change. That is just going to be 14 multiplied, sorry. That is just going to be 17 multiplied by 1.6 into 10 raised power minus 24 grams. Whatever scale you want to choose, nothing is going to happen to this particular term. Actual mass of the substance, that does not change. We have discussed it long back. I believe all these things are super clear to you. And a lot of students are asking me, where do they get session notes? Notes you'll be getting on my Telegram. You can find it afterwards. Its name is Wassim Bhat Chemistry Official. Wassim Bhat Chemistry Official is the name of my Telegram channel on which I shall be sharing the handwritten PDF at the end of the session. Okay? Perfect. Perfecto. Quick. I believe all the things still here are absolutely clear. Right? Right, people? If all the things are clear, just give me some green signal. I mean, let me know in the chats with some thumbs ups quickly if all the things are clear till here. 1 hour done. 9 more hours to go. Are you all ready? Supercharged? Are you supercharged? Are you supercharged? I want the Josh to be the same on day 75. First of all, tonight only I'll get to know how many people are actually serious about NEET 2025 preparation, right? Which I'll get to know at the end of the session. I'll exactly see at the 9th or 10th hour how many people will be there. That's going to give me the actual count of the competition. Perfect. Let's move on now. Let's move on now. Let's move on. So my dear students, my next terminology is, again, one simple terminology which is equally important, molar mass. Okay? Molar mass. How do we first of all define the term molar mass? Let me write its simple definition first of all. Molar mass. My dear students, molar mass is defined as the mass of molar mass is defined as the mass of 1 mole of a substance. Point number 1. Point number 2. It is expressed in, you can say grams or grams per mole. It is expressed in grams or you can say grams per mole. So before going into the details of the term molar mass, I just want to tell you few basic things. After that, we'll go into the molar mass. After that, we'll discuss about the term molar mass. My dear students, if I write 1 mole substance, let's say I'm writing, I've got 1 mole of a substance. What does it mean? What does it mean? Let's say I've got 1 mole of some substance. What does it mean? It means that we have got 6.022 into 10 raised power 23 particles of that substance. If I say I've got 1 mole of some substance, what does that mean? That means I have got 6.022 into 10 raised power 23 particles of that substance. Yes. For example, if I say we have got 1 mole of carbon, 1 mole of carbon, what does that mean? That means we have got 6.022 into 10 raised power 23. Is carbon in atomic form? Absolutely. 6.022 into 10 raised power 23 carbon atoms. Yes. If I say I have got 1 mole of carbon dioxide, what does that mean? That means we have got 6.022 into 10 raised power 23. Now this is carbon dioxide in molecular form. I'll say CO2 molecules. Right? If I say I've got 1 mole of water, 1 mole of water, what does that mean? That means I've got 6.022 into 10 raised power 23 water molecules. I hope you are getting all these things clearly. If I say I've got 1 mole of marker, what does that mean? That means I've got 6.022 into 10 raised power 23 markers. Right? Perfect. I hope you got the meaning of what this 1 mole is basically. Right? 1 mole of any substance contains what? It contains 6.022 into 10 raised power 23 particles of a substance. As simple as that. Now, try to understand few things which I'm going to tell you now. First of all, this 6.022 into 10 raised power 23. 6.022 into 10 raised power 23. We call this particular number, this number is called as the Avogadro's number. You should know it. This is called as the Avogadro's number. And this particular number is represented by Na. We represent this number as Na. So whenever I'll be writing this Na, it means I'm talking about this particular number, which is what you call as Avogadro's number. As simple as that. Now, if this particular stuff is clear, let's try to understand the term molar mass. Let's try to understand the term molar mass. Now guys, before making you clear about the term molar mass, do you remember I told you a few minutes back, 1 AMU, which is basically 1U, which is basically 1D. We can write the term in terms of Avogadro's number as well. Do you remember this particular stuff, which I told you already? This is something I've mentioned. I've discussed with you. This is something which I've discussed with you. Now, look at the term molar mass. Molar mass is defined as the mass of 1 mole of the substance. Mass of 1 mole of any substance. Like we had mass of 1 atom. Mass of 1 atom is what we call as atomic mass. Mass of 1 molecule is what we call as molecular mass. Mass of 1 mole of a substance is what we call as molar mass of that substance. Mass of 1 mole of the substance is what I call as molar mass of the substance. Mass of 6.022 into 10 raised power 23 particles of the substance is what I call as molar mass of the substance. Try to understand what exactly it means. See guys. First of all, for example, I'm asking you, what is the molar mass of this marker? I'm asking you, what is the molar mass of this marker? What does it mean? It means that I'm asking you, what is the mass of 1 mole of a marker? It means that I'm asking you, what is the mass of 6.022 into 10 raised power 23 markers? Right? For example, I'm asking you, what is the molar mass of carbon? What does that mean? What am I asking you? I'm asking you to calculate the mass of 1 mole of carbon. I'm asking you to calculate the mass of 6.022 into 10 raised power 23 carbon atoms. Yes? Similarly, if I ask you, what is the molar mass of water? That means I'm asking you to calculate the mass of 1 mole of water. The mass of 6.022 into 10 raised power 23 water molecule. Let's try to analyze this. See guys, what for example, I'm writing a term. I'm writing a term as molar mass. Molar mass of what? For example, molar mass of nitrogen or oxygen. Over here, oxygen I've taken in atomic form, right? I want you guys to calculate the molar mass of oxygen. What does that mean? That means I want you to calculate the mass of, that means I want you to calculate the mass of 1 mole of O. I want you to calculate the mass of 1 mole of O, right? Or I can say, I'm asking you to calculate the mass of 6.022 into 10 raised power 23 oxygen atoms. Right? Whether you want to say mass of 1 mole O, or you can say mass of 6.022 into 10 raised power 23 oxygen atoms. Right? That's what you will be calling as molar mass of oxygen. Now tell me one thing. How can we calculate the mass of 6.022 into 10 raised power 23 oxygen atoms? That is the point now. How can we calculate that? We can do that. We can do that. Let's use a bit of common sense. Let's first of all try to calculate the mass of 1 oxygen atom. Let's first of all try to calculate the mass of 1 oxygen atom. And once we calculate the mass of 1 oxygen atom, at the end multiply that with the Avogadro's number. Isn't it simple? Get the mass of 1 oxygen atom first. Once you get the mass of 1 oxygen atom, multiply that term with Avogadro's number. You will be getting the mass of 6.022 into 10 raised power 23 oxygen atoms. That means you will be getting the mass of 1 mole oxygen. And mass of 1 mole oxygen is what you call molar mass of oxygen. As simple as that. Right? So people, tell me one thing. What is the mass of 1 oxygen atom? What is the mass of 1 oxygen atom? That means I'm asking you about atomic mass of oxygen. How much that is? Atomic mass of oxygen is 16 AMU. Right? Multiply with what? Multiply with Avogadro's number. Now tell me one thing. The 16 AMU I can write as 16 multiplied by 1 AMU. Multiplied with what? Avogadro's number. Now here is a point. 16 I'm writing as such. 1 AMU. Can we express 1 AMU like this? Yes. Instead of 1 AMU, I can write 1 upon Na grams. Right? And at the end, multiply it with what? Multiply it with Na. So Na got cancelled. The value came out to be 16 grams. Tell me what is the 16 grams? Tell me what is the 16 grams? This is not the mass of 1 atom of oxygen. This is the mass of 1 mole of oxygen. This is the mass of 6.022 into 10 raised power 23 oxygen atom, which is what you call as molar mass of oxygen. Right? So my dear students, molar mass of O is nothing but it is 16 grams. It is 16 grams. What was the atomic mass of oxygen? That was 16 AMU. That was 16 AMU. What is the molar mass of oxygen? 16 grams. That means we just have to change the units. Instead of AMU, we have to write grams. That's all. Instead of AMU, we just have to write what? Instead of AMU, we just have to write grams. That's all. We are done. We are sorted. Yes? Now, tell me one more thing. See, we know atomic mass of nitrogen is how much? 14 AMU. Atomic mass of nitrogen is 14 AMU. So what does that mean? Mass of 1 nitrogen atom is 14 AMU. If I ask you what is the molar mass of nitrogen, replace AMU with grams. So you will say 14 grams is the molar mass of nitrogen. Simple. Okay? Perfect. One more thing. First of all, this 16 grams is what we'll be calling as molar mass of oxygen, molar mass of O, or at the same time, you can call it as one more term. Since oxygen here is in atomic form, oxygen here I've taken in atomic form. So molar mass is also called as gram atomic mass. You'll be calling it as gram atomic mass of oxygen as well. You'll be calling this as gram atomic mass of oxygen as well. Whether you want to call it as molar mass of O or you want to call it as gram atomic mass of oxygen, one and the same thing. Perfect. Now, if this is clear, let's try to analyze and understand this in a better way. Right? Let's try to analyze this and understand this in a better way. Try to be very careful with all the terminologies now. Okay. So whatever terminologies we have discussed, okay, I'm summarizing all the things so that you can remember them properly. For example, here I'm writing N. And here I'm writing N2. Here I'm writing N2. What is the difference, first of all? The difference is nothing. This is the atomic form of nitrogen. This is the atomic form of nitrogen. And this is what? This is your molecular form of nitrogen. This is your molecular form of nitrogen. Now, people, few terminologies I'm writing over here. And you are going to let me know the meaning of all the terminologies. First term, 14 AMU. Second term, just 14. Third term, 14 multiplied by 1.66 into 10 raised power minus 24 grams. Next term, instead of 14 AMU, I'm just writing 14 grams. I'm just writing 14 grams. Similarly, over here, the first term, 28U. Second term, just 28. Third term, 28 multiplied by 1.66 into 10 raised power minus 24 grams. Last term, instead of 28U, I'm just writing 28 grams. Tell me the meaning of all these terms now. I want the meaning of all these terms, people. First of all, nitrogen here is an atomic form. What is this called as? Atomic mass of nitrogen. That means this is the mass of one atom of nitrogen in AMU. One nitrogen atom is 14 times heavier than one AMU. One nitrogen atom is 14 times heavier than 1/12 of mass of carbon-12 atom. Right? What is this 14? This is my relative atomic mass of nitrogen. Relative atomic mass of nitrogen. What do I call this particular term as? You call this as the actual mass of nitrogen, N. Actual mass of nitrogen. Or you can say, this is the mass of one nitrogen atom in grams. What is this term? This is not the mass of one nitrogen atom. This is the mass of one mole of nitrogen. Or you can say, this is the mass of 6.022 into 10 raised power 23 nitrogen atoms, which is what you will be calling as molar mass of nitrogen N, or since nitrogen here is in atomic form, so you'll be calling this as the gram atomic mass of nitrogen. Gram atomic mass of nitrogen as well. The choice is all yours. Yes? Now tell me the meaning of all these things now. 28U, molecular form. Molecular form. That means this is the molecular mass of nitrogen. This is the relative molecular mass. This is the relative molecular mass of nitrogen. This is the actual mass of what? Of N2, not N. And what is this 28 grams? What is this 28 grams? First of all, this is the mass of one mole N2, or you can call it as the mass of 6.022 into 10 raised power 23 N2 molecules. As per the definition, you call it as the molar mass of N2. Or since nitrogen here is in molecular form, you can call this as the gram molecular mass of nitrogen as well. Here it was gram atomic mass because nitrogen I have taken in atomic form. Here you can call this as gram molecular mass of nitrogen as well. Perfect. My dear students, if all these things are clear, let me know once in the chats with some thumbs ups quickly. Yes? All clear? Quick. Quick, people. Quick, people. Everybody in the chats. Everybody in the chats, quickly. Amazing. Amazing, people. Let's move on then. Let's move on. In order to solve certain basic questions, let me just write a statement over here. And I would want you guys to take a note of this statement, right? One simple statement I'm writing, which will help you out in order to tackle a lot of things. See guys, I'm writing a statement as molar mass. Molar mass of, for example, element X. Molar mass of element X. Molar mass of element X. What is meant by this? Mass of 1 mole of X. Mass of 6.022 into 10 raised power 23 atoms of X. How do we calculate molar mass of X? In short, what you will be remembering now? It is equal to mass of 1 atom of X in grams. Just first of all calculate the mass of 1 atom of X in grams, and at the end multiply it with Avogadro's number. That's all. This is something which you have to remember, nothing else. This is something which you will have to remember, nothing else. Got it? Molar mass of some element X is nothing but mass of 1 atom of X in grams. Get the mass of 1 atom of X, right? And then once you get the mass of 1 atom of X in grams, multiply that with Avogadro's number at the end. You'll be getting what? You'll be getting mass of 6.022 into 10 raised power 23 atoms. You'll be getting mass of 1 mole of X. And once you get mass of 1 mole of X, you'll be calling that as molar mass of X. As simple as that. Perfect? But remember, this is the mass of 1 particle in grams, right? This is not in AMU. This is in grams. I believe I'm clear. If I'm clear, let me know once the chat's quick. Yes, this class is useful for JEE students as well. Quickly, people. Is it clear? Should I move ahead? Okay. Tell me the answer of this simple question. One basic question this is. The mass of 1 atom of X is this much. Calculate its molar mass. So, you will simply say molar mass of X is nothing but mass of 1 atom of X, which is 4 into 10 raised power minus 23 grams, multiplied with Avogadro's number, which is approximately 6 into 10 raised power 6.02 into 10 raised power 23. So this term cancels. 6 4s are 24. So 24 grams here is going to be the molar mass of X. Done and dusted, right? Simple. I believe this is clear. Okay. For example, if I write one simple question over here again, one more simple question, guys, okay? So that I just want your basics to be clear, basically. The point is that. Understand. The question I'm writing, the molar mass of X is equal to 10 grams. The molar mass of X is equal to 10 grams. What will be the mass of 10 atoms? 10 atoms of X in AMU. What do you think? What do you think is going to be the answer? Quick. The molar mass of X is equal to 10 grams. What will be the mass of 10 atoms of X in AMU? You should be able to solve this. Think over it. It's a basic common question, simple question. Say, molar mass of X is 10 grams. If molar mass of X is 10 grams, what would be the atomic mass of X? You'll just change the units. Instead of G, you'll write AMU. Right? So I would say, first of all, atomic mass of X will be 10 AMU. And what is meant by atomic mass of X? That means I'm talking about the mass of 1 atom of X. I'm talking about the mass of one atom of X. So if the mass of one atom of X is 10 AMU, what will be the mass of 10 atoms of X? Mass of one atom of X is 10 AMU. So therefore, the mass of 10 atoms of X in AMU will be equal to 10 multiplied by 10. Value comes out to be 100 AMU. Am I clear? Perfect, people. Simple and basic. Simple and basic. Yes. Amazing. Amazing. Chalo, solve one more question. Solve one more question. Look at this question carefully. Look at this question carefully. If Avogadro's number is changed from 6.022 into 10 raised power 23 to 6.022 into 10 raised power 20, then what would be the mass of 1 mole of carbon? What would be the mass of 1 mole of carbon? Think over it. Think over it, people. Think over it. It's simple. You know, since we have made a convention as 6.022 into 10 raised power 23 particles. 6.022 into 10 raised power 23 particles. That is basically 1 mole of substance. That is basically 1 mole of substance. And since we are talking about 1 mole of carbon, right? What is the mass of 1 mole of carbon? Mass of 1 mole of carbon is nothing but 12 grams. This is something which we knew till now. 6.022 into 10 raised power 23 atoms of carbon, particles of carbon means 1 mole of carbon, which has got the mass of what? Will have the mass of 12 grams. Correct? Now, people, if 6.022 into 10 raised power 23 atoms of carbon have got the mass of 12 grams, what will be the mass of one particle of carbon, mass of one atom of carbon? What will be the mass of one particle of carbon? It will be 12 divided by 6.022 into 10 raised power 23 grams. Correct? This is the mass of one particle of carbon. Right? This is the mass of one particle of carbon. This is the mass of one particle of carbon. Yes? Perfect. Now, as per the question, if Avogadro's number is changed from 6.022 into 10 raised power 23 to 6.022 into 10 raised power 20, what would be the molar mass of carbon? So, if mass of one particle of carbon is this much, therefore, the mass of 6.022 into 10 raised power 20 particles of carbon will have the mass of how much? 12 divided by 6.022 into 10 raised power 23 multiplied by 6.022 into 10 raised power 20 grams, right? This term cancel, this gets cancelled. The value comes out to be 12 into 10 raised power minus 3 grams. Just tell me one thing, what is this particular term? This is the mass of now. Now this is the mass of 6.022 into 10 raised power 20 particles of carbon. And as per the definition, this is my new Avogadro's number now, right? As per the definition, this is my new Avogadro's number now, right? And mass of Na particles is what we call as molar mass. This is my new Na. So the mass of new Na particles, is my molar mass. So now I would be calling this as the molar mass of carbon. Did you understand this question? Did you understand this question? Quickly. Quickly, people, everybody. Earlier this was the value of Na, right? When the value of Na was this, at that time molar mass of carbon was 12 grams. Now when the value of Na is this, I would say molar mass of carbon will be this much, 12 into 10 raised power minus 3 grams. All clear? Yes. If this is clear, let's try to analyze one more question. Look at this particular question carefully. Again, you should be in a position to solve this particular question. Guys, I'll show you all the types of the question. You need not to worry. Just remember the approach of these questions. How I am solving, the way I am solving. I want you guys to remember that approach. Okay, look at this particular question now. Suppose two elements X and Y they combine to form xy2 and x3y2. So we have got two elements, x and y. And x and y combines to form two compounds. The first compound is your xy2 and second compound is your x3y2. Second compound is your x3y2. Okay. Now people, as per the question, 0.1 mole xy2, 0.1 mole xy2 has got the mass of 10 grams. 0.1 mole xy2 has got the mass of 10 grams. Similarly, as per the question, 0.05 grams of x3y2 has got the mass of 9 grams. Right? What is the atomic mass of x and y? What is the atomic mass of x and y? Understand, guys. Have a look. First of all, tell me one thing. If the mass of 0.1 mole xy2 is equal to 10 grams, therefore, the mass of 1 mole xy2, if I use the unitary method, 0.1 moles has got the mass of 10 grams. Therefore, 1 mole xy2 has got the mass of 10 divided by 0.1. The value comes out to be 100 grams. Correct? What is this particular term? This is the mass of 1 mole xy2. This is the mass of 1 mole xy2. And mass of 1 mole substance is what you call as molar mass. So this is basically the molar mass of xy2. This is basically the molar mass of xy2. This is basically the molar mass of xy2. So first of all, I calculated the molar mass of xy2. Now understand. If 0.05 grams of x3y2 has got the mass of 9 grams, therefore, sorry, this is not grams, this is moles here. This is moles here. If 0.05 moles of x3y2 has got the mass of 9 grams, therefore, 1 mole x3y2 will have the mass of how much? 9 divided by 0.05 grams, which comes out to be 180 grams. What is this particular term? This is the mass of 1 mole x3y2, and the mass of 1 mole substance is what I call as molar mass. So my dear students, first of all, I got the molar mass of xy2 and I got the molar mass of x3y2. Correct? I got the molar mass of xy2 and I got the molar mass of x3y2. Now just tell me one thing. If you got the molar mass of xy2, what do you think will be the molecular mass of xy2? What do you think will be the molecular mass of xy2? In order to convert molar mass into molecular mass, we just have to change the units. Instead of 100 grams, I'll be writing 100 U. Correct? Similarly, if this is the molar mass of x3y2, what is the molecular mass of x3y2? Change the units. Molecular mass of x3y2. Molecular mass of x3y2 will be 180 U. Correct? So technically we got the molecular masses of these two compounds. Now people, tell me one thing. What is molecular mass? Sum of atomic masses. Let the atomic mass of X be A and atomic mass of Y be B. Let the atomic mass of X be AAMU and the atomic mass of Y is equal to BAMU. Let's assume that. Now, if the molecular mass of XY2 is equal to 100, I would say molecular mass is nothing but sum of their atomic masses. Atomic mass of X is A plus atomic mass of Y is B. B multiplied by 2 is 2B is equal to 100. So I got one equation. Similar equation you'll get from here. You will get 3A plus 2B. You'll get 3A plus 2B is equal to what? Is equal to 180. Calling this is equation 1, calling this is equation 2. Right? Subtract both the equations. Subtract these two equations. So 2B cancels. 3A minus A comes out to be 2A. 2A is equal to 180 minus 100 is 80. So from here, A comes out to be equal to 40 AMU. So this is my A. What is A? A was the atomic mass of X. If you got A, you can easily calculate B. Right? Put the value of A in any of these equations. For example, in this equation, A here, which is 40 plus 2 times B is equal to 100. So 2B is equal to 60. Therefore, B is equal to 30 AMU. And what was this B? This B was the atomic mass of, Y. This A was the atomic mass of X, right? These were the two things which I was supposed to calculate as per the question. right? Prachi is saying, sir, kindly explain both these questions again. Just, this is a live session going on. Just drag the video a little back. It will be automatically a replay for you, right? There is no need for me to repeat the same thing again. Just take the video a little back. You can watch it again. Perfect. People, am I all clear? Did you understand how do you approach this sort of a question if it comes? And this is your asked question. It is a PYQ. It's a PYQ. It is a PYQ. I would want you guys to let me know in the chats if this is super clear to everyone or not. Let me know with some thumbs ups, quick. Let me know with some thumbs ups, quick. Quick, people. Quick, 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 quick. Everybody. Everybody. Yes? All clear? All clear? Amazing. Amazing, people. So all the things, whatever things I've discussed till now, I believe every single thing is super clear. Perfect, perfect, perfect. Then let's move on then. Let's move on to one more topic. That is your average atomic mass of the isotopic mixture. Average atomic mass of the isotopic mixture. This is again one important topic from which questions are frequently asked. Okay, and let's master this concept now so that you can solve all the questions of it. Just a second, guys. Just give me a second, guys. Perfect. So let's move on to this particular topic now, that is average atomic mass of an isotopic mixture. My dear students, first of all, if you ask me, what are isotopes? You should know first of all, what are isotopes? How do we define the isotopes? Isotopes are nothing but, I would say isotopes are the atoms of same element, having same atomic number, but different mass numbers. Isotopes are basically the atoms of same element which have got same atomic number but different mass numbers. For example, let's say I have got the element hydrogen. My dear students, in case of hydrogen, you have got three atoms. Of hydrogen which have got same atomic number, but their mass numbers are different. Their atomic mass are different. This is 1, this is 2, this is 3. So I would be calling these three as the isotopes of hydrogen. These three would be called as the isotopes of hydrogen. For example, If I talk about chlorine, you know, chlorine has got two atoms. Chlorine has got two atoms which have got same atomic number, but their mass numbers are different. One is 35, one is 37. So I would say these are the atoms of chlorine having same atomic number but different atomic masses. So I'll be calling them as the isotopes of chlorine. As simple as that. So in general, my dear students, let's say we have got the element X. In general, we have got the element X. Let's say this element has got two atoms having same atomic number but different atomic masses, M1, M2. So I will be calling these two as the, I'll be calling these two atoms as the atomic, I'll be calling these two atoms as the isotopes of this particular element X. So these are the three isotopes of hydrogen. These are the two isotopes of chlorine. And these are the two isotopes of the element X. As simple as that. Right? As simple as that. And my dear students, let me tell you one thing. Whenever you see element existing in the form of isotopes, whenever you see element existing in the form of isotopes, at that point of time, you will not be calculating the normal atomic mass. You won't be talking in terms of, you won't be talking about the normal atomic mass. You'll be talking in terms of average atomic mass. So first of all, whenever you see an element existing in the form of isotopes, at that time, you will be defining the average atomic mass of this X. Now, let's try to get more details of it. See guys, for example, if I ask you, what is the atomic mass of hydrogen? If I ask you what is the atomic mass of hydrogen, your counter question will be, which isotope of hydrogen you are talking about? If you are talking about this isotope, its atomic mass is 1. If you're talking about this isotope, its atomic mass is 2. If you're talking about this isotope, its atomic mass is 3. Right? If I ask you, what is the atomic mass of chlorine? Your counter question should be, which isotope of chlorine you are talking about? This one or this one? If you are talking about this one, it is 35. If you are talking about this one, it is 37. Right? Perfect. So my dear students, whenever the element exists in the form of isotopes, at that point of time, what do we define? We will be defining the average atomic mass of these isotopes. We'll be defining the average atomic mass over here. Perfect. We'll be defining the average atomic mass. Right? Now, let's get into its details. Understand properly what exactly I'm going to say. Okay? We are going to get into its details. We are going to get into its details. See, for example, I've taken an element X. Okay? Imagine that this element has got 3 isotopes. These are the atoms of X which have got same atomic number, but their atomic mass are different. This is M1, this is M2, this is M3. As I told you, whenever element exists in the form of isotopes, what do we calculate? We calculate average atomic mass for that element. We calculate average atomic mass for that element. Well, let me tell you, in order to calculate the average atomic mass of the element, what do we need? We need the percentage abundances of its isotopes, or we need the mole percentage of its isotopes. What are percentage abundances or mole percentage? What are percentage abundances or mole percentage? Right? That is something which I'll explain you in some time. First of all, remember what I'm saying. Whenever you see element existing in the form of isotopes, at that time, we calculate average atomic mass of the element. In order to calculate average atomic mass of the element which exists in the form of isotopes, what do we need? We need percentage abundances of these isotopes. And percentage abundances I'm representing with A%, B%, C%. What are these percentage abundances? I'll tell you in some time. Right? Repeating the same thing. Whenever you see element existing in the form of isotopes, we do not calculate normal atomic mass of element. We calculate average atomic mass of an element. In order to calculate average atomic mass of an element, what do we need? We need percentage abundances of its isotopes, which I'm representing with A, B, and C. And once we get the value of A, B, C, we make a formula over here, and the formula is simple. M1 multiplied by A, M1 multiplied by A plus M2 multiplied by B plus M3 multiplied by C. Divided by what? Divided by A plus B plus C. This is a general formula which I'll be using to calculate the average atomic mass of an element that exists in the form of isotopes. That exists in the form of isotopes. Okay? That exists in the form of isotopes. Perfect? Now, my dear students, one more thing. Before letting you know what these percentage abundance are, or let me first of all tell you what these percentage abundance are. Understand? 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 For example, I'm talking about chlorine, right? How many isotopes chlorine has? You know, chlorine has two isotopes. One is Cl35, one is Cl37. Correct? Cl35, Cl37. For example, I'm telling you that the percentage abundance of Cl35 is, for example, 75%. Let's say its abundance is 25%. What does this mean? What does these terms mean? It means something like this. Try to understand what it means. My dear students, imagine in this room right now, there are 100 chlorine atoms. Imagine that there are 100 chlorine atoms in the room, right? Now, out of those 100 chlorine atoms, some of the chlorine atoms will be Cl35 and some of the chlorine atoms will be Cl37. If you know the percentage abundances, I can clearly say in this room, out of total 100 chlorine atoms, 75 chlorine atoms will be Cl35 and 25 chlorine atoms will be Cl37. Did you understand? If in total there are 100 chlorine atoms in this room, right? Now some of the chlorine atoms will be Cl35, some of the chlorine atoms will be Cl37, right? If I know their percentage abundances, I can clearly say out of the 100 chlorine atoms, 75 chlorine atoms will be present in the form of Cl35 and the remaining 25 chlorine atoms will be present in the form of Cl37. As simple as that. As simple as that. I hope you got the idea of what this percentage abundance is all about. I hope you got the idea of what this percentage abundance is all about. Okay? And my dear students, one more thing. If you take the sum of these percentage abundances, it will always come out to be 100. So write a note over here first. Write a note over here first. The note is something like this. The sum of percentage abundances. The sum of percentage abundance of all the isotopes. The sum of percentage abundance of all the isotopes of a particular element. The sum of percentage abundances of all the isotopes of a particular element. Of a particular element. That means I'm talking about A plus B plus C, right? It's always equal to what? It's always equal to 100. It's always equal to 100. Okay? It's always equal to 100. Now, at the same time, one more thing which I would want to tell you over here. My dear students, just a second, people. There is some electricity cut. I need to turn the generator on. Just give me a second, okay? Just give me a second. Yes, it's fine now. No dark mode. No dark mode. No dark mode today. No dark mode today, relax. Okay, so I was talking about the sum of percentage abundances of all the isotopes of a particular element. That's always equal to 100. Okay, one more thing, guys. One more thing. Let me tell you one simple thing, right? Which I believe already you guys will be knowing. When percentage abundance of an isotope, is divided with 100, when percentage abundance of an isotope is divided with 100, then you won't be calling it as percentage abundance. You'll be calling it now as fractional abundance. You'll be calling it as the fractional abundance of the isotope. You'll be calling it as the fractional abundance of the isotope. When percentage abundance of an isotope is divided with 100, you will be calling it as the fractional abundance of the isotope. Now, why do I need this fractional abundance? Understand carefully. If you talk about the formula which I have given you over here, MAV is equal to, see, A plus B plus C is always 100. A plus B plus C is always 100. So M1A divided by 100. I can write it like this. M1 A by 100 plus M2 B divided by 100 plus M3 C divided by 100. Right? Now, people, if you think carefully, M1 I'm going to write as such. A by 100. What is A? A is the percentage abundance of this isotope. Percentage abundance divided by 100. What do I call that as? Fractional abundance. So I'll be writing M1 multiplied by fractional abundance of first isotope plus M2 multiplied by fractional abundance of second isotope plus M3 multiplied by fractional abundance of third isotope. This is my one more result with the help of which you can calculate the average atomic mass of an element that exists in the form of isotopes. Right? And my dear students, one more thing. The way I told you, the sum of percentage abundances of all the isotopes of a particular element, that's always 100. In the similar way, do remember, the sum of fractional abundances of all the isotopes of a particular element, that's always equal to 1. This is one more important thing which I would want you guys to remember. And if you are done with this particular slide, that means we are in a position to understand, to do all the types of the questions which can be asked. Okay? Right, people? Let me give you the quick overview of the things which I told you till now. Whenever you have got the element which has got isotopes, for that element, what do we calculate? Average atomic mass. In order to calculate average atomic mass, what do I need? I need percentage abundances of these isotopes, which I'm representing with A, B, and C respectively. Right? If you get percentage abundances, then this is the formula which you'll be using. MAV is equal to M1A plus M2B plus M3C divided by A plus B plus C. Sum of percentage abundances, that is A plus B plus C plus D plus E, something, it's always equal to 100. Okay? Right? And one more thing. When percentage abundance is divided with 100, you call it as fractional abundance. So over here, A by 100. A was the percentage abundance of first isotope, right? Divided by 100. I'm calling this as fractional abundance of first isotope. Plus M2 multiplied by fractional abundance of second isotope. Plus M3 multiplied by fractional abundance of third isotope. And at the same time, do remember, the sum of fractional abundances of all these isotopes, right? It's always equal to 1. Let's try to solve the questions so that you can understand all these things in a better way. For example, let me give you one simple question. Let me solve one simple question over here. Understand carefully. For example, I'm taking the element chlorine. You know, chlorine has got two isotopes. One is Cl35, one is Cl37. Right? Cl35, Cl37. My dear students, remember this data from now onwards. Percentage abundance of Cl35 is 75 and this is 25. Remember this data. Now, for example, I'm asking you to calculate the average atomic mass of chlorine. Okay? So first of all, we have got chlorine. It has got isotopes. The element which has got isotopes, what do we calculate? Its average atomic mass. In order to calculate average atomic mass, what did I need? I needed the percentage abundances. And these percentage abundances we are going to represent with A and B respectively. This is the value of M1. This is the value of M2, right? So I can use the direct formula. I can use the formula. Formula is going to be M1A plus M2B divided by A plus B. A simple formula I'll be using. What is the value of M1? M1 value is 35. What is the value of A? A value is 75. M2 value is your 37, right? B value is nothing but 25 divided by A plus B. A plus B is nothing but 100. When you solve this equation, you'll be getting the value exactly as 35.5 AMU. So this is your average atomic mass of chlorine, which we have calculated over here. Is this clear, people? Is this clear? Is this clear? I believe this particular question is clear. If this is clear, let's try to solve one more. Let's try to solve one more. Look at this question. It is your PYQ. Ask question. Ask question, guys. It is your PYQ. As far as this particular question is concerned, boron has two stable isotopes. Boron has two stable isotopes. One is your B10 and another one is your B11. B11. As per the question, their percentage abundances are given to me. As per the question, their percentage abundances are given to me. One is 19 and another one is 81. What am I supposed to calculate? I'm supposed to calculate average atomic mass of boron. Right? I'm supposed to calculate average atomic mass of boron. In order to calculate average atomic mass of boron, this is something which I'm going to represent with A. This is something which I'm going to represent with B. This is something which I'll be representing with M1. And this I'm representing with M2. Now make the formula. You know the formula already. What is that? M1A plus M2B divided by what? Divided by A plus B. And you know A plus B is always equal to 100. And we are done. What is M1 value? That is 10. What is A value? 19. M2. M2 is 11. B, 81. Divided by A plus B is always 100. When you solve this, you get the value exactly as 10.81 AMU. So this is the average atomic mass of boron, which I was supposed to calculate in this question. All clear? All clear, people? Simple? Absolutely, it's a simple question. Moving on to one more question. Moving on to one more question. Moving on to one more question. Let me write that question on my own. For example, I'm giving a question like this. You've got an element X. Let's say it has got two isotopes. X35, X37. As per the question, for example, average atomic mass of X is equal to 35.5 AMU. And I am asking you to calculate the percentage abundances of these isotopes. I'm asking you to calculate the percentage abundances of these isotopes. Can we solve this? We should be in a position to solve this question, guys. What do we want? We want to calculate the percentage abundances of these isotopes. Tell me one thing. Tell me one thing. The sum of percentage abundances of these isotopes will be 100. Right? Sum is 100. Sum is 100. Now, let's assume the percentage abundance of this isotope is, for example, X. Therefore, percentage abundance of this isotope is simply going to be 100 minus X. Because the sum of percentage abundances, that's always equal to what? The sum of percentage abundances, that's always equal to 100. Right? The sum of percentage abundances of these isotopes is equal to 100. Out of that 100, if the percentage abundance of the first isotope is X, therefore this has to be 100 minus X. Now, my dear students, these percentage abundances we represent with A and B. This is the value of your M1. This is the value of your M2. Now use the formula. Instead of MAV, I can write M1A plus M2B divided by A plus B, which is always 100. And this value is nothing but 35.5. What is the value of M1? M1 value is 35. What is the value of A? That is X. What is the value of M2? That is 37. What is the value of B? That's 100 minus X divided by A plus B is 100. And as per the equation, it is nothing but 35.5. Simple. Now, cross multiplication is needed. You'll be getting the value of X here as 75. And what was this X? X was the percentage abundance of this isotope. And what is the percentage abundance of X37? It is 100 minus X. So 100 minus 75 comes out to be 25%. So these are the percentage abundances of these two isotopes which we were supposed to calculate. If it is clear, let me know once in the chats. Yeah? Right, people? Perfect. Amazing. Amazing. Let's move on to one more question. Look at this particular question. Magnesium has 3 isotopes. Magnesium has 3 isotopes. The percentage abundance of Mg24 is this much. Average atomic mass of magnesium is this much. Find the percentage abundance of Mg25 and Mg26. Let me exactly show you how do we approach this sort of equation. Understand. Understand, guys. The element which we have taken as per the equation, that is magnesium. And this magnesium, it has 3 isotopes. As per the equation, one is Mg24, one is Mg25, and one is Mg26. These are the 3 isotopes of magnesium. As per the question, the average atomic mass of magnesium is given to me as 24.31 AMU. And at the same time, the percentage abundance of Mg24, the percentage abundance of Mg24 is 79. What am I supposed to calculate? I'm supposed to calculate the percentage abundances of these 2 isotopes, Mg25 and Mg26. What do you think? You should be able to solve this question as well. You should be able to solve this question as well. My dear students, understand very carefully. I told you already, the sum of percentage abundances of all these 3 isotopes has to be 100. That is 100, right? Now, if the sum of the percentage abundances of all these 3 isotopes is 100, out of 100, the percentage abundance of first one is 79. Out of 100, the percentage abundance of the first isotope is 79. That means, what will be the percentage abundances of these 2? The percentage abundances of these 2 combinedly will be 100 minus 79. That means 21. The percentage abundances of these 2 combinedly will be 100 minus 79. That means 21. Out of that 21, let's assume that the percentage abundance of Mg25 is X. Therefore, this will be 21 minus X. Is this particular point clear? Is this particular point clear, people? As simple as that. Right? The sum of percentage abundances, that's equal to 100. Out of 100, the first one is showing 79. That means the percentage abundance of these 2 combinedly has to be 21. Out of that 21, the percentage abundance of this isotope is X. Therefore, this will be 21 minus X. Now we are done. We are done with the question. See, guys, this is something which I'm representing with A. This is something which I'm representing with B. And this is something which I'm representing with C. This is the value of your M1. This is the value of your M2. This is the value of your M3. Now just use the formula and we are done. We are sorted. Yeah? MAV is going to be nothing but M1A plus M2B plus M3C divided by A plus B plus C always is equal to 100. And as per the question, this term has to be equal to 24.31. Now tell me one thing. What is M1? M1 is 24. What is A? A is 79. So M1 into A, 24 multiplied by 79 plus M2 multiplied by B. M2 multiplied by B. So 25 multiplied by X. 25 multiplied by X plus M3 multiplied by C. That is 26 multiplied by 21 minus X divided by A plus B plus C. That's 100. And this term as per the question has to be 24.31. Now just calculations needed. Cross multiplication. Cross multiplication, right? Okay. Cross multiplication and get the value of X here. And when you do the cross multiplication and stuff, the value of X you will be getting over here as 11%. What was this X? X was the percentage abundance of Mg25. So basically, you got the percentage abundance of Mg25. Therefore, percentage abundance of Mg26 will be how much? 21 minus X. 21 minus X. The value comes out to be 10%. These were the two things which I was supposed to calculate as far as the question is concerned. If I'm clear, let me know once in the chats quickly. If I'm clear with this, let me know once in the chats quickly. Right, people? Let me know once in the chats with some fire emojis. Quickly, everyone. Everyone in the chats, quick. Break, I'll give you at I'll give you one break that is going to be dinner break, which I'll also take. Just wait for some time. This is not the time for dinner. This is not the time for dinner, guys. Just wait. Yeah? I hope this particular stuff is all clear to everyone. Chalo, let me move ahead. Just give me a second. Just give me a second, guys. Perfect. So let's move on to one more important topic, that is your calculation of moles. This is comparatively simple only. This is comparatively simple only. And let's try to cover this particular thing right now. Calculation of moles. How do we calculate moles of a substance? How do we calculate moles of any substance? Right? How do we calculate moles of any substance? My dear students, there are few results which I'm going to give you. Just remember those results and I'll show you how to apply them. Understand properly. I'm first of all writing number of moles. Number of moles of the substance, which I'm representing with N. Okay? And the formula which I'm going to give you, it is valid for solids, liquids, as well as gases. Number of moles of the substance, which is valid for solids, liquids, as well as gases. It is always equal to given mass of the substance in grams divided by given mass of the substance in grams divided by molar mass of the substance. Given mass of the substance in grams divided by molar mass of the same substance, that gives me number of moles of the substance. How do we apply it? You'll get the idea in some time. First of all, let me write all the other results. Second one. This was the first one. Second one. Number of moles of the substance. Number of moles of the substance, which is again equal to, which is again represented by N. Which is again represented by N. It is equal to. Given number of particles. Given number of particles of the substance divided by the Avogadro's number. Divided by the Avogadro's number. The third result, which is only valid for gases. Number of moles of gases. Number of moles of a gas. But the gas has to be present at STP, standard temperature pressure. The gas has to be present at STP. It is equal. As per the old convention, it is equal. Given volume of the gas in liters divided by 22.4 liters. Given volume of the gas in liters divided by 22.4 liters. This third result is only valid for what? This third result is only valid for gases. The first two results, they are valid for solids, liquids, as well as gases. This result is also valid for solids, liquids, as well as gases. But the third result, it's only valid for gases. So my dear students, in short, if I ask you, how many results do we have to calculate moles? In order to calculate moles of a substance, number one, given mass of the substance divided by molar mass of substance. That gives me moles. Second, number of moles is always equal to given number of particles divided by Avogadro's number. Third, is only valid for gases. Gas has to be present at STP. Gas has to be present at STP, right? Standard temperature pressure. So it is equal to given volume of the gas in liters divided by 22.4 liters. Okay? Right? Now, let's exactly analyze how do we use these formulas. Let's exactly analyze how do we use these formulas. Where do we use these formulas? Right? That's important. That is important. I hope you're clear with these three formulas, right? Are you done with this? Are you done with this? Yes, divided by 22.4 liters this is. As per the old STP convention. Perfect. Now guys, if you are done with this, can we solve these basic simple questions? Can we solve these basic simple questions? The first question is, calculate the number of moles in 160 grams of NaOH. As per the question, we are given with 160 grams of NaOH. So basically, we are given with mass of a substance. And when we are given with the mass of the substance, and we have to calculate moles. So given mass of substance in grams divided by molar mass of substance. So I'll simply say number of moles of NaOH will be equal to given mass of the substance in grams divided by molar mass of the substance. Molar mass of NaOH will be equal to, this is 23 plus 16 plus 1, which comes out to be 40. So 40, and it's going to be grams per mole. So the value comes out to be 4. Right? I was given with the mass of NaOH. I was given with the mass of NaOH. I was supposed to convert the mass into moles. So given mass divided by molar mass, that gives me moles. Given mass of the substance is 160 grams. Molar mass of NaOH is 40 grams per mole. So given mass by molar mass is giving me the moles. So I can say 160 grams of NaOH. It simply means 4 moles of NaOH. 160 grams of NaOH simply means 4 moles of NaOH. That's all. Second, calculate the number of moles in 67.2 liters of carbon dioxide gas at STP. Look here, we are given with the gas. And for gases, we just have one formula. Given volume of the gas in liters divided by 22.4. So, the second one. The second question. Number of moles of carbon dioxide. Number of moles of carbon dioxide is equal to given volume of carbon dioxide in liters divided by what? 22.4. The value comes out to be 3. Now, it's completely your wish. Whether you want to say that you have got 67.2 liters of carbon dioxide, or you can say we have got 3 moles of carbon dioxide. One and the same thing. Right? Given volume in liters divided by 22.4 liters. That gives me the number of moles of the substance. The third result. Number of moles present in these many atoms of carbon. So basically we are given with the particles. And whenever we are given with the particles, how do we convert moles? Given number of particles divided by Avogadro's number. So I'll say number of moles of carbon will be equal to given number of particles, which is 24 into 10 raised power 23, divided by Avogadro's number, which is approximately 6 into 10 raised power 23. The value comes out to be 4, because this term gets cancelled. Now it's your choice whether you want to say that we have got 4 moles of carbon, or we can say we have got these many atoms of carbon. One and the same thing. Okay? The fourth one. What are we given with? We are given with molecules. We are given with molecules of what? Molecules of water. Molecules means particles. So again, given number of particles divided by Avogadro's number. So number of moles of water is equal to given number of particles divided by Avogadro's number, which is approximately 6 into 10 raised power 23. So this term and this term gets cancelled. 6 1 6 8 8 10s are 80. So whether you want to say that we have got these many molecules of water, or you can say we have got 80 moles of water, both the things means the same. So in short, how many formulas do we have to calculate moles? In short, how many formulas do we have to calculate moles? We have got how many results? We have got 3 results to calculate moles. We have got 3 results to calculate moles. First one, when mass of the substance is given mass by molar mass, that gives me moles. Second, given number of particles divided by Avogadro's number. Given volume of the gas divided by 22.4 liters at STP. Right? The first 2 results are valid for solids, liquids, as well as gases. The third result is only valid for gases. Right? The third result is only valid for gases. I hope I'm clear. I hope I'm clear. Now, guys, something which is important and simple at the same time, right? Which will solve a lot of basic questions of your mole concept. A lot of basic questions. Try to understand. My dear students, just tell me one thing. In order to calculate moles of any substance, how many ways do we have? How many ways do we have? 3 ways. Either I will be given with the mass of the substance in grams. Either I'll be given with the mass of the substance in grams, or I will be given with the number of particles of the substance, or I will be given with the number of particles of the substance, or I can say I will be given with the volume of the gas, or I'll be given with the volume of the gas in liters at STP. Right? If any of these 3 things is given to me, I can calculate moles. If any of these 3 things is given to me, I can calculate moles of the substance. And you know it now. You know it now. Have a look. The first thing. My dear students, if mass of the substance is given and you are supposed to convert mass into moles, how do you do it? Given mass of the substance in grams divided by molar mass of the substance, that gives you moles. Given mass divided by molar mass, that gives me moles, right, of a substance. Or if you want to do the reverse of it, imagine that you are given with moles and you are supposed to convert moles into mass. Imagine you want to convert moles into mass. How do you convert moles into mass? Moles multiplied by molar mass. Moles multiplied by molar mass of substance gives you the mass of the substance. Simple. Simple. Guys, simple. You know the formula. Number of moles is equal to given mass divided by molar mass. Given mass divided by molar mass, right? Okay. One thing. If mass is given, moles are to be calculated. Then given mass divided by molar mass gives you moles. Given mass divided by molar mass gives me moles. Or if moles are given and mass is to be calculated, how? Moles multiplied by molar mass. That gives me mass. That's what I mentioned over here. Given mass divided by molar mass gives me moles. Moles multiplied by molar mass gives me mass. Nothing else. Yeah? Nothing else. Similarly, if number of particles are given to me, given number of particles divided by Avogadro's number, given number of particles divided by Avogadro's number, that gives me moles. Similarly, moles multiplied by Avogadro's number, that gives me particles. Just reverse. Moles multiplied by Avogadro's number, that gives me particles. Right? Similarly, people, given volume of the gas divided by 22.4 liters. Given volume of the gas divided by 22.4 liters, that gives me moles. And similarly, moles multiplied by 22.4 liters, that gives me volume of the gas at STP. Right? Simple. Simple, guys. Simple diagram which you are going to remember, and with the help of this diagram, we can solve a lot of basic questions. Right? You just have to remember this diagram. Perfect. How do we utilize this diagram? How do we use this diagram? For that, some basic questions will do, so that you will be familiar with the fact how this particular diagram is used. Look at this first and the basic question. Calculate the mass of 67.2 liters of carbon dioxide gas at STP in grams. Just understand one thing. look into the question and understand what is given and what is to be calculated. Just tell me that. What is given and what is to be calculated? My dear students, I am given with volume of the gas. I'm given with volume of the gas. And I'm supposed to convert volume into mass. I'm supposed to convert volume into mass. I'm supposed to convert volume into mass. Do you understand? Imagine that. In the container, there are 67.2 liters of carbon dioxide. And I have to check what is the mass of those 67.2 liters of carbon dioxide. So I need to convert volume into mass. I need to convert volume into mass. Now, is there any direct result between volume and mass? There is no direct result between volume and mass. There is no direct arrow between volume and mass. Right? As per the question, I am given with volume. I'm given with volume. I'm supposed to convert volume into mass. I'm supposed to convert volume into mass. So what you'll be doing? You'll be following this diagram. Right? You'll be following this diagram. How exactly you are going to follow this diagram? My dear students, remember one thing. Remember just one thing. Whatever is given to you, start from there. Whatever is to be calculated, reach there. Whatever is given, start from there. What is to be calculated, reach there. And follow all the arrows. Follow all the arrows that take you from given quantity to the calculated quantity. Follow all the arrows that take you from the given quantity to the calculated quantity. So in this particular question, I'm given with what? I'm given with volume. I'm supposed to calculate mass. I'm given with volume. I'm supposed to calculate mass. Right? I'm supposed to calculate mass. So in this diagram, I'll be starting with volume. I'll be ending at mass. So whatever arrows will take me from volume to mass, I'll be following all those arrows. That's all. The first arrow has to be this one. Second arrow has to be then this one. Perfect. So in 2 steps, this question will be done. First step will be whatever is the given volume, divide that with 22.4 liters. You'll be getting the moles. Once you get moles, multiply that with the molar mass of the substance. You'll be getting the mass. We are done. We are done. Right? So in order to solve the first question, 2 steps are there. First step, convert the given volume into moles. Right? So first of all, I'll be calculating the number of moles of carbon dioxide, which is equal to given volume of carbon dioxide in liters divided by 22.4 liters. The value is 3. So I calculate moles. Second step, moles into mass. So second step, mass of carbon dioxide in grams will be equal to moles of carbon dioxide multiplied by molar mass of carbon dioxide, which we saw from the diagram. How many moles of carbon dioxide we have? 3. Multiplied by molar mass of carbon dioxide is 44 grams. The value simply comes out to be 132 grams. So it simply means 67.2 liters of carbon dioxide at STP will have the mass of how much? 132 grams. As simple as that. Right? My dear students, simple things. First thing, in the question, first identify what is given and what is to be calculated. In this question, volume was given, mass was to be calculated. So we started from volume, and we ended at mass. Whatever arrows take me from volume to mass, just follow all those arrows. So this has to be a first arrow, this has to be a second arrow. In the first step, given volume has to be divided by 22.4 liters, so you'll be getting the moles. Once you get moles, multiply that with molar mass of the substance, you'll be getting the mass. That's all. Right? This was the first and the basic question. Look at the second one. Look at the second question. Look at the second question. Second question. Calculate the number of molecules. Number of molecules means particles, right? Present in 440 grams of carbon dioxide. So mass is given, molecules are to be calculated. Mass is given. Mass is given. Molecules means particles are to be calculated. Mass is given. Particles are to be calculated. So you'll be starting from mass and you'll be reaching the particles. Whatever arrows will take me from mass to particles, I'll be following all those arrows. The first arrow has to be this one. This is going to be my first arrow, and then this is going to be my second arrow. By following these 2 arrows, I'll go from mass till particles. So my first step is going to be given mass divided by molar mass. That's going to give me moles. Once I get moles, multiplied by Avogadro's number, that's going to give me the particles. Right? Done and dusted? So my first step here will be number of moles of carbon dioxide is equal to given mass of carbon dioxide in grams divided by molar mass of carbon dioxide, right? The value comes out to be 10. So I got moles. Now second, to calculate volume of carbon dioxide. That will be moles of carbon dioxide multiplied by 22 not volume. We have to calculate what? We have to calculate particles. Particles means molecules. So second step, molecules of carbon dioxide will be equal to moles multiplied by Avogadro's number. So 10 Na is the final answer. Is it simple? Isn't it simple, guys? So I believe from now onwards, you can easily utilize this formula, this diagram. So you'll be starting from where, which is given in the question, right? And you'll be reaching what is to be calculated. You'll be reaching there. Simple. Am I clear with this? Tell me once in the chats. Can you solve this question? Look at the question. Calculate the volume of 128 grams. Calculate the volume of 128 grams of carbon dioxide. So mass is given, volume is to be calculated. So start from mass and reach volume. Start from mass. Start from here and finally reach here. Start from here and reach here. What all arrows take me from mass to volume? What all arrows take me from mass to volume? So this is the first arrow and this is the second arrow. So two steps. First step, given mass divided by molar mass gives me moles. Moles multiplied by 22.4 gives me volume. Done and dusted, right? So I'll be writing the first step. Number of moles of carbon dioxide is equal. Given mass of carbon dioxide in grams divided by molar mass of carbon dioxide. This is going to give me the moles. Once I get moles from here. Once I get moles from here. Moles multiplied by 22.4 liters. That will give me the volume. So moles are, so volume of carbon dioxide will be moles of carbon dioxide multiplied by 22.4 liters. Moles we have calculated from here. Multiply that with 22.4 liters. You'll be getting the volume of carbon dioxide. Is it simple? Simple questions. So again, I'm summarizing the same thing, guys. Again, I'm summarizing the same thing. Right? If, for example, mass is given, volume is to be calculated. Start from mass, reach the volume. Use all the arrows that take you from mass to volume. Imagine, if volume is given, particles are to be calculated. Start from volume, reach the particles. Follow all the arrows that take you from volume to particles. For example, particles are given, mass is to be calculated. Start from particles and reach the mass. And what all arrows take you from particles to mass, follow all those arrows. That's all. Yes? Am I clear, people? Am I clear? So whatever they ask you, your first step always is to convert the given quantity, which can be mass, volume or particles. Your first step always is going to convert the given quantity into moles. And from moles, you can calculate anything. Is it crystal clear? Let me know once in the chats with some fire emojis quick so that I can move on. Look at this question now. Look at this question, people. Look at this question. If you look at the question carefully, the mass of one atom of X, is equal to this much. Calculate the number of moles present in 96 kg of X. So basically, we are given with 96 kg, means 96,000 grams of X. And we have to calculate how many moles are present in 96,000 grams of X. We have to calculate how many moles are present in 96,000 grams of X. So what is given? Mass is given. What is to be calculated? Moles are to be calculated. Which formula I'll be using? Mass of X in grams divided by molar mass of X. Mass of X in grams divided by molar mass of X. What is the mass of X in grams? It is 96,000 divided by. What is the molar mass of X? Do you remember, guys? I've taught you long back. Molar mass of X is equal to mass of one atom of X in grams multiplied by Avogadro's number. Now, what is the mass of one atom of X here? 4 into 10 raised power minus 23 grams. You'll be multiplying it with 6 into 10 raised power 23. Now this term in the denominator, now this whole term in the denominator is going to give me the molar mass of X. Yes? Simple? Perfect. So 10 raised power this, 10 raised power this cancel. So it comes out to be 96,000 divided by 24. 96,000 divided by 24 has to be 4,000. So 4,000 is the final answer. Simple. So what does it mean? It means that 96 kg of X means 4,000 moles of X. Right? Am I clear? Am I clear, people? Am I clear? Someone is saying quality of the video is not clear. I think you need to change your quality. I can clearly see it over here. It's like properly clear. Just improvise your settings in the phone or laptop, wherever you're watching this video from, right? Just improvise the quality. Perfect. Perfect, people. Let's move on to one more question then. Okay, look at this question. What do you think? Can you solve this question? Simple. This is again one asked question. It's a PYQ of JEE Mains. It's a PYQ of JEE Mains. How many moles of electrons? How many moles of electron weighs 1 kg? 1 kg means 1000 grams. 1 kg means 1000 grams. So what are we given with? We are given with mass. What are we supposed to calculate? We are supposed to calculate moles. How do you convert mass into moles? How do you calculate mass into moles? Number of moles of electrons will be equal mass of electron in grams divided by molar mass of electron divided by molar mass of electron, right? Now, what is the mass of electron that's given to me? 1000 grams divided by, what is the molar mass of electron? Molar mass of electron means mass of 1 mole of electron, means mass of 6.022 into 10 raised power 23, 10 raised power 23 electrons. How do we get the molar mass of electron here? Molar mass of electron means mass of 1 electron in grams, mass of 1 electron in grams, and multiply it with 6.022 into 10 raised power 23. Now, this whole term in the denominator is going to give you the molar mass of electron. This is going to give you the mass of 1 mole of electron. This is going to give you the mass of 6.022 into 10 raised power 23 electrons, which is what you call as molar mass of electron. So given mass divided by molar mass. Just a matter of calculation. Solve it and you're done. Yes? Simple? Simple, guys? Am I clear with this? I hope this is super clear to everyone. Look at this question. It is again a PYQ. Again a PYQ. Equal masses of H2, O2 and CH4. So we are given 3 gases. If you look carefully, we are given 3 gases. Which all? We are given with H2, we are given with O2, and we are given with CH4. As per the question, we are given with equal masses of these 3 gases. Equal masses of these 3 gases. Let's assume mass of hydrogen is X grams. Mass of oxygen is also X grams. Mass of CH4 is also X grams. Since as per the question, we are given with equal masses of these 3 gases. Right? Under identical conditions. The ratio of their volumes. Remember one simple thing. Ratio of volume is same as that of ratio of volume is same as that of ratio of moles. Is same as that of ratio of moles under identical conditions. Under identical conditions. What do I have to calculate? I have to calculate ratio of volume. In order to calculate ratio of volume, I just need ratio of moles. That's all. Now, what am I given with? I'm given with masses. What do I need? I need the ratio of the moles. First of all, let's calculate the moles of H2. Given mass of H2 divided by molar mass of H2. Given mass of O2 divided by molar mass of O2. Given mass of CH4 divided by molar mass of CH4. XXX. If you want to calculate the ratio of the moles, XXX gets cancelled. This is 1 by 2 is to 1 upon 32 is to 1 upon 16. This is the ratio of the moles, right? But if I ask you what is the LCM of these denominators over here? LCM of denominators. LCM of 2, 32 and 16. LCM of 2, 32 and 16. That is 32. Multiply all of them by 32. Multiply all of them by 32. By the LCM basically. By the LCM. So 2, 1 to 16. So it's 16 is to 32, 32 cancel 1. 16, 1, 16, 2. So 16 is to 1 is to 2 is the ratio of the moles of these gases And whatever is the ratio of the moles of the gases, same is going to be the ratio of their molecules. Right? Perfect. Perfect, guys. Quick in the chats. If all the things are clear. Everyone. Yeah? Yes, mass of electron in grams is 9.1 in 10 raised power minus 28 grams. Right? In kg, that is minus 31. But we have to take mass in grams. I hope you can easily solve this sort of equation if it is asked. Okay. Tell me about this one. Can you solve this one on your own? Again, the asked question. Again, the asked question. Again, the asked question. Again, a PYQ. Perfect. Solve it. Quick. I mean, you should be able to solve this one. A mixture contains gases H2 and O2 in the mass ratio of 1:4. Calculate their molar ratio. So, the ratio of the masses of these two gases. What does that mean? I can write it like this. Mass of H2 divided by mass of O2. This is given to me as 1:4. This is my given data. What do I need to calculate? I need to calculate the ratio of their moles. That means I need to get this value. Moles of H2 divided by moles of O2. This is something I need to calculate. Now guys, it's simple. Moles of H2 means mass of H2 divided by molar mass of H2. Moles of O2 means mass of O2 divided by molar mass of O2. Now, as per the question, this particular term, WH2 by WO2, it is already given to me as 1/4 multiplied by molar mass of O2 is nothing but 32 grams divided by molar mass of H2 is 2 grams. So it's going to be 4:1, right? 4:8, right? It's going to be 4:1. So 4:1 is the answer of the question. So I can say number of moles of H2 is to number of moles of O2 is equal to 4:1. This is something which I was supposed to calculate to get the ratio of their moles, right? Perfect. Perfect, people. I hope this is clear to everyone. I hope this is clear to everyone. This is again your PYQ, guys. Again your PYQ, and you should be in a position to solve this. The number of water molecules is maximum n. Number of water molecules is maximum n. So we have to calculate molecules. What am I given with? I'm given with mass. So from mass to molecules. From mass to molecules. First step will be number of moles of water is equal to given mass of water in grams divided by molar mass. The value is 0.1. I got the moles. Now moles multiplied by Avogadro's number. That gives me molecules. So how many molecules of water we have here? Moles multiplied by Avogadro's number. So in the first case, there are 0.1 Na molecule of water. Look at the second case, 18 grams of water. So convert mass into moles first of all. Given mass in grams divided by molar mass of water, the value is 1. So molecules will be moles multiplied by Avogadro's number. Moles multiplied by Avogadro's number. So these many molecules are in the second one. In the third one, already there are moles given, 18 moles. How do you convert moles into molecules? Moles multiplied by Avogadro's number directly. So molecules of water in this case will be equal to moles multiplied by Avogadro's number. So these are the molecules of water in the third case. And in the last case, already they have given the molecules only. Now, which of the following is the largest value? Which of the following is the largest value? Quick. 0.1 Na molecules, 1 Na molecules, 18 Na molecules, or 18 molecules. Which of the following contains maximum number of molecules? It has to be option C. I hope this is clear. I hope this is clear, people. I hope this is clear. Okay. One more question. You might do a mistake here. Look at this one. Look at this one, guys. And check whether you can solve this question or not. Quick. Check whether you can solve this question or not. Quickly. I believe you should be in a position to solve this question. You You should be in a position to solve this question. Calculate the number of molecules present in 1.8 liters of H2O. But this is H2O liquid. This is not gas. This is not gas. This is not a gas. Now, how do you solve this? We have to basically convert volume into molecules. Now, normally you'll be thinking we'll be starting from the volume and we have to reach the molecules. So let's do one thing. Given volume divided by 22.4, that gives me moles. Moles multiplied by Avogadro's number, that gives me molecules. If you are thinking like this, you're gone. You're over. Because given volume by 22.4 liters, that's valid for gases. Here, you are not given with a gas. You are given with a liquid. So what I'll be doing first of all, understand. 1.8 liter water means 1800 ml water. It means 1800 ml water, right? Since 1800 ml water means 1800 grams of water, right? 1800 grams of water. Perfect. So imagine as if we were not given with the volume of water. Imagine you were given with the mass of the water. Because 1.8 liter water means 1800 grams of water. Yeah. Perfect. 1.8 liter water means 1800 grams of water. Now imagine you are given with mass of water. From mass, you have to calculate molecules. So from mass, you have to calculate molecules. So first step, given mass divided by molar mass gives you moles. Moles multiplied by Avogadro's number. That gives you molecules. Simple. Perfect. Right, people? So my first step, number of moles of water will be equal to given mass of water in grams, which is 1800, divided by, what is the molar mass of water? That is 18 grams per mole. The value comes out to be 100. Perfect. So first step is over. Given mass divided by molar mass. That gives me moles. Second step, moles multiplied by Avogadro's number. That gives me molecules. So molecules of water will be equal to moles multiplied by Avogadro's number. This is the final answer. Am I clear with this, people? Am I clear with this, people? Quickly, everybody. Everybody, people. Everybody, is it clear? I think you guys deserve a break now. Yeah? We are almost done with 3 hours. Should we take a break here? Should we take a break here, guys? Should we take a break here? Yes or no? PDF I'll send you in my Telegram, which is Wassim Bhat Chemistry Official. I'll send in my Telegram. No need to worry. Okay, let's take a break for 30 minutes then, right? But guys, you have to make a promise with me that you all will be back by 8:30. If yes, then okay. Then let's take a break. Yeah? I would want every one of you to be back exactly at 8:30. I'll be starting again sharp at 8:30, guys. Okay? I'll be starting exactly at 8:30 back. So whatever basics was there in this chapter, yes, it's a dinner break. It is a dinner break. It is a dinner break. It is a dinner break. Okay, have your dinner. I'll also have mine. And we'll be back exactly at 8:30 and we'll start again. How many hours? This will be over at, I think, 2 a.m. Okay? Chalo. See you guys in a while. See you all in a while, okay? Have your dinner, come back. But come back. Yeah? So let me keep some lights off for some time. Is everyone back? Welcome back, guys. Welcome back. Welcome back. What's up? How are you all? Are you guys done with your dinner? Are you guys done with your dinner? Yeah? All right. That's great. So let me once in the chats. Whatever things we have discussed till now, is every single thing clear till now? Is every single thing clear till now? Whatever things we have discussed. And I would want the honest answers. I did not have my dinner yet. I just had some tea. I'll have dinner afterwards. Because when you have dinner, you get sleepy. I don't want to be sleepy. Just give me a second. Let me fix the lights. Just a second. No, you guys won't be sleepy. I know that. All right then. Should we start again? All ready? All ready, people? Should we start again? Perfect. Chalo then, let's get going. So my dear students, our next topic is calculation of atoms, electrons, protons, neutrons, ions. From this particular topic also questions are sometimes asked, right? And let me tell you, simple, basic questions are asked from this particular topic. So let's get to know how do we do the calculation of these atoms, electrons, protons, neutrons, ions, etc. One-on-one, we'll do all these things. Okay? First of all, my dear students, let me give you one block diagram. The way I gave you the mole conversion diagram. In the similar way, I'll be giving you one diagram over here, which you are going to remember first of all. And then I'll show you how to apply that diagram in the questions. Okay, first, the diagram which I'm going to give you, that is to be remembered. Understand, guys. Over here, I'm writing a term, given quantity. Over here, I'm writing a term, given quantity. What does that mean? My dear students, whatever is given to us in the question, whatever is given in the question, be it mass of the substance, volume of the substance, particles of the substance, whatever is given in the question, that is something which I'll be calling from now onwards as given quantity, right? If we are given with mass of substance or volume of substance, particles of substance, whatever is given in the question, that is something which I'll be calling as given quantity. My dear students, the first thing always is going to be to convert the given quantity into moles. This will be always my first step, to convert the given quantity into moles, right? If the given quantity is mass, we know how to convert mass into moles. Given mass by molar mass, right? If the given quantity is volume of the gas at STP, divided by 22.4, that gives me moles, right? So basically whatever is given to us as per the question, you'll be calling that as given quantity, right? Now, my dear students, you'll be converting that given quantity into number of moles. That is your first step always, right? Just give me a second. Again, there is a electricity cut, I think. Just a second, guys. Just a second. Yeah, it's fine now. Just a second. Okay. All right, look now. So first of all, my first step is always going to be convert the given quantity into moles. That's always my first step. Number one. Number two. My dear students, if the given substance is in molecular form, given substance means the one whose data is given, right? The one whose data is given. If the given substance is in molecular form, at that point of time, moles multiplied by Avogadro's number. Moles of that substance multiplied by Avogadro's number. That's going to give me the molecules. Once I get the molecules, from the molecules, we can easily calculate atoms, we can calculate electrons, we can calculate protons, we can calculate neutrons, even we can calculate ions, right? This is the diagram which we are supposed to follow. First of all, whatever is the given quantity, convert the given quantity into moles, right? Now, if the given substance is in molecular form, at that point of time, moles multiplied by Avogadro's number, that gives me molecules. Once we calculate molecules, atoms, electrons, protons, neutrons, etc., they can be easily calculated. Okay? Now, my dear students, let's try to utilize this diagram in the questions so that you will understand what kind of questions can be asked out of this. Okay? Let's try to understand that. See, the first and the basic question which we have on the screen. Calculate the total number of atoms. Present in 448 liters of carbon dioxide gas at STP. So what do we have to calculate? We have to calculate atoms. And in order to calculate atoms, we'll be following this particular diagram. The first step, given quantity into moles. My dear students, try to identify what is our given quantity here. We are given with volume. Of the gas at STP, right? And we know how to convert volume into moles. So my first step is number of moles of carbon dioxide gas. It is going to be equal to given volume of carbon dioxide gas in liters divided by 22.4 liters. The value comes out to be 20. So my first step is done. We have converted the given quantity into moles. Now look at the given substance. The given substance is in molecular form. Right? My dear students, I told you already, if the given substance is in molecular form, then moles multiplied by Avogadro's number, that gives me the molecules. So my second step is to calculate the molecules of carbon dioxide. That will be equal to moles of carbon dioxide multiplied by Avogadro's number. So I have calculated the molecules. Second step is done. Right? I have calculated the molecules. Perfect. So I've solved the question till here. Now from here, we just have to calculate atoms. Try to understand. My dear students, talk about one molecule of carbon dioxide. If I talk about one molecule of carbon dioxide, tell me one thing. In one molecule of carbon dioxide, how many total atoms are there? 2 plus 1, 3. Right? There are 2 oxygen atoms and 1 carbon atom. Perfect. So I would say one molecule of carbon dioxide contains 3 atoms. Now think over it. If one molecule of carbon dioxide contains 3 atoms, 2 molecules of carbon dioxide will contain multiplied by 2 atoms. 3 molecules will contain multiplied by 3. 4 molecules multiplied by 4. How many molecules of carbon dioxide we have? 20 Na. So tell me about 20 Na molecules of carbon dioxide. I would say 20 Na molecules of carbon dioxide will contain 3 multiplied by 20 Na. The value comes out to be 60 Na atoms. So these are the total number of atoms These are the total number of atoms which are present in 20 Na molecules of carbon dioxide. These are the total number of atoms which are present in 20 moles of carbon dioxide. These are the total number of atoms which are present in 448 liters of carbon dioxide gas at STP. And this is something which I was supposed to calculate. Done and dusted, right? Now, my dear students, one more thing. Since these are the total number of atoms, perfect? These are the total number of atoms which are present in 448 liters of carbon dioxide. Now, if I ask you, since we have calculated total number of atoms, right? Now, can I write a statement like this as well? Just look over it. Look at it properly. Can I say one molecule of carbon dioxide? If you talk about one molecule of carbon dioxide, one molecule of carbon dioxide contains one carbon atom. One molecule of carbon dioxide contains one carbon atom and two oxygen atoms. Right? Perfect. First of all, this was the calculation of total atoms. Now let's do the calculation of individual atoms. Have a look. One molecule of carbon dioxide contains one carbon atom as well as two oxygen atoms. Now tell me one thing. If one molecule of carbon dioxide contains one carbon, two molecules multiplied by 2, 3 molecules multiplied by 3, 4 molecules multiplied by 4. How many molecules we have? 20 Na. So I would say 20 Na molecules of carbon dioxide will contain 1 into 20 Na. The value comes out to be 20 Na carbon atoms. 20 Na carbon atoms and 2 multiplied by 20 Na, which comes out to be 40 Na oxygen atoms. Right? So this is something which we did extra over here. Right? This is the individual atom calculation. So I would say in 448 liters of carbon dioxide, in 20 moles of carbon dioxide, in 20 Na molecules of carbon dioxide, these many carbon atoms will be there and these many oxygen atoms will be there. If you take the sum of these two, 40 Na plus 20 Na, it will come out to be total atoms, which is 60 Na. I believe I'm clear with this. Yes? Yes, Lee, I'm from Kashmir. Yes. I'm from Srinagar. I hope this is super clear to everyone. Yeah? I believe this is super clear to everyone. Perfect, guys. Will you be able to solve these sort of questions? Just one block diagram is required. Given quantity into moles. Moles multiplied by Avogadro's number. Right? And then you know what I did. Perfect. Moving on. Have a look on this particular question. Calculate the total number of atoms. First of all, we have to calculate atoms. Then we have to calculate electrons, then protons, then neutrons in 44.8 liters of carbon dioxide gas at STP. Right? Now in this question, we have to calculate atoms, electrons, protons, neutrons, etc., etc. See, how do we do this sort of a calculation as well? Try to understand, people, what do I do over here? First of all, whenever we have to do atoms calculation, electron calculation, proton calculation, neutron calculation, what is the first step? Convert the given quantity into moles. Check your given quantity first of all. This is my given quantity. I'm given with volume. Of the gas at STP. So my first step is to convert the given quantity into moles. How do you convert moles? How do you convert volume into moles? So I'll say number of moles of carbon dioxide is equal to given volume of carbon dioxide in liters divided by 22.4. The value comes out to be 2. Right? So my first step is done. Converted given quantity into moles. Second step, check the given substance. The given substance is in molecular form. If the given substance is in molecular form, moles multiplied by Avogadro's number, that gives you molecules. So the second step, molecules of carbon dioxide. Molecules of carbon dioxide will be equal to moles multiplied by Avogadro's number. So these many molecules of carbon dioxide we have. Right? These many molecules of carbon dioxide we have. Now let's do the calculation of atoms first of all. Right? Let's do the calculation of atoms. My dear students, I'll write one simple statement. I'll write, since we know one molecule of carbon dioxide contains 3 atoms in total. Right? One molecule of carbon dioxide contains 3 atoms in total. If one molecule of carbon dioxide contains 3 atoms, 2 molecules will contain multiplied by 2, 3 molecules multiplied by 3. How many we have? 2 Na. So I would say 2 Na molecules of carbon dioxide will contain 3 multiplied by 2 Na. The value comes out to be 6 Na atoms in total. 6 Na atoms in total, right? So this is the calculation of atoms. This is the calculation of atoms, right? This is the calculation of atoms. Now, I got to know people, I got to know in 44.8 liters of carbon dioxide, there are 6 Na atoms in total. Perfect. Now tell me one thing. What is the second thing which I'm supposed to calculate? Electrons. Electrons, right? Second thing is electrons. Now, first of all, the way we analyzed one molecule of carbon dioxide in terms of atoms, in the similar way, let's try to analyze, one molecule of carbon dioxide in terms of electrons. One molecule of carbon dioxide contains how many electrons, how many protons, how many neutrons? Let's get to know that. See, if you talk about carbon dioxide, carbon, oxygen, CO2, right? CO2. Its atomic number is 6, mass number 12. This is 8, this is 16. This is 8, this is 16, right? So if I talk about protons, tell me, how do you get the protons in the atom? Whatever is the atomic number of carbon here is 6. That means in one atom of carbon there are 6 protons, plus in one atom of oxygen there are 8 protons. In one atom of oxygen there are again 8 protons. So in total 8 is 16, 16 plus 6 is 22. So I would say in one molecule of carbon dioxide there are 22 protons. Tell me about electrons. How do you get the electrons here? Again, atomic number is going to play a role. In one atom of carbon there are 6 electrons. In one atom of oxygen, 8 electrons. In one more atom, 8 electrons. So again, 22 electrons. How do you get the neutrons? Mass number minus atomic number. 12 minus 6 is equal to 6, plus 16 minus 8 is equal to 8. 16 minus 8 is equal to 8. So how many neutrons? 22 neutrons. Right? So my dear students, I got to know in one molecule of carbon dioxide, there are 22 protons, there are 22 electrons, as well as 22 neutrons. This is something which I'm talking about. This is something which I'm talking for one molecule of carbon dioxide. So in one molecule of carbon dioxide, this is the data. In 2 molecules of carbon dioxide, multiply with 2. 3 molecules of carbon dioxide, multiply with 3. 4 molecules of carbon dioxide, multiply with 4. How many molecules of carbon dioxide we have? 2 Na. So 2 Na molecules of carbon dioxide will contain 22 into 2 Na comes out to be 44 Na protons. Similarly, 22 into 2 Na, 44 Na electrons. Similarly, 44 Na neutrons. This is something which I was supposed to calculate as well. And we are done with it. Is this particular question clear to you? Let me know once in the chats quick. Let me know once in the chats quick, people. If this is clear, let me know once in the chats quick. Everybody. 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 Everybody in the chats. Quickly, people. Perfect. It's all clear. Amazing. Let's move on then. Let's move on, people. If you remember, I told you one thing. I told you if the given substance is in molecular form, at that point of time, moles multiplied by Avogadro's number, that gives me molecules. Now, guys, if the given substance is in atomic form, at that point of time, moles multiplied by Avogadro's number, that is going to give me the atoms directly, right? That's going to give me the atoms directly. Perfect. If the given substance is in atomic form, at that point of time, moles multiplied by Avogadro's number, that gives me atoms directly. And similarly, if the given substance is in ionic form, at that point of time, moles multiplied by Avogadro's number, that gives me ions directly. Right? And this is something which we already know. This is something which we already know. If the given substance is in molecular form, at that time, moles multiplied by Avogadro's number, that gives us molecules. These are some basic, simple things wherein a lot of students, they get confused at the end. So I'm writing them one by one. Okay, do remember all these things. Now, let's try to solve one more question so that you'll understand and analyze things in a better way. This is your asked question. This has been asked in your NEET examination, right? And I believe you should be in a position to solve this particular question on your own, right? This is your PYQ. This is your PYQ. Look at it carefully. Calculate the valence electrons in 4.2 grams. Calculate the valence electrons in 4.2 grams of N3 negative. Of N3 negative, right? What do you have to calculate? Valence electrons, right? So again, I'll be following the diagram. What is the first step in the diagram? Convert the given quantity into moles. What is my given quantity? I'm given with mass. How do we convert mass into moles? Given mass by molar mass. Simple, right? So my first step, number of moles of N trinegative is equal to given mass of N trinegative divided by molar mass of this N. What is the molar mass of nitrogen? 14, right? The value comes out to be 0.3. Is the first step done? The first step is done. The first step is done. The first step is done. Yeah? Now guys, understand one more thing. The first step is done. We have calculated moles. Second step, check the given substance. The given substance is in ionic form, right? And when the given substance is in ionic form, at that point of time, moles multiplied by Avogadro's number, that gives me ions directly. Yeah? That gives me ions directly. So I would say number of N trinegative ions will be equal to moles multiplied by Avogadro's number. So these many N trinegative ions we have. These many N trinegative ions we have. Now, my dear students, you tell me one thing. Talk about N trinegative. Talk about N trinegative. Okay? See, if I ask you, in one N trinegative, how many total electrons are there? Since atomic number of nitrogen is 7. If there was no charge on nitrogen, then there should have been 7 electrons in one atom of nitrogen. Perfect. But the charge is trinegative. That means it has gained 3 electrons. So 7 plus 3 comes out to be 10, right? So one N trinegative ion contains how many electrons in total? 10 electrons in total. Now tell me one thing. Out of these 10 electrons, how many electrons will be there in the first shell? In the first shell, there will be 2 electrons. In the second shell, there will be 8 electrons, right? So this second shell, I'll be calling as the valence shell, right? So these electrons, I'll be calling as valence electrons. So I can say one N trinegative ion. One N trinegative ion contains, one N trinegative ions contains 8 valence electrons. Now think over it. If one N trinegative ion contains 8 electrons, contains 8 valence electrons, 2 ions will contain multiplied by 2. 3 ions will contain multiplied by 3. How many ions do we have? 0.3 Na. So 0.3 Na N trinegative ions will be containing 8 multiplied by 0.3 Na valence electrons. The final answer comes out to be 2.4 Na valence electrons. So these are the total number of valence electrons which are present in 0.3 Na ions of N trinegative. These are the total number of valence electrons which are present in 0.3 moles of N trinegative. These are the total number of valence electrons which are present in 4.2 grams of N trinegative. Am I clear with this? Let me know with the thumbs ups quickly. Let me know with the thumbs ups quickly. Yes? Let me know with the thumbs ups quickly. Look at one more question. Calculate the atoms in. The first question, calculate the atoms in. So we have to calculate atoms, right? We have to calculate atoms. Now, my dear students, understand carefully. In order to calculate atoms, what is the first thing? Convert the given quantity into moles. What is the given quantity? Mass. We are given with mass of helium. So, my first step, number of moles of helium is equal to given mass of helium in grams divided by molar mass of helium. The value comes out to be 4, right? So my first step is done. Given quantity into moles, done and dusted. Now look carefully. The given substance is in atomic form. When the given substance is in atomic form, at that point of time, moles multiplied by Avogadro's number, what does that give me? That gives me atoms directly. So how many atoms of helium do we have? I'll say atoms of helium will be equal to moles multiplied by Avogadro's number. Aren't we done? We were supposed to calculate atoms only. And we got to know atoms are 4Na. So basically, in 16 grams of helium, there are 4 Na atoms present. There are 4 Na atoms present. Done and dusted. Number one. Number two. You might do a mistake over here in the second question. Calculate the atoms in 16U. 16U of helium. Right? 16U of helium. We have to calculate again the atoms. So my first step, convert the given quantity into moles. Right? What is the given quantity? Given quantity is mass. But mass is not given in grams. It is given in U. It is given in U. Right? It should have been in grams. But it is given in U. So how do I solve it? How do I get the atoms? Guys, very simple. Just use your common sense. If I talk about helium, what is the atomic mass of helium? 4U. Right? Yeah? What is the atomic mass of helium? That is 4U. What does that mean? I can say 4U is basically the mass of one atom of helium. 4U is basically the mass of one atom of helium. If I use the unitary method, if 4U is the mass of one atom of helium, what do you think about 1U? Can I say 1U will be the mass of 1 by 4 atoms of helium? Right? 4U is the mass of one atom of helium. Therefore, 1U has to be equal to the mass of 1 by 4 atoms of helium. Am I given with 1U or 16U? I'm given with 16U. Now tell me, what about 16U? Can I say 16U of helium will be equal to 1 by 4 multiplied by 16 atoms of helium? Which comes out to be how much? 4144. So it is going to be basically 4 atoms of helium. So 16U of helium. 16U of helium means 4 atoms of helium. In short, done and dusted. Yes? Clear? Did you understand why I used this approach? Because here the mass was not given in grams. If it was given in grams, then I would have followed the similar approach as I did in the first question. Right? Similarly, my dear students, you can solve the next one. Calculate the molecules in 126U of HNO3. You have to calculate molecules, right? You have to calculate molecules. What is the first thing? Given quantity into moles, right? Second, moles multiplied by Avogadro's number. That is going to give you molecules. But, look at the given quantity. It is mass. But mass is not given in grams here. It's again in AMU. So I'll be following this approach only. Understand how? If you talk about HNO3, my dear students, if I ask you, what is the molecular mass of HNO3? You will say molecular mass of HNO3. 1 plus 14 plus 16 into 3. That will be 63U. This is the molecular mass of HNO3. What does that mean? That means this is the mass of one molecule of HNO3. This is the mass of one molecule of HNO3. If this is the mass of one molecule of HNO3, tell me what about 1U? Can I say 1U will be the mass of 1 upon 63 molecules of HNO3? Right? As per the question, am I given with 1U or 126U? 126U. Can I say 126U has to be equal to 1 upon 63 multiplied by 126, which comes out to be 2 molecules of HNO3. Right? So I can clearly say 126U means 2 molecules of HNO3. That's all. This is something which I was supposed to calculate. Done and dusted. If I'm clear, let me know once in the chats, then only I can move on to one more topic. Quickly, people, in the chats with some fire emojis. Everybody. All clear? All clear, people? All clear? Perfect. Wonderful. Good job. Let's have a look on one more small topic, but important at the same time, because questions have been asked from this topic as well, right? Let's try to understand it in a very simple way. Okay? See, guys, understand properly. First of all, I'm going to write one statement. I'm going to write one statement. The statement is like this. The statement is like this. I'll write 1 mole carbon dioxide. 1 mole carbon dioxide. Okay? Can you let me know in 1 mole carbon dioxide, how many moles of carbon are there? I'll say in 1 mole carbon dioxide, there is 1 mole carbon. 1 mole carbon dioxide contains 1 mole carbon, right? At the same time, 1 mole carbon dioxide contains 2 moles of O as well. It contains 2 moles of O as well, correct? Or let me make it more simple for you. Let me make it simpler for you. See how? See how? If I write 1 molecule of carbon dioxide, tell me, in 1 molecule of carbon dioxide, how many atoms of carbon do you see? 1 carbon atom. 1 carbon atom. How many oxygen atoms? 2 oxygen atoms. 2 oxygen atoms. One more thing, guys. Understand. Here I have taken oxygen in atomic form. Here I have taken oxygen in atomic form. Here I have taken oxygen in atomic form. If I take oxygen in molecular form in the same statement, should I be writing 2 oxygen atoms, or I should write 1 O2 molecule? I should write 1 O2 molecule. I'll say 1 molecule of carbon dioxide contains 1 oxygen molecule, which means 2 oxygen atoms. I hope you're getting this. Yeah? I hope you're getting this. Now, my dear students, if I multiply this equation throughout by Avogadro's number, instead of 1 molecule, you'll be writing Na molecules. Na molecules of carbon dioxide contains 1 carbon atom, I'll write Na carbon atoms. Na carbon atoms. 2 oxygen atoms means 2 Na oxygen atoms. 2 Na oxygen atoms. Similarly, 1 O2 molecule means NaO2 molecules. What did I do? I wrote a statement. And at the same time, I multiplied the same statement with the Avogadro's number. Now, people, understand one thing. Na molecules of carbon dioxide, what does that mean? Na molecules of carbon dioxide, what does that mean? That means 1 mole carbon dioxide. So instead of this term, I'll write 1 mole carbon dioxide. Because 1 mole carbon dioxide contains Na molecules of carbon dioxide, right? Na carbon atoms, 6.022 into 10 raised power 23 carbon atoms. What does that mean? That means 1 mole carbon. Right? Similarly, 2 Na oxygen atoms. That means, see, Na oxygen atoms means 1 mole oxygen. 2 Na oxygen atoms means 2 mole oxygen. So I'll write 2 mole O. Right? Now, NaO2 molecules means Na molecules means 1 mole. So 1 mole O2. 1 mole O2. Now, do you understand this statement? Right? I can simply write. Now, this is something which you need not to write all the time. You just can write the statement 1 mole carbon dioxide contains 1 mole carbon, 2 moles of O, and 1 mole O2. And 1 mole O2. Yes? Sir, do you know Amrit, sir? Yes, I know Amrit, sir. He is one of my very close friends, right? Yes, he was working in Xylem, right? I know him. He's a very good friend of mine. Okay? Perfect? Yes, he teaches biology. Now what? Yes, now he left that platform where he was working. He's a very close friend of mine. Okay. See guys, I hope this particular statement is clear. Now one more thing I have to tell you. One more thing. My dear students, I'm using the term mole over here. Is any other name given to moles? Is any other name given to moles? Sometimes instead of moles, you write gram atoms. Sometimes instead of moles, you write gram molecules also. Sometimes instead of atoms, you write gram atom. Instead of moles, you write gram atoms. Sometimes instead of moles, you write gram molecules. So basically, sometimes you'll be asked a question, calculate the moles of this, right? Sometimes the language will be changed. They won't ask you to calculate the moles. They'll ask you to calculate the gram atoms. Gram atoms also means moles. Sometimes they'll ask you to calculate the gram molecules. Gram molecules also means the moles, right? Gram molecules also means the moles. I hope I'm clear. Gram atoms, gram molecules means moles basically, right? Now try to understand. I'll write the same statement again in a different format. I'll write 1 mole carbon dioxide contains. 1 mole carbon dioxide contains. Carbon here is in atomic form. If the carbon is in atomic form, instead of mole, I can write gram atom. I'll write 1 mole carbon dioxide contains 1 gram atom of carbon. 1 gram atom of carbon, right? Oxygen here is in atomic form. So instead of moles, I can write gram atoms. So 2 gram atoms of oxygen. 2 gram atoms of oxygen. Here oxygen is in molecular form. So instead of moles, I can write gram molecules. I'll write 1 gram molecule of oxygen. 1 gram molecule of oxygen. I hope you got to know these two statements properly. If yes, let me know once in the chats quickly. Let me know once in the chats if all these statements are absolutely clear to you. Quickly, people. If all these statements are clear, just tell me one thing. One last statement I'm writing, then I'll show you how do we utilize these statements in the questions. Okay? Right? See guys, for example, I'm writing a statement, 1 mole H2SO4. 1 mole H2SO4. What all things can I write from this particular thing? Understand. 1 mole H2SO4 contains, I'll say it contains 2 moles of H. 2 moles of H, hydrogen in atomic form I'm taking. Now take the same hydrogen in molecular form. If you are writing 2 moles of H, that means 1 mole H2. That means 1 mole H2. Correct? Talk about oxygen. For example, talk about oxygen. I'll say 4 moles of O. 4 moles of O. And 4 moles of O means 2 moles of O2. Right? 2 moles of O2. Similarly, guys, understand. Hydrogen here is in atomic form. So instead of moles, I can write gram atoms of hydrogen. Gram atoms of hydrogen. Here hydrogen is in molecular form. Instead of mole, I can write gram molecule of hydrogen. Gram molecule of hydrogen. Here oxygen is in atomic form. So I can write 4 gram atoms of oxygen. 4 gram atoms of oxygen. And here oxygen is in molecular form. I can write 2 gram molecules of oxygen. Are all these statements clear? Let me know once in the chats. Quick. Quick, people. Everybody. Everybody, quick. Perfect. Now, people, let's try to understand few questions. Let's try to see few questions. One of the simple question, very simple question, guys. Very simple question. Calculate the moles of O. Do you see the question? Calculate the moles of O. Calculate the moles of O. Or, since oxygen, you're taking an atomic form. So they might ask you to calculate the gram atoms of O. So the question can be, calculate the moles of O. Or they might ask you to calculate the gram atoms of oxygen in 196 grams of H2SO4. In 196 grams of H2SO4, how many moles of O are there? That is the question. That is the question, right? How many moles of O? First thing, my dear students, first thing always, convert the given quantity into number of moles. What is my given quantity? I am given with mass of H2SO4. Do we know how to convert the mass into moles? So moles of H2SO4 is equal. Given mass of H2SO4 in grams divided by molar mass of H2SO4. The value comes out to be 2. So basically we have got 2 moles of H2SO4. And in those 2 moles of H2SO4, we have to check how many moles of O are there. How many moles of O are there, right? Now, my dear students, some things which I taught you a few minutes back only. Tell me one thing. In 1 mole H2SO4, what do you think? How many moles of O are there? In 1 mole H2SO4, there are 4 moles of O. There are 4 moles of O, right? In 1 mole H2SO4, there are 4 moles of O. Therefore, 2 moles of H2SO4 will contain 8 moles of O. Simple. I'll say 2 moles of H2SO4 will contain O2s are 8 moles of O. I think this is something which I was supposed to calculate. How many moles of O are present in 2 moles of H2SO4? 2 moles of H2SO4 means 196 grams of H2SO4, right? Perfect. So, my dear students, you got to know in 196 grams of H2SO4, in 2 moles of H2SO4, how many moles of O are there? There are 8 moles of O. Correct? Remember one more thing. Remember one more thing. Remember one more thing, guys. In the question, if you look carefully, calculate the moles of O in 196 grams of H2SO4. As per the question, this is the substance. As per the question, this is the substance whose data was given. And this is the substance whose data was to be calculated. This is the substance whose data was given, and this is the substance whose data was to be calculated. Remember, the one whose data is to be calculated. The one whose data is to be calculated. The one whose data is to be calculated. That always has to be on the right side of the statement. See, this is the statement I wrote. And on the right side of the statement, I wrote O. Perfect. That substance is to be written on the right side, whose data is to be calculated. I was supposed to calculate the data for O. That's why I wrote the statement in this format. That's why I did not write the statement in the reverse format. Did you understand? The one whose data is to be calculated, that always has to be on the right side of the statement. That always has to be on the right side of the statement. And I believe this is clear till here to everyone, right? The one whose data is to be calculated, that always has to be on the right side of the statement. Let's try to solve a few more questions so that you can understand and analyze it properly. This is one more PYQ. It was asked in JEE Mains. Proper, NEET oriented question. Understand carefully. Calculate the mass of H3PO4. Calculate the mass of H3PO4. This is the one whose data is to be calculated. Calculate the mass of H3PO4. That contains 0.25 moles of O. So in what mass of H3PO4 there will be 0.25 moles of O? See guys, as I told you, if you use the general information, if you talk about H3PO4, tell me in 1 mole H3PO4, how many moles of O do we have? In 1 mole H3PO4, there are 4 moles of O. Right? There are 4 moles of O. Now, should I write the statement like this or should I reverse it? That is the question. For that, I told you already, the one whose data is to be calculated, that has to be on the right side of the statement. The one whose data is to be calculated, that has to be on the right side of the statement. Whose data are we supposed to calculate? We are supposed to calculate the mass of H3PO4. So H3PO4 has to be on the right side. So that means I have to reverse the statement. That means I need to reverse the statement. And when I reverse the statement, I'll write it like this. I'll write 4 moles of O. 4 moles of O are present in 4 moles of O are present in 1 mole H3PO4. 4 moles of O are present in 1 mole H3PO4. Now guys, the question is done. If 4 moles of O are present in 1 mole H3PO4, use the unitary method. Therefore, 1 mole of O will be present in 1 by 4 moles of H3PO4. 1 mole of O will be present in these many moles of H3PO4, right? But look at the question. I'm not given with 1 mole of O. I'm given with 0.25 moles of O. So can I say 0.25 moles of O will be present in 1 by 4 multiplied by 0.25 moles of H3PO4? 1 by 4 into 0.25. This value comes out to be 1 by 16. So it is 1 by 16 moles of H3PO4. My dear students, look at what we have calculated. We got to know one thing. We got to know 0.25 moles of O. 0.25 moles of O are present in these many moles of H3PO4. 0.25 moles of O are present in these many moles of H3PO4. But as per the question, was I supposed to calculate moles of H3PO4 or mass of H3PO4? We were supposed to calculate the mass of H3PO4. Tell me, how do we convert moles into mass? How do we convert moles into mass? We have seen that. Moles multiplied by molar mass. That gives me mass, right? So I'll say mass of H3PO4. Mass of H3PO4 will be equal to moles of H3PO4, which is 1 by 16, multiplied by. When you calculate molar mass of H3PO4, that comes to be 98. And this value over here will be 6.125 grams. If you look carefully, what is this? Is it mass or moles? I would say this is the mass of H3PO4. This is the mass of H3PO4 that contains 0.25 moles of O. I would say these are the moles of H3PO4 that contains 0.25 moles of O. I hope you can solve these sort of questions easily from now onwards. Yes? So my dear students, can you solve this one? Can you solve this one? Only changes instead of O, I have mentioned O2. I believe you should be able to solve this one. I believe you can solve this one. I believe you can solve this one. Yes? Quick. Can you solve this one on your own? In the earlier question, I wrote statement in terms of O. Here you have to write the statement in terms of O2. That's it. Here you have to write the statement in terms of O2. That's all. So what do you do in this particular question? If you look carefully, calculate the mass of H3PO4. Calculate the mass of H3PO4 that contains 0.25 moles of O2. Right? 0.25 moles of O2. My dear students, think carefully. Write the first statement, which we always write, which is a general information. 1 mole H3PO4, 1 mole H3PO4 contains how many moles of O2? I'll say it contains 2 moles of O2. 1 mole H3PO4 contains 2 moles of O2. Should I write the statement in this format or I should reverse it? Depends on whose data I'm supposed to calculate. Calculate the mass of H3PO4. I'm supposed to get the data of H3PO4. That means I'll be reversing the statement. H3PO4 has to be on the right side. So I can clearly say 2 mole O2. 2 mole O2 are present in 1 mole H3PO4. Therefore, 1 mole O2 will be present in 1 by 2 moles of H3PO4. Okay? Therefore, 0.25 moles of O2, 0.25 moles of O2 should be present in 1 by 2 multiplied by 0.25. The value comes out to be 1 by 8 moles of H3PO4. What did I calculate here? I got the moles. Moles of what? These are the moles of H3PO4, which contains 0.25 moles of O2. But was I supposed to calculate moles of H3PO4? No. I want to calculate mass of H3PO4. Now tell me one thing. How do you convert moles into mass? You'll simply write mass of H3PO4 will be equal to moles of H3PO4 multiplied by molar mass of H3PO4. The value comes out to be 12.25 grams. Now tell me the meaning of this particular thing. What did we do? What did we calculate? What did we calculate, people? This is the mass of what? This is the mass of H3PO4. This is the mass of H3PO4 that contains 0.25 moles of O2. This is the mass of H3PO4 that contains 0.25 moles of O2. These are the moles of H3PO4 that contains 0.25 moles of O2. I believe it's clear. I believe it's clear, people. I believe it's clear. Look at this one. See how easy you'll feel this question is now. This is again the PYQ, by the way. It's again the PYQ. Calculate the number of moles of O. Moles of O we have to calculate. Moles of O. Present in 3.2 grams of something something. Whose molar mass is given. Moles of O present in these many grams of this particular substance. Right? So my first thing always is to convert the given quantity into moles. Given quantity is mass right now. Convert it into moles first. So number of moles of the substance is equal to given mass of substance in grams divided by molar mass of the substance, which is given to me as 178. So these many moles of substance we have. Convert the given quantity into moles first, right? Now, my dear students, let's use the general information. 1 mole Na2SO4 dot 2 times water contains how many moles of O? 4. 4 plus 2 is 6. So 6 moles of O. 6 moles of O, right? 1 mole of this substance contains 6 moles of O. If 1 mole of the substance contains 6 moles of O, 2 moles will contain multiplied by 2, 3 moles multiplied by 3, 4 moles multiplied by 4. How many moles we have? 3.2 divided by 178 moles of this substance will contain 6 multiplied by 3.2 divided by 178 moles of O. Right? This is something which I was supposed to calculate. Done. These are the moles of O which are present in these many moles of substance. Right? Or I'll say these are the moles of O which are present in 3.2 grams of the substance. Perfect. So give me some green signal. Tell me if similar sort of question is asked in the question. I mean, if similar sort of question is asked in your examination, will you be able to solve it? Yeah? Quickly, people. Quickly, quickly, quickly. Quickly, guys. All clear? Let me know in the chats with some fire emojis if all the stuff is clear till now. Let me know in the chats if all the stuff is clear. Quickly, everybody. Everybody in the chats. Perfect. So till now, a lot of concepts we have discussed, and I believe if any question is asked from these sort of concepts, you should be in a position to solve all of them. My dear students, look at one more question. This is again one question which was asked, few years before in your JEE mains examination, and it's a proper NEET standard question. Proper NEET standard question. Look at the question carefully and see what are we supposed to calculate. Look carefully. The question is, calculate the. Again, we have to calculate the moles of O present in 126 AMU of HNO3. 126 AMU of HNO3. First of all, think logically. If, look at this given substance, what is the given substance? We are given with the mass of HNO3. We are given with the mass of HNO3. But is this mass in grams? This mass is not in grams. This mass is in AMU. And I hope you remember the approach when mass is given in AMU. I hope you remember the approach. Yeah? Right? I hope you remember the approach. That's something which I've taught you already. Tell me one thing. 126 AMU of HNO3 means 2 molecules of HNO3. Means 2 molecules of HNO3. 2 molecules of HNO3 means how many moles of HNO3? Given number of particles divided by Avogadro's number. So 2 by Na moles of HNO3. Correct? 2 by Na moles of HNO3. Perfect? 2 by Na moles of HNO3. So technically, if you look at the question, we are supposed to calculate the moles of O. We are supposed to calculate the moles of O, which are present in 2 by Na moles of HNO3. Now, use the general information. Use the general information. We know 1 mole HNO3 contains 3 moles of O. We know 1 mole HNO3 contains 3 moles of O. Now, am I given with 1 mole HNO3? No, I'm given with 2 by Na moles of HNO3. So tell me about 2 by Na moles of HNO3. So I'll say 2 by Na moles of HNO3 will be containing 3 multiplied by 2 by Na. That comes out to be 6 by Na moles of O. So my dear students, look at it properly. What did we calculate? What did we calculate? These are the moles of O. These are the moles of O which are present in 2 by Na moles of HNO3. These are the moles of O which are present in 2 molecules of HNO3. These are the moles of O which are present in 126 AMU of HNO3. That's something which I was supposed to calculate. Am I clear? Am I clear, people? Quickly. Quickly, people. Sir, how backlog of whole 11th wasted? What do I do? Follow this series. Simple. Follow this series. More than sufficient for you. Yes, there is no need to spam the chats. Please. Please, bro. Yeah? So my dear students, I believe till here every single thing is clear. Now I'm moving on to one more amazing topic, one more interesting topic, which you do not find on YouTube mostly, right? Your NEET teachers, they don't teach you this stuff, but I feel this is super important, particularly when it comes to equilibrium. In equilibrium, these particular concepts, which I'm going to teach you now, right? They'll be used in equilibrium in majority of the times. Perfect. But before starting this particular topic, tell me once in the chats. Tell me once in the chats. Whatever things I've discussed till now. Are all the things clear? Are all the things clear, people? I would want the honest answers from. Yeah? Quickly, quickly, quickly. Quickly, people. Perfecto. Let's kill this topic as well. Okay? Hey guys, what exactly this particular topic is all about? The topic name is average molar mass of the gaseous mixture. Average molar mass of the gaseous mixture. Okay? Average molar mass of the gaseous mixture. Let me write its definition first of all. Then I'll make you understand how do we get the formulas over here and how do we use those formulas in the questions. All those things I'll be letting you know now. First of all, average molar mass of the gaseous mixture. How do we define it? It is defined as the mass of one mole of a gaseous mixture. It is defined as the mass of one mole of a gaseous mixture. Point number one. Point number two. It is expressed again in grams per mole. Now let's try to analyze this particular topic in detail. Let's try to analyze this particular topic in detail. Hey guys, there is no need to talk in between. Stop spamming and stuff. I have got the option to block you as well. You will never be able to see the lectures. Nonsense. If you have come to study, then be here. If you want to talk or chit chat, there are a lot of channels wherein every time chit chatting is going on. Go there, right? Do whatever stuff you want to do there, but not here. Here people come to study, right? We don't do nonsense stuff on this particular channel. This is content-based channel. This is not your... Okay, I hope you get it. Go to some other channel and do all this chit-chatting, you know, sharing the numbers, getting the Insta IDs, etc., etc. Yeah? I hope I'm clear. All right. See, guys, what this particular topic exactly is all about. Try to understand now. Try to understand. Imagine that I've got a container over here. Imagine that I've got a container which is closed on all the sides. My dear students, imagine in this particular container, you have got some chemically non-reacting gases. Imagine that there are some chemically non-reacting gases present in the container. For example, in this particular container, we have got N2 gas and O3 gas. Let's say these are the two gases which are there in the container. For example, let's say we have got 2 moles of N2 as well as 2 moles of ozone in the container. Assume that. We have got 2 moles of N2 and 2 moles of O3 in the container. So in total, in this mixture, since we have got a gaseous mixture, this gaseous mixture contains 2 gases. So if I ask you, how many total moles are there in the mixture? You'll say 2 plus 2, 4. So there are total 4 moles in the gaseous mixture. Number 1. Number 2. If I ask you, what is the molar mass of N2? Molar mass of N2 is 28 grams. Molar mass of N2 is 28 grams. Molar mass of N2 is 28 grams. That means mass of 1 mole of N2 is 28 grams. That means mass of 1 mole of N2 is 28 grams. But am I given with 1 mole of N2 or 2 moles? I'm given with 2 moles of N2. If the mass of 1 mole of N2 is 28 grams, therefore the mass of 2 moles of N2 will be 28 into 2, that is 56 grams. So I can say in this container, there are 56 grams of N2 present. Yeah? Now people, what is the molar mass of O3? Molar mass of O3 is 48 grams. That means mass of 1 mole of O3 is 48 grams. Am I given with 1 mole of O3 or 2 moles? 2 moles of O3. If the mass of 1 mole of O3 is 48 grams, therefore mass of 2 moles of O3 will be 48 into 2, that means 96 grams. So in this container, you can say we have got 56 grams of N2 and 96 grams of O3 present. Okay? So if I ask you, what is the mass of the complete gaseous mixture? Mass of the mixture will be 56 plus 96. That will come out to be 152 grams. That will come out to be 152 grams. How many total moles are there in the mixture? 4. What is the total mass of the mixture? 152 grams. So my dear students, I can write a statement over here. I can say 4 mole gaseous mixture. 4 mole gaseous mixture. 4 mole gaseous mixture has got the mass of 152 grams. Now think logically. If 4 moles of gaseous mixture have got the mass of 152 grams, what do you think will be the mass of 1 mole of gaseous mixture? Mass of 1 mole of gaseous mixture will be 152 divided by 4 grams. It will be 152 divided by 4 grams. If you think logically, what did we calculate? What is this particular term? This is the mass of 1 mole of a gaseous mixture. And as per the definition, mass of 1 mole of a gaseous mixture is what you call as average molar mass, which is represented with MAV. I hope you got to know what is average molar mass. Average molar mass of the mixture, average molar mass of the gaseous mixture is basically the mass of 1 mole of a gaseous mixture. Okay? Perfect. Right, people? Now, think logically. If you want to make a result to calculate M average, you can do that as well. You can do that as well. Make a direct result. See, what is this 152? 152 was basically the mass of the mixture. What is this 4? 4 were basically total moles present in the mixture. So if I want to make the formula, in the numerator, I'll be writing the mass of the gaseous mixture in grams divided by. This 4 was total moles present in the mixture. So this becomes my direct result. This is my direct formula with the help of which you can calculate average molar mass of the gaseous mixture. Right? Mass of the mixture in grams divided by total moles present in the mixture. That's always going to give you the average molar mass of the mixture. That's always going to give you the mass of 1 mole of the gaseous mixture. Did you understand this? Did you understand this, how this formula comes? So first of all, how do we define average molar mass of the mixture? Average molar mass of the gaseous mixture is basically the mass of 1 mole of a gaseous mixture. Right? How do we calculate it? Simple formula. Total mass of the mixture in grams divided by total moles present in the mixture. That's all. Okay? Now, let's try to derive its more results, right? So that all the different types of questions you can easily solve. See guys, let me derive certain results for M average. Some important results. See people, imagine that this is your container, and for example, this container contains 2 chemically non-reacting gases, gas 1 and gas 2. These are your 2 chemically non-reacting gases present in the container, gas 1 and gas 2. Okay, gas 1 and gas 2. Now, for example, in this container, for example, the mass of gas 1 in the container is, for example, W1 grams. Mass of gas 2 in the container is, for example, W2 grams. W1, W2 represents mass of gas 1 and gas 2 in the container, right? Second, for example, in this container, we have got N1 moles of gas 1 and N2 moles of gas 2. Let's say in the container, there are N1 moles of gas 1, N2 moles of gas 2. For example, let's say the molar mass of gas 1 is, for example, M1, molar mass of gas 2 is M2. Let's say volume of gas 1 in the container is V1, volume of gas 2 in the container is V2. Let's say mole fraction of gas 1 in the container is represented by Chi1, mole fraction of gas 2 is represented by Chi2. These are few things which I'm assuming over here, right? Few things which I'm assuming over here. Now guys, since we have got a gaseous mixture, if I ask you to calculate the average molar mass of the gaseous mixture, what is meant by average molar mass of gaseous mixture? It means that I'm asking you to calculate the mass of 1 mole of a gaseous mixture. How do we do it? I made a result few minutes back, if you remember. That was mass of the gaseous mixture in grams divided by total moles present in the mixture. Perfect? Perfect. Now guys, tell me one thing. What is the mass of the gaseous mixture? Mass of the mixture will be W1 plus W2. Mass of the mixture will be simply W1 plus W2 divided by total moles in the mixture will be simply N1 plus N2. N1 plus N2. These are the total moles in the mixture. Okay. So this becomes my first result with the help of which we can calculate average molar mass of the mixture. Number one. Number two, guys. MAV is equal to W1. See guys, if I write N here, what N represents? Number of moles. Number of moles of the substance is equal to given mass by molar mass. If I write N1, this has to be W1, this has to be M1. Therefore, W1 will be equal to M1N1. W1 has to be equal to M1N1. Similarly, W2 has to be equal to M2N2. W2 has to be equal to M2N2. So instead of W1, I'll be writing M1N1. Instead of W2, I'll be writing M2N2. Divided by what? Divided by N1 plus N2. This becomes my one more result with the help of which we can calculate average molar mass of the gaseous mixture. Average molar mass of the gaseous mixture, right? Similarly, guys, See, in this container right now, how many moles of gas 1 are there? N1. How many moles of gas 2 are there? N2. If I write like this, N1 divided by N1 plus N2. Number of moles of gas 1 divided by total moles present in the mixture. Should I be calling this as mole fraction of gas 1? Yes. Similarly, mole fraction of gas 2 has to be equal to N2 divided by N1 plus N2. Now, my dear students, think logically. See, this N1 plus N2, it is the denominator of this term as well as this term, right? So, I can say MAV is equal to M1, M1, M1. Or let me write it like this. First of all, I'll write M1, N1 divided by N1 plus N2 plus M2, N2 divided by N1 plus N2. Now tell me just one thing. N1 divided by N1 plus N2. I'll be calling it as mole fraction of gas 1 plus this plus M2 as such. N2 divided by N1 plus N2. It is mole fraction of gas 2. So this is my one more result. This is one more result to calculate average molar mass of the mixture. M1 mole fraction of gas 1 plus M2 multiplied by mole fraction of gas 2. And what is this M1, M2? What is this M1, M2? M1, M2 means molar masses of the individual gases. As simple as that. Yeah? Molar masses of the individual gases. Correct, people? Is it clear? Is it clear? Is it clear? Now, one more result. One more result over here. My dear students, remember one thing. Sometimes in order to confuse you, they might give the data for mole percentage, right? They might give mole percentage. What is mole percentage? It's nothing. Mole fraction multiplied by 100 gives me mole percentage. Mole fraction multiplied by 100 gives me mole percentage. So mole fraction of 1 multiplied by 100, that gives me mole percentage of 1. Similarly, mole fraction of 2 multiplied by 100, that gives me mole percentage of 2. So this particular result, I can convert in terms of mole percentage as well. I can write M1 instead of mole fraction of 1, I can write mole percentage of 1 divided by 100 plus M2 instead of mole fraction of 2, I'll be writing mole percentage of 2 divided by what? Divided by 100. This is one more result to calculate average molar mass of the mixture. Okay? Instead of mole fraction, what did we write? Mole percentage divided by 100. Mole percentage of 1 divided by 100, mole percentage of 2 divided by 100. That's all. Okay? This is one more result with the help of which we can calculate the average molar mass of the mixture. Now there is one result left. What is that? Let me write that particular result. See guys, I'm erasing this particular part. This was just for the calculation purpose, right? See, my dear students, remember one thing. If the gaseous mixture is present at constant pressure and temperature, if the gaseous mixture is present at constant pressure and temperature, what does that mean? The mixture which we have, if its pressure and temperature was constant, if its pressure and temperature was not changing, if its pressure and temperature was not changing, if it was given as constant at that point of time, how do we calculate M average? M average is calculated by the formula M1 instead of N1, you'll be writing V1 plus M2 multiplied by V2 divided by V1 plus V2. This is the formula which is not used everywhere. This is the formula when the gaseous mixture will be present at constant pressure and temperature, right? Perfect. Just instead of moles, I replaced moles with volume. Why is that? You know ideal gas equation, PV is equal to nRT. Pressure, temperature, constant. R already constant. Volume is directly proportional to moles. So wherever you see moles, you can replace moles with volume. That's why I replaced N1 with V1, N2 with V2, right? And I got this particular result. So these are different formulas which we have to remember to calculate the average molar mass of the gaseous mixture. I believe I'm clear with it till here. Now, all these results which we got till now, right? There will be different types of questions asked from all these results. Let's try to understand, right? What kind of questions can be asked. First of all, I'm starting with a basic, with a simple question. This is something which you should kill. Calculate the average molar mass of the gaseous mixture containing. Calculate the average molar mass of the gaseous mixture containing So gaseous mixture is containing 4.4 grams of gas A, 4.4 grams of gas A, and 6.4 grams of gas B, and 4.8 grams of gas C, and 4.8 grams of gas C, right? Molar masses of A, B as well as C is given. Molar mass of A, B as well as C is given. What do we have to calculate? Average molar mass of the mixture. What do we have to calculate? Average molar mass of the mixture. My dear students, average molar mass of the gaseous mixture as per the first formula itself is equal to W1 plus W2 plus W3 divided by N1 plus N2 plus N3. What is W1? 4.4 grams. W2, 6.4. W3, 4.8 divided by. What is N1? N1 means number of moles of gas 1, which is mass of gas 1 divided by molar mass of gas 1. What is the mass of gas 1? 4.4 divided by. What is the molar mass of gas 1? Molar mass of gas 1 is 44. The value is 0.1. Right? Similarly, N2, number of moles of gas 2 is equal to mass of gas 2 divided by molar mass of gas 2. What is the mass of gas 2? 6.4. What is the molar mass of gas 2? Molar mass of gas 2 is 64. The value is again 0.1. Similarly, N3, number of moles of gas 3 is equal to mass of gas 3 divided by molar mass of gas 3. What is the mass of gas 3? 4.8 grams divided by molar mass of gas 3 is 48. The value comes out to be 0.1. So N1, N2, N3 we calculated. All are 0.1. 0.1 plus 0.1 plus 0.1. After solving, what is the value which you get? People are saying it's coming out to be 52 grams, right? So it will be 52 grams per mole. 52 grams per mole. So this is the average molar mass of the mixture. What does it mean? It means 1 mole gaseous mixture. 1 mole gaseous mixture has got the mass of how much? 1 mole gaseous mixture has got the mass of 52 grams. Right? 1 mole gaseous mixture has got the mass of 52 grams. I believe it's clear to everyone. Right, people? All clear till here? This was the first question. Have a look on the second type of the question. Have a look on the second type of the question. This type of the question, right, you should be able to solve as well. Understand, guys. At 27 degrees centigrade and 1 atm, what can you understand from these two things? At 27 degrees centigrade and 1 atm. What can you understand from these two things? That means pressure temperature is constant. So pressure temperature constant means we have got only one formula to calculate average molar mass of the mixture when pressure temperature is constant. Which formula is that? Moles, volume, which one? That is the volume wali formula. Right? Yes? Right, people? Exactly. See, as per the question is concerned, let's try to understand. At 27 degrees centigrade and 1 atm pressure, a given mixture of O2 and SO2. We have got O2 gas and SO2 gas present in the container, right? Contains gases in 2:1 volume ratio. The gases are given in 2:1 volume ratio. Calculate the number of moles present in 20 grams of the mixture. Calculate the number of moles present in 20 grams of the mixture. 20 grams of the mixture. So basically, as per the question, the mass of mixture is given to us. How much is the mass of mixture? 20 grams. Right? The mass of the gaseous mixture is 20 grams. What are we supposed to calculate? Total moles present in 20 grams of the mixture. Total moles present in 20 grams of the mixture. Moles we have to calculate. Mass is given. Moles we have to calculate. Now, my dear students, think logically. Right? Total moles present in the mixture will be equal to mass of the mixture divided by molar mass of the mixture. And molar mass of the mixture is what you call as M average. Molar mass of the mixture is what you call as M average. Average molar mass, right? So, what is the mass of the mixture? Mass of the mixture is 20 grams. Now, what do I need to calculate? I need to calculate average molar mass of the mixture, right? So, let's try to calculate average molar mass of the gaseous mixture first. What do we calculate? What do we need to calculate? We need to calculate average molar mass of the gaseous mixture first. Since the mixture is present at constant pressure and temperature. If I ask you what is the molar mass of O2 here, 32 grams per mole. What is the molar mass of SO2 here? 64 grams per mole, right? Volume ratio is how much? 2:1. If the volume ratio of the gases is 2:1, let's assume volume of SO2 is X. Therefore, volume of O2 has to be 2X. Perfect. Let me call this as V1. Let me call this as V2. Volume ratio is given. Therefore, volume of SO2, if this is X, this has to be 2X, right? I think we are done. M average is equal to M1 V1 plus what? Plus M2 V2 divided by V1 plus V2. Now, what is M1? 32. What is V1? 2X. 32 multiplied by 2X is nothing but 64X plus M2 V2. M2 V2. 64 into X means 64X divided by V1 plus V2. V1 plus V2. 2X plus X makes it 3X. The value comes out to be 128 divided by 3 and it's going to be grams per mole. So this is basically your average molar mass of the mixture. And this average molar mass of mixture is required here. So it is 20 divided by 128 by 3. The value comes out to be 60 upon 128. So these are the total moles. These are basically the total moles which are present in 20 grams of the gaseous mixture. Is it clear? Is it clear, people? Let me know once. Let me know once in the chats. Is this question clear? Or see, you could have solved this question without using the formula as well. What is the average molar mass of the mixture you got? 128 by 3 grams, right? This is the average molar mass. Now understand carefully. See, you got the average molar mass of the mixture as 128 divided by 3 grams. What does it mean? What does it mean? It means that 128 by 3, which means 42.6. Which means 42.6. So 42.6 grams is basically the mass of 1 mole mixture. 42.6 grams is basically the mass of 1 mole mixture. Therefore, 1 gram means 1 upon 46 moles of the mixture. Am I given with 1 gram of the mixture? No, I'm given with 20 grams of the mixture. That means 20 grams of the mixture means how many moles? 1 upon 42.6 multiplied by 20 moles of the mixture. Right? So this would have given you, these are the total moles which are basically in 20 grams of the mixture. This was one more way of solving. This was one more way of solving question. Right? Now the choice is all yours. I got the average molar mass. So 42.6 grams is basically the mass of 1 mole mixture. So 1 gram mixture means these many moles of mixture. 20 grams mixture means these many moles of mixture. Right? Anything. Whatever you feel feasible, you can either use the formula or you can do the question in a different way. Right? The choice is completely yours. All right. Can you try to solve this question? It's again a simpler one. It's again a simpler one. A gaseous mixture contains 60 mole percentage of carbon dioxide and 40 mole percentage of O2. Calculate the average molar mass of the mixture. Guys, this is also something very simple, which I believe you should be doing on your own. So we are given with carbon dioxide and O2, right? First of all, what is the molar mass of carbon dioxide? 44 grams per mole. What is the molar mass of O2? 32 grams per mole, right? And as per the question, we are given with the mole percentage of these gases. Mole percentage. Mole percentage of carbon dioxide is 60. Therefore, it has to be 40. Because sum of mole percentage is always 100, right? Now, people, understand. What do I need to calculate? Average molar mass of the gaseous mixture. Now, first of all, average molar mass of the gaseous mixture. Since the data for mole percentage is given, so use the formula in terms of mole percentage. So M1 multiplied by mole percentage of 1 divided by 100 plus M2 multiplied by mole percentage of 2 divided by 100. The question is done and dusted. What is M1? M1 is 44. Mole percentage of 1, 60. 60 by 100 is 0.6. It is 0.6 plus. What is M2? 32. Mole percentage of 2, 40. 40 divided by 100, 0.4. Solve it. Get the value, which will come out to be 39.2 and it's going to be grams per mole. That means the mass of 1 mole of the gaseous mixture is 39.2 grams. Correct? Simple? Simple, guys? Yeah? Done and dusted? I believe this is also clear to everyone. I believe this is also clear to everyone. Look at this question. Look at this question properly. Look at this question properly, guys. 600 ml mixture of O2 and O3 at STP weighs 1 gram. Calculate the volume of ozone in the mixture. Okay, calculate the volume of ozone in the mixture. Let's try to solve this as well. Let's see what the question says, first of all. See, guys, there are two approaches which I'm going to give you in this question. There are two approaches which I'm going to give you in this particular question. Okay, two approaches. See, guys, imagine this is the container which we have. And in this particular container, we have got two gases. One is your O2 gas and one is your O3 gas. These are the two gases which are there in the container. So this gaseous mixture, as per the question, it is present at STP. It is present at STP. What is the volume of this whole mixture? Volume of this entire mixture is 600 ml. 600 ml is the volume of the entire mixture. 600 ml is the volume of the entire mixture, right? It is the volume of entire mixture. 600 ml. What is the mass of the entire mixture? The mass of the entire gaseous mixture is 1 gram. The mass of the entire mixture is 1 gram. Okay? Mass of the entire mixture is 1 gram. As per the question, the mixture is present at STP. Mixture is present at STP. What do we need to calculate? Volume of ozone in the mixture. Volume of ozone in the mixture. My dear students, first of all, the volume of entire mixture is 600 ml, right? Let's assume out of 600 ml. Let's assume out of 600 ml. Volume of ozone in the mixture is, for example, x ml. Therefore, volume of O2 in the mixture will be 600 minus x ml. Okay, 600 minus x ml. Perfect. Now, if I ask you what is the molar mass of O2? Molar mass of O2 is 32 grams per mole. Molar mass of O3 is nothing but 48 grams per mole. Correct? Now, first thing which I'll be doing over here, understand properly. If I ask you how many total moles are there in the mixture, how many total moles are there in the mixture? See, volume of the mixture is 600 ml. Volume of the mixture is 600 ml divided by, since condition is STP, so divided by 22.4 liters. That will be 22400 ml, which comes out to be 6 upon 224. So these are basically the total moles which are there in the mixture. These are basically the total moles which are there in the mixture, right? These are the total moles which are there in the mixture. These are the total moles which are there in the mixture. Okay. Now, my dear students, is there any other way to calculate total moles in the mixture? Is there any other way? See, I'm given with the mass of the mixture. I'm given with the mass of mixture. I'll say total moles in the mixture will be mass of mixture in grams divided by molar mass of mixture, which is your average molar mass. So this is 1 divided by m average. 1 by m average. This is one more way of calculating the total moles in the mixture. See, this particular term is giving you the total moles in the mixture. This particular term is also giving you the total moles in the mixture. So I can directly equate them. I can say 1 upon m average has to be equal to 6 upon 224. So from here, m average is equal to 224 divided by 6 grams. This is the m average which I got. I got the average molar mass. But, am I supposed to calculate average molar mass? No. I'm supposed to calculate volume of ozone in the mixture. But if you think logically, instead of m average, since condition is STP, STP means pressure temperature constant. If pressure temperature is constant, instead of m average, I can write M1V1 plus M2V2 divided by V1 plus V2. And as per the equation, it is equal to what? 2 to 4 divided by 6. Now, what is M1? 32. What is V1? V1 is 600 minus 6. Plus, what is M2? M2 is 48. What is V2? V2 is X divided by V1 plus V2. V1 plus V2 will come out to be 600 only, right? And as per the question, this is equal to 2 to 4 divided by 6. Now, it is just the matter of calculation. Cross multiple and get the value of X. And what is this X? X is basically the volume of ozone in the mixture, which I believe is something I'm supposed to calculate. Calculate the volume of ozone in the mixture, right? Am I clear, people? Am I clear? Am I clear? All clear? Can you give me this? Can you suggest me some names which I need to block? Because people are spamming. Who is this? My name is Marvel. My name is Marvel. Sorry, bro. Just a second. Marvel is over. Who's the next one? Give me the names. Give me the names. Marvel is gone from the channel. Who's the next one? Is there any other person who is disturbing you? Quick, quick, quick. Marvel has gone to DC. Yeah, he'll be never able to write anything. If he comes with a different account, that account will also get blocked. Any other? Any other Marvel is there? Any other Tony Stark? I mean, you know, or yeah, right. Keep on informing me. How do you calculate so fast? You know, every year, like online plus offline combined, I teach one particular chapter minimum 30 times, right? 30 times. So I remember their answers as well. See, here you'll be getting 200, 400 as the answer. So with practice, your calculation becomes faster. And there'll be a time when you'll remember the, values also. When you'll remember the values also. Okay? Perfect, perfect. Should we move on? Should we move on? Or do you want to see one more approach of this question? Do you want to see? Do you want to see one more approach of this question? See, in one line, understand. What is the volume of O2 in the container? 600 minus 6. See, 600 minus 6. This is the volume of, or let's write one thing. Let's do one thing. Can I say mass of O2 plus mass of O3? It has to be equal to 1 gram. It has to be equal to 1 gram as per the given scenarios, right? Mass of O2. See guys, volume of O2 is how much? 600 minus x ml. This is the volume of O2. Condition is STP. If I divide volume with 22400, what do I get? These are moles of O2 in the container. These are moles of O2 in the container. Moles of O2 multiplied by molar mass of O2. This is the mass of O2. This particular term is going to give you the mass of O2 in the container, right? Plus mass of O3. What is the volume of O3? X divided by 22400. This is going to give you moles of O3. Now moles multiplied by molar mass of O3. Molar mass of O3 is 48. So this particular term now gives you the mass of O3. It now gives you the mass of O3, right? So mass of O2 plus mass of O3 has to be equal to 1. So you made one equation here, right? Just solve this equation, get the value of X. Done and dusted, right? Solve this equation, get the value of X. I hope you got to know what I did. I hope you got to know what I did. So listen, let's take one more break because I need to have my dinner, right? You guys are done with your dinner? If I do not have my dinner now, okay, my family members, they are going to sleep and I'll have to remain hungry throughout the night. Okay, so I'll be back. Be back at 10:35, okay? But everyone, because now we are going to start something amazing. Be back at 10:35. Till then you can revise the things. But I would want every one of you to be back. And the ones who did not, who could not, who did not have dinner yet, you guys can also have. Be back exactly at 10:35. I would want every one of you to be here at 10:35. Okay? See you. See you in some time. See you in some time. Are you guys back? Yes. Are you all back? All right. So the ones who were not done with the dinner yet, are you guys done? Are you guys done? Are you guys done? Yeah? There is no special dinner or something. It is just I had some rice with chicken. That's all. That's all. Did we start now? Yes. Okay, tell me if all the things are clear till here. Tell me quickly in the chats whether all the stuff, whatever we have discussed till now, is every single thing clear? I would want to know the honest answers. If all the things, whatever topics, whatever questions we have discussed till now, if every single thing is absolutely clear. Class duration. I have no idea about class duration. Till we complete this chapter, I'm here. And you guys are supposed to be there too. Yeah? See, your competition is decreasing hour by hour. Do you see? Your competition is decreasing hour by hour. Just think in that perspective. And the kind of satisfaction which you will get once you are done with the chapter, that will be something amazing. Perfect then. So let's get started with something which is one of the most important topics of the chapter. You know it, stoichiometry, right? So my dear students, what kind of information the stoichiometry gives us? What the stoichiometry exactly is all about? What kind of questions are asked from it? Let's try to understand each and everything one by one. See guys, in order to understand the stoichiometry in detail, I'll be taking a general reaction. Like, for example, I'm taking a reaction N2 gas plus H2 gas. It gives NH3 gas. N2 gas plus H2 gas. It gives NH3 gas. This is one general reaction that I've taken. If I ask you whether the reaction is balanced or not, what is it? It is not a balanced chemical equation. So my dear students, first of all, remember whenever we'll be using stoichiometry in reactions, the first thing always is to be balancing the reaction. The first thing which you'll be doing always is to balance the reaction. If I balance this particular reaction, it will be 3 times, this will be 2 times, and this is going to be 1. Now, after balancing the reaction, this 1, 3, and 2, this 1, 3, and 2, I will be calling them as the stoichiometric coefficients. I'll be calling them as the stoichiometric coefficients. And my dear students, let me tell you, these stoichiometric coefficients, they are treated as moles. The stoichiometric coefficients which we have over here, they are treated as moles. Now, understand what kind of information these stoichiometric coefficients are going to give us. Understand what kind of information. What kind of information these stoichiometric coefficients are going to give us about a reaction. See guys, as I told you, we are going to treat the stoichiometric coefficients as moles. So I can say from the stoichiometric coefficients of reactants and products, I can say 1 mole N2 completely reacts with 3 moles of H2 and produces 2 moles of NH3. This is the first information in the form of a statement which stoichiometric coefficients gave us. Stoichiometric coefficients are telling us exactly in this particular reaction, 1 mole of N2 is completely going to react with 3 moles of H2 and are going to produce 2 moles of NH3 at the end. Now, my dear students, you can think logically. If 1 mole N2 completely reacts with 3 moles of H2, imagine we have got 2 moles of N2. 1 mole N2 reacts with 3 moles H2. Can I say 2 moles of N2 reacts with 6 moles of H2 and will be producing 2 2s are 4 moles of NH3? As simple as that. 3 moles of N2 will be reacting with 9 moles of H2 and will be producing 6 moles of NH3. 10 moles of N2 will be reacting with 30 moles of H2, will be producing 20 moles of NH3. So all this information stoichiometry gives us. All this information stoichiometric coefficients are going to give us, right? This is the first type of information which we got in terms of moles. The first kind of information which we got in terms of moles. Now, the second type of information. First information is in terms of what? First information is in terms of moles. Second information will be in terms of mass. Understand. If I ask you what is the molar mass of N2, you will say 28 grams. 28 grams. That is the molar mass of N2. Molar mass of N2 means mass of 1 mole of N2. So mass of 1 mole of N2 is basically 28 grams. How many moles of N2 we have? We have got only 1 mole of N2. So instead of this 1 mole of N2, can't we write 28 grams of N2? Yes, we can do that. Instead of 1 mole of N2, we can write 28 grams of N2. Now, my dear students, tell me one more thing. What is the molar mass of H2? Molar mass of H2 will be 2 grams. That means mass of 1 mole of H2 will be 2 grams. But do we have 1 mole of H2? No, we have 3 moles of H2. If mass of 1 mole of H2 is 2 grams, therefore mass of 3 moles of H2 will be 3 2s are 6 grams. So instead of 3 moles of H2, I am writing 6 grams of H2, right? Similarly, what is the molar mass of NH3? Molar mass of NH3 will be 17 grams. That means mass of 1 mole of NH3 is 17 grams. That means mass of 1 mole of NH3 is 17 grams. But my dear students, do we have 1 mole of NH3? No, we have 2 moles of NH3. If mass of 1 mole of NH3 is 17 grams, therefore mass of 2 moles of NH3 will be 17 into 2, 34 grams. Look at the statement carefully. I can say 28 grams of N2 completely reacts with 6 grams of H2 and produces 34 grams of NH3. This is again one more information which we got about the reaction, and this information is in terms of mass. Right? Correct? Now, my dear students, we can treat these stoichiometric coefficients directly as volume as well, right? I can say 1 volume N2 completely reacts with 3 volume H2 and produces 2 volume NH3. Now, what is this volume? This volume you can take in liters, for example. I can say 1 liter N2 completely reacts with 3 liters of H2 and produces 2 liters of NH3. Or you can write the same statement in terms of ml, for example. Let me write the statement like this. 1 ml N2 completely reacts with 3 ml H2 and produces 2 ml NH3. The choice is all yours. So look at the last 3 statements. The last 3 statements I wrote directly in terms of volume, right? So the last 3 statements are basically giving me the information about the volume of reactants products. Perfect. The last three statements are giving me the information about the volume of reactants products. So I hope you understood what kind of information these stoichiometric coefficients are going to give us. They are going to give us the information about the moles, about the mass, about the volume, etc., etc. Right? Now, how do we use these stoichiometry in the questions? Before that, there are some important reactions which I would want you guys to remember. Now, what those important reactions are, let me write certain reactions one on one so that you will remember those reactions from now onwards. Okay? Some important reactions which I would want every one of you to remember from now onwards. My dear students, first reaction. Let's say we have got KClO3. KClO3. KClO3 upon heating produces KCl, and with KCl you get O2 gas. This is the first reaction which I would want you guys to remember. KClO3 upon heating produces KCl and O2. First reaction. Second, calcium carbonate solid, right? Upon heating, it decomposes, it breaks down into calcium oxide plus carbon dioxide gas. This is the second reaction, which I would want you guys to remember. Okay? The third reaction. My dear students, imagine you have got a hydrocarbon containing carbon and hydrogen, CXHY. When you do its combustion, it always leads to the formation of carbon dioxide and water. It always leads to the formation of carbon dioxide and water. And there is one way by means of which you can balance this reaction as well. How? See, you have got X carbon atoms here, so make it X. How many hydrogen atoms? Y. So make it as Y by 2. What will be the stoichiometric coefficients of O2? It will be X plus Y by 4. This is something which you are going to remember directly. Right? This is how we are going to balance this sort of a reaction. Let me give you an example as well. For example, you are taking methane, CH4, right? This is basically C1H4, perfect, plus O2. It is going to give us carbon dioxide and water. How you are going to balance it? You are not going to use hit and trial here. See, what is the value of X? X value is 1. So this 1 is going to be the coefficient here. What is the value of Y? 4. So 4 by 2 comes out to be 2 here. Stoichiometric coefficient of O2 will be X plus Y by 4. So 1 plus 4 by 4. 1 plus 4 by 4 comes out to be 2. Right? Perfect. This is how we are going to balance this sort of a reaction. I hope this is clear. Yes? Right, people? Similarly, let's say you have got an organic compound like this, CXHYOZ. You have got an organic compound like this. For example, you are doing its combustion. You are making it to react with O2. So first of all, it's going to lead to the formation of carbon dioxide. And with carbon dioxide, you'll be getting water. Now, again, here we have got a method by means of which you are going to balance this sort of a reaction as well. How exactly? See, we have got X carbon atoms here. So make it X times. How many hydrogen atoms? Y. So make this as Y by 2. What will be the stoichiometric coefficient of O2? It's going to be X plus Y by 4 minus Z by 2. This is going to be the stoichiometric coefficient of O2. This is how we are going to balance this sort of a reaction as well. Okay. Similarly, my dear students, there are few more reactions from which questions are frequently asked, right? For example, you have got H2SO4. You are making it to react with NaOH, right? H2SO4, acid base. It's going to give us salt and water. So, for example, it's giving us NaHSO4, and with that, you are getting water. This again one more reaction, right? H2SO4 plus NaOH gives NaHSO4 plus water. Few more reactions I'm writing over here. From which questions will be frequently asked. Your H2SO4, if I make it to react with 2 times NaOH, it is going to give us Na2SO4, and with that you'll be writing 2 times water as well. This is one more reaction. Which I'll frequently use, right, in the questions. Who is saying this? Your friend Adil sir is my zoology teacher. Who is Adil sir? I don't know who is Adil. Which Adil you are talking about? Which Adil sir you are talking about? I don't know. Which friend of mine, namely Adil sir, is a zoology teacher? I don't have any friend namely Adil. I don't know what you're talking about. I hope I'm clear. All right, let's look at few more reactions. See guys, for example, you have got zinc plus 2 times HCl. It's going to give us ZnCl2. With this, you'll be getting H2 gas. Right? This is one more reaction from which questions will be framed. For example, you have got the reaction like this. Aluminium plus HCl. It is going to give us AlCl3. With this, you'll be writing H2 gas. Well, I'm not writing all the reactions in the balanced format. I'm just giving you the reactions. And we'll be balancing them when we'll start the questions. Right? So you just take a note of these reactions. Similarly, for example, we have got, this one is done. Okay. We have got, for example, sodium bicarbonate, NaHCO3. NaHCO3 upon heating, it gives Na2CO3. With this, you'll be writing water as well as carbon dioxide, right? My dear students, there is one more thing which I would want you to remember. Let's say you have got sodium carbonate. Sodium carbonate upon heating gives nothing, right? Sodium bicarbonate upon heating gives this. Sodium carbonate upon heating, right? There'll be no reaction. There'll be no reaction, okay? There will be no reaction. I hope I'm clear. Similarly, BaCl2 plus Na3PO4. It is going to give me Ba3PO4 whole twice plus NaCl. This is one more important reaction, right? From which questions have been framed and will be framed as well. Okay, so these are some of the important reactions which I would want you guys to remember. Now guys, how do we solve the questions? How do we solve the questions on stoichiometry? Some standard questions, basic questions with the help of which you will understand stoichiometry in a better way. See guys, look at the question carefully. The question is very simple and basic. Calculate the mass of O2. Calculate the mass of O2 gas produced on heating 12.25 grams of KClO3. As per the question is concerned, we are going to heat up KClO3. And you should know, on heating up KClO3, what do we get? We get KCl, and at the same time, we get O2 gas. We get O2 gas, right? This is something which you should know now. Now, as per the question, how many grams of KClO3 we are going to heat up? As per the question, we are going to heat up 12.25 grams of KClO3. My dear students, let me first of all show you how to solve this question with the help of mole method. Let me show you how do we solve the questions with the help of which method? Mole method. First thing always, whenever you see such kind of the questions, the first thing always is going to be balancing the reaction. So you are going to be balancing this reaction first, right? Balance the reaction, guys. This has to be 2 times, this has to be 2 times, this has to be 3 times. Is the reaction balanced? Yes, the reaction is balanced. Now, after balancing the reaction, the first step is to be balance the reaction. Second step, convert the given quantity into moles. Convert the given quantity into moles. In the mole method, we are supposed to convert the given quantity into moles. What is my given quantity? I'm given with mass. Mass of what? Mass of KClO3. So let me convert mass of KClO3 into moles of KClO3. So moles of KClO3 will be equal to given mass of KClO3 in grams divided by molar mass of KClO3, which is 122.5. When you solve it, the value comes out to be 0.1. So I converted given quantity into moles as well. Right? Balance the reaction, first step. Second step, convert the given quantity into moles. Done. Now, my dear students, in the reaction, I will be analyzing 2 components. First component, the one whose data is given. See, mass of KClO3 is given. So this is the one whose data is given. And at the same time, this is the one whose data is to be calculated. The one whose data is given and the one whose data is to be calculated. They are to be related. They are to be analyzed. Now people, since we are using the mole method, in the mole method we use stoichiometric coefficients as moles. We treat stoichiometric coefficients as moles. So can I say from the stoichiometry of the reaction, from the stoichiometric coefficient of reactants and products, can I say 2 mole KClO3, 2 mole KClO3 upon heating should produce 3 moles of O2? Yes. This is something which stoichiometry is telling me. 2 moles of KClO3 upon heating should produce 3 moles of O2. If I use the unitary method, I say 1 mole KClO3 upon heating should produce 3 by 2 moles of O2. Yes, it should produce 3 by 2 moles of O2. As per the question, do I have to heat up 1 mole of KClO3? No. As per the question, we have to heat up 0.1 moles of KClO3. So I would say 0.1 mole KClO3 upon heating should produce 3 by 2 multiplied by 0.1. The value comes out to be 0.15 moles of O2. If you look carefully, my dear students, if you look carefully, what is this particular term? These are the moles of O2 which are being produced when we heat up 0.1 moles of KClO3. When we heat up 12.25 grams of KClO3. Right? Now, as per the question, am I supposed to calculate moles of O2 produced? No. I'm supposed to calculate mass of O2 produced. Now, how do we convert moles into mass? So I'll say mass of O2 produced will be equal to moles of O2 produced multiplied by what? Multiplied by molar mass of O2. So moles of O2 produced is 0.15. Molar mass of O2 is 32 grams. The value comes out to be 4.8 grams. So this is the mass of O2 which will be produced on heating 12.25 grams of KClO3. This is the mass of O2 which will be produced on heating 0.1 moles of KClO3. Right? I believe this is clear to everyone. Right? I believe this is clear to everyone. So when we use the mole method, first thing, balance the reaction. Second thing, convert the given quantity into moles. Right? Now, in the reaction, we have to think about only 2 components. One whose data is given, one whose data is to be calculated. And remember, the one whose data has to be calculated, that has to be on the right side of the statement. See, in this statement, O2 is on the right side. Why O2 is on the right side? Because its data is to be calculated. So the one whose data is to be calculated, that has to be on the right side of the statement. This is solving the question with the help of mole method. Now, I'll solve the same question with the help of mass method. Then, whatever you find easy, you can solve that. You can do that. Let me solve the same question with the help of mass method. As per the question, what was given? As per the question, we were heating up 12.25 grams of KClO3. Right? And we know when KClO3 is heated, it gives KCl. And with that, you get O2 gas as well. So the question is saying, on heating 12.25 grams of KClO3, what mass of O2 will be produced? Now let's solve the question with the help of mass. Method. In mass method also, like your mole method, in mass method also, what we are supposed to do, we are supposed to balance the reaction. So balance the reaction first, 2 times, 3 times. The reaction is balanced. Now, in the mass method, my dear students, remember, we are supposed to convert the given quantity into mass. But if you look carefully, the given quantity is already in terms of mass. So we are not supposed to convert it. It's already in mass, right? You cannot convert mass into mass. It's already in mass. If it was not in mass, then I was supposed to convert it into mass. Now, I will be writing a statement in terms of mass. In mole method, I was writing the statement in terms of moles. Now here, I'll be writing the statement in terms of mass. Understand? In the reaction, I'll be considering 2 components. First component, whose data is given. Second component, whose data is to be calculated. Right? Okay? Yes? Now guys, tell me what is the molar mass of KClO3? Molar mass of KClO3 is 122.5 grams. That means mass of 1 mole of KClO3. That means mass of 1 mole of KClO3 is 122.5 grams. Do I have 1 mole of KClO3 or 2 moles? I have 2 moles of KClO3, right? I have 2 moles of KClO3. My dear students, mass of 1 mole of KClO3 is 122.5 grams. Therefore, mass of 2 moles of KClO3 will be 245 grams. Right? Now, what is the molar mass of O2? Molar mass of O2 is 32 grams. That means mass of 1 mole of O2 is 32 grams. If mass of 1 mole of O2 is 32 grams, what will be the mass of 3 moles of O2? 32 into 3, that means 96 grams. Now, as per this statement, I can say 245 grams of KClO3 on heating should produce 96 grams of O2. Use the unitary method. 1 gram of KClO3, 1 gram of KClO3 upon heating should produce 96 divided by 245 grams of O2. Right? But as per the question, do we have to heat up 1 gram of KClO3? No. We have to heat up 12.25 grams of KClO3. So 12.25 grams of KClO3 upon heating should produce 96 divided by 245 multiplied by 12.25 grams of O2. When you solve this, you get the value exactly as 4.8 grams. So you got to know exactly 4.8 grams of O2 are produced upon heating 12.25 grams of KClO3. I believe this is clear to everyone. I believe this is clear to everyone, right? So this is solving the same question with the help of which method? Mass method. And this is solving the question with the help of mole method. I hope you got the difference, right? But one thing I'll tell you guys, I would say 99% of the times we'll be solving the question with the help of mole method. Because remembering so many methods, that's going to confuse you only, right? Let's remember one method properly. Let's remember one method properly and let's try to utilize that method in the questions. And that one method here is going to be mole method, right? That one method here is going to be mole method, which we are going to remember properly, okay? Let's solve some more questions so that it becomes clear. Let's solve some more questions so that it becomes clear. See guys, the same question I'm taking in the reverse format. Same question I'm taking in the reverse format. The question is, calculate the mass of KClO3 required to produce 4.8 grams of O2 during its decomposition. So first of all, when KClO3 undergoes decomposition, when it is heated, it gets converted into KCl and with that you get O2 gas, right? Now the question says, what mass of KClO3 is required? What mass of KClO3 is required to produce what? To produce 4.8 grams of O2. To produce 4.8 grams of O2. In order to produce 4.8 grams of O2, what mass of KClO3 is required? So as I told you, we'll be solving the questions with the help of which method? Mole method. In the mole method, what do we do first? We try to balance the reaction. Is the reaction balanced? The reaction is not balanced yet. So I would be first of all balancing the reaction. So balance it. This has to be 2 times. This has to be 2 times. This has to be 3 times. The reaction is balanced. Well, after balancing the reaction, convert the given quantity into moles. What is the given quantity in this question? What is given quantity in this question? We are given with mass of O2. Convert the mass of O2 into moles of O2, right? So, moles of O2 will be equal to mass of O2 divided by molar mass of O2. The value will be 0.15. Whether you want to say that we have to produce 4.8 grams of O2 through this reaction, or you can say we need to produce 0.15 moles of O2 through this reaction. One and the same thing, right? One and the same thing. Now, my dear students, in the reaction, I have to consider only 2 components. One whose data is given, one whose data is to be calculated. And the one whose data is to be calculated, that has to be on the right side of the statement. So I'll be writing the statement in the reverse form. I'll write 3 moles. 3 moles of O2 are produced from. 3 moles of O2 are produced from. Produced from what? 2 moles of KClO3. Are produced from 2 moles of KClO3. Stoichiometry is telling me this. Therefore, 1 mole of O2 is produced from 2 moles of KClO3. Yes. If 1 mole of O2 is produced from these many moles of KClO3, therefore 0.15 moles of O2. Therefore 0.15 moles of O2 will be produced from 2 by 3 multiplied by 0.1. The value comes out to be 0.1 mole KClO3. So what did I get over here? My dear students, these are the moles. These are the moles of KClO3 which are required to produce 0.15 moles of O2. These are the moles of KClO3 which are required to produce 4.8 grams of O2. But as per the question, was I supposed to calculate moles of KClO3? No. I'm supposed to calculate mass of KClO3. Now, how do you convert moles into mass? Moles multiplied by molar mass, right? The value comes out to be 12.25 grams. So I would say 12.25 grams of KClO3 are required to produce 0.15 moles of O2 to produce 4.8 grams of O2. I believe this is clear to everyone. Yeah? I believe this is clear to everyone. Perfect. So you should be able to solve this sort of a question as well. Right? It was a simple basic question. Let's try to solve a few more questions so that you get used to it properly. Look at this question, guys. Look at this question. It's again one simple question only. Calculate the volume of carbon dioxide gas produced at STP by complete combustion of 570 grams of octane. So we are doing the combustion of octane. Octane is C8H18. If we are doing its combustion, that means your products here will be carbon dioxide, and with carbon dioxide, you'll be getting water. Perfect. Now, as per the question, calculate the volume of carbon dioxide gas produced. Calculate the volume of carbon dioxide gas produced at STP by complete combustion of 570 grams of octane. 570 grams of octane. So as per the question, we need to do the combustion of 570 grams of octane. My dear students, which method we are using? Mole method. In the mole method, the first thing, we need to balance the reaction. So balance it. Balance it. This is 8, so make it 8 times. This is 18. 18 by 2 is 9 times. And the stoichiometric coefficient here used to be x plus y by 4, if you remember. X plus y by 4 comes out to be 25 by 2. And here the stoichiometric coefficient is 1. In the reaction, I have to consider only two components. The one whose data is given and the one whose data is to be calculated. That's all. Right? Now, in the mole method, since we have balanced the reaction, what is the second thing? Convert the given quantity into number of moles. What is the given quantity here? What is given to us? We are given with mass of octane. So convert the mass of octane into moles of octane. So moles of octane will be equal to mass of octane divided by molar mass of octane. The value comes out to be 5. So technically, if you see, we need to do the combustion of 570 grams of octane. That means we need to do the combustion of 5 moles of octane. Right? Now, what stoichiometry is telling us? What stoichiometry is telling us? Stoichiometry is telling us that 1 mole octane when undergoes combustion, when 1 mole octane when undergoes combustion, 8 moles of carbon dioxide are produced. 8 moles of carbon dioxide are produced. Therefore, when 5 moles of octane undergoes combustion, 8 multiplied by 5, 40 moles of carbon dioxide are produced. 40 moles of carbon dioxide are produced. So, these are the moles of carbon dioxide which are produced during the combustion of 5 moles of octane. These are the moles of carbon dioxide which are produced during the combustion of 570 grams of octane. Right? Perfect. 570 grams means 5 moles of octane. But as per the question, was I supposed to calculate moles of carbon dioxide produced? No. I'm supposed to calculate volume of carbon dioxide. Now, how do you convert moles into volume at STP? I'll say volume of carbon dioxide produced will be equal to moles of carbon dioxide produced multiplied by 22.4 liters, right? So this has to be 40 multiplied by 22.4. The value comes out to be 896 liters. So I would say 896 liters of carbon dioxide gas will be produced during the combustion of 5 moles of octane, during the combustion of 570 grams of octane. I believe this is also clear to everyone. Yeah? Perfect. Now, let's solve this question. Let's solve this question, guys. It's again simple. It's again simple. Sir, Hindi bolo. भाई चैनल का नाम देख पहले क्या है. चैनल का नाम है अनअकैडमी नीट इंग्लिश, और अंग्रेजी चैनल पे हिंदी नहीं बोलते. या Is it clear, guys? Is it clear? UAC method also I'll be showing. Just wait. Perfect. Let's move on. Let's try to solve this particular question. See, as per the question, there is some reaction given to us, and I believe the reaction is already given in the balanced format. That's good for us. So 3 times NO2 plus H2O. What does it give? It gives 2 times HNO3, and with that, we have NO. Perfect. How many grams of NO2? How many grams of NO2 are required to produce 25.2 grams? To produce 25.2 grams of HNO3. As per the question, in order to produce 25.2 grams of HNO3, how many grams of NO2 are required? How many grams of NO2 are required through this reaction? So, since the reaction is balanced and we are solving the equations with the help of mole method, my first step right now will be to convert the given quantity into moles. Given quantity here is mass. We are given with mass of HNO3. So convert the mass of HNO3 into moles of HNO3. So moles of HNO3 will be equal to mass of HNO3 in grams divided by, what is the molar mass of HNO3? It will be 63 grams per mole, right? Can you let me know in the chats how much this value comes out be after solving? Can you let me know in the chats, people? Can you let me know in the chats how much this value comes out be after solving? 25.2 divided by 63? Quickly, everyone. How much it's going to be? Is it going to be 0.4, I think? Right? Is it 0.4? Okay, people are saying 0.4, all right. So as per the question, whether you want to say that we have to produce 25.2 grams of HNO3, or you can say we have to produce 0.4 moles of HNO3. Completely your choice, right? Now guys, since we are using the mole method, right? I'll be writing a statement. In the reaction, I have to consider only two things. The one whose data is given, the one whose data is to be calculated. And the one whose data is to be calculated, that has to be on the right side of the statement. So I'll write the statement in the reverse format. I'll write 2 moles of HNO3. 2 moles of HNO3 are produced from 3 moles of NO2. 2 moles of HNO3 are produced from 3 moles of NO2. Therefore, I can say 1 mole HNO3 will be produced from 3 by 2 moles of NO2. Okay? But as per the question, do we have to produce only 1 mole of HNO3? No. We have to produce 0.4 moles of HNO3. So I would say 0.4 moles of HNO3 are produced from 3 by 2 multiplied by 0.4. It comes out to be 0.6 moles of NO2. So what did we get over here? We got the moles of NO2. These are the moles of NO2 which are required. These are the moles of NO2 which are required to produce 0.4 moles of HNO3. To produce 25.2 grams of HNO3. But as per the question, I was not supposed to calculate the moles of NO2. I was supposed to calculate the mass of NO2. Now, how do you convert moles into mass? Simple. Moles multiplied by its molar mass. Its molar mass will be, this is 32 plus 14, that's 46, right? So when you solve this, the value will be 27.6 grams. So I would say 27.6 grams of NO2. 27.6 grams of NO2 are required to produce 25.2 grams of HNO3. Is that clear? Is that clear, people? I hope this is clear to everyone. I hope this is clear to everyone. Perfect. Now, try to solve this particular question as well. Try to solve this particular question as well. See, again, if you look at this particular reaction, it is given to us in the balanced format, and the reaction is 4 times HCl plus MnO2, it gives MnCl2 plus 2 times water plus Cl2 plus Cl2. This is the reaction that is given to us. Okay. This is the reaction that's given to us. And my dear students, this particular reaction is already given in the balanced format. If this particular reaction is given in the balanced format, so one step is reduced. I'm not supposed to balance it. It's already given in the balanced format. Now look at the question carefully. How many grams of HCl? How many grams of HCl are needed for the complete reaction? How many grams of HCl are needed for the complete reaction with 69.6 grams of MnO2? So the question says, how many grams of HCl we need to react with 69.6 grams of MnO2, right? Perfect. Now, my dear students, which method we are using? Mole method. In the mole method, what's the first thing? What is the first thing? What is the first thing? We are supposed to convert the given quantity into moles, right? So we are given with the mass of MnO2. So convert into moles. So number of moles of MnO2 will be equal to mass of MnO2 divided by molar mass of MnO2. How much this value comes out to be? I think 0.8. I think it will be 0.8, right? Yes. So I've converted the given quantity into moles. Now in the reaction, we just have to consider two components. The one whose data is given, the one whose data is to be calculated, and the one whose data is to be calculated, that has to be on the right side of the statement. So how do I write the statement? I'll be writing it like this. 1 mole MnO2. Stoichiometry is telling us 1 mole MnO2 reacts with 4 moles of HCl. 1 mole MnO2 reacts with 4 moles of HCl. If 1 mole MnO2 reacts with 4 moles of HCl, therefore 0.8 moles of MnO2 will be reacting with 4 multiplied by 0.8. The value is going to be 3.2 moles of HCl, right? So these are the moles of HCl. These are the moles of HCl which are required to react with 0.8 moles of MnO2. These are the moles of HCl which are required to react with 69.6 grams of MnO2. But am I supposed to calculate moles of HCl? No. I'm supposed to calculate mass of HCl. How do I convert moles into mass? So moles multiplied by molar mass of HCl, right? Moles multiplied by molar mass of HCl. I think this will be 116.8 grams. Yes? Right, people? Am I clear? So I would say 116.8 grams of HCl are required to react with 69.6 grams of MnO2. So tell me quickly whether you will be able to solve these sort of questions on your own now. Quick, everyone. Quickly, guys, everyone. Quickly, guys. Quickly, I'm texting one of my friend. Just a second. Okay, so I believe all the things are clear till here. Perfect. I believe all the things are clear till here. Sir, if oxidation state is given, how can we overcome the problem? What? I did not get you. What are you trying to say? What are you trying to say? If oxidation state is given, how to overcome it? Like what? Is this clear, people? I think yes, yeah? Perfect. Let's move on. Now, let's try to have a look on one more important topic. What is that? That is stoichiometry, which is involved in the sequential reactions, right? how do we utilize, how do we, solve the questions which are basically based on the sequential reactions, right? Let's try to understand this in detail. See, guys. See, there are few things which you need to remember over here. That's all. Few things which you need to remember. That's it. Understand. For example, you have got the reaction like this. A plus B. Let's say it gives C. Let's say it gives C. The C which is formed in this reaction, let's say it reacts with D and is forming E. Okay. The E which is getting formed over here, let's say that reacts with F. What do we have after F? A, B, C, D, E, F, G. Okay. It gives G. Right? First of all, these are the series of the reactions. These are the series of the reaction. Right? Which we call as the sequential reaction. We call them as the sequential reaction. My dear students, one thing you have to remember over here. One thing. See, in the first reaction, C is being produced. In the first reaction, C is being produced. C will be getting formed in the first reaction. Remember, whatever amount of C will be formed in the first reaction. See, the C is the product of the first reaction, but at the same time, the same C is the reactant of the second reaction. This C is the product of the first reaction. At the same time, this C is the reactant of the second reaction. E is the product of the second reaction, but at the same time, E is the reactant of the third reaction. And the concept which you'll be using here, the concept is going to be very simple. The concept is, whatever C is formed in the first reaction, all that C will be used over here. All that C will be consumed over here in the second reaction. Whatever E gets formed in the second reaction, all that E gets consumed over here in the third reaction. Just this concept will be using, nothing else. Just this concept will be using, nothing else. Yeah? Whatever product we get in the first reaction, that entire product is consumed in the second reaction. Whatever product we get in the second reaction, that entire product is consumed in the third reaction. This is the concept we'll be using, and we are done. And we are done, people. Yeah? Let's have a look. How come we are done? Try to understand what I'll be saying. For example, this is your reaction. Let's say this is your reaction. Okay? Analyze this reaction carefully. Again, my dear students, if you see, we are given 3 reactions, right? The question says calculate the mass of KClO4. Calculate the mass of KClO4 formed on starting with 568 grams of Cl2. So as per the question is concerned, we are starting with 568 grams of Cl2. We are starting with 568 grams of Cl2. And we have to calculate the mass of KClO4 which gets formed at the end. Right? We have to calculate the mass of KClO4 which gets formed at the end. Okay? Now guys, which method we are using? Mole method. In mole method, the first thing is to balance the reactions. And all these reactions are already balanced. All these reactions are given in the balanced format. Right? Now people, the first thing in the mole method, balancing the reaction is done. Now after balancing, what am I supposed to do? I'm supposed to convert the given quantity into moles. What is my given quantity? I'm given with mass of Cl2. So let me convert mass of Cl2 into moles of Cl2. So moles of Cl2 will be given mass of Cl2 in grams divided by molar mass of Cl2. What is the molar mass of Cl2? Molar mass of Cl2 will be 71, right? The value comes out to be 8. So basically we are starting with 8 moles of Cl2. We are starting with 8 moles of Cl2, right? We are starting with 8 moles of Cl2. Perfect. Now, my dear students, understand carefully. Understand carefully. What is getting formed in the first reaction? Or if I ask you like this, what is common in first and second reaction? I would say KClO is common in first and second reaction. In second and third reaction, what is common? KClO3 is common. In first and second, I saw the common components. In second and third, I saw the common components. Right? Now people, understand. Now people understand. If you analyze the first reaction properly, stoichiometric coefficient here is 1, here it's also 1. Okay? So from the first reaction, can I say 1 mole Cl2. 1 mole Cl2 as per stoichiometry gives 1 mole KClO. If 1 mole Cl2 gives 1 mole KClO, therefore 8 moles of Cl2. 8 moles of Cl2 will be giving 8 moles of KClO. So I got to know in the first reaction, 8 moles of KClO are being formed, right? As I told you, whatever KClO will be formed in the first reaction, all that KClO will be consumed here. Okay? Now, look at the second reaction. The second reaction, stoichiometry is telling us that 3 moles of KClO gives 1 mole KClO3. 3 mole KClO gives what? Gives 1 mole KClO3. Gives 1 mole KClO3. Therefore, I can say 1 mole of KClO gives 1 by 3 moles of KClO3. Gives 1 by 3 moles of KClO3. Okay? 1 mole KClO gives 1 by 3 moles of KClO3. How many moles of KClO we have here? Since 8 moles got formed in the first reaction, all that 8 moles will be consumed over here. So I would say 8 moles of KClO should give me 8 by 3 moles of KClO3. So I got to know in the second reaction, how many moles of KClO3 are being formed? 8 by 3 moles of KClO3 are being formed. Now, whatever KClO3 is formed in the second reaction, all that KClO3 will be utilized here. Right? Now, understand and look at the third reaction and analyze its stoichiometry. I'll say 4 moles are giving me 3 moles. I'll say 4 moles KClO3 gives 3 moles of KClO4. Therefore, 1 mole KClO3 gives 3 by 4 moles of KClO4. As per the reaction, how many moles of KClO3 got formed here? 8 by 3. All these 8 by 3 moles of KClO3 will be consumed here. So I would say 8 by 3 moles of KClO3 would be giving 3 by 4 multiplied by 8 by 3. The value comes out to be 2 moles of KClO4. So at the end, I got to know that 2 moles of KClO4 are being formed at the end of the reaction. 2 moles of KClO4 are being formed at the end of the reaction. But as per the question, am I supposed to calculate moles of KClO4 formed or mass of KClO4 formed? I'm supposed to calculate mass of KClO4 formed. So I'll say mass of KClO4 formed will be equal to moles of KClO4, that's 2, multiplied by molar mass of KClO4. What is the molar mass of KClO4? Can you let me know in the chats? Anyone calculated? Anyone calculated the molar mass of KClO4? Quick. Quick, people. Anyone calculated the molar mass of KClO4? I think it will be 138.5, I believe. Is that? Is that? I think somewhat around that. 138 point something. Yeah, 138.5. 138.5 grams, right? So when you solve this, the value comes out to be 267 grams. I got to know 267 grams of KClO4 are being formed at the end of the reaction. Am I clear with this? Am I clear with this? So guys, in simple words, whatever product we are getting in the first reaction, all that product is being consumed in the second reaction. Whatever product we get in the second reaction, all that product is getting consumed in the third reaction. That's all. Simple concept we'll be using and we'll be done. Yeah? Perfect. Let's try to solve one more question based on the same format so that it'll be like properly clear. Okay, look at this question. Let me make calculation a bit easy. Let me just change the values and make a calculation a bit easy. So let's call it as 224 liters. 224 liters of NH3. Okay. Can you give it a try? Can you give it a try? As per the question, calculate the mass of HNO3. Calculate the mass of HNO3 formed on starting with 224 liters of NH3. 224 liters of NH3. So, reactions are already balanced. Now, first thing, convert the given quantity into moles, right? Now, I'm given with volume of NH3. I'm converting it into moles. So, moles of NH3 is equal to given volume of NH3 in liters divided by 22.4 liters. The value comes out to be 10. So we are starting with 10 moles of NH3. We are starting with 10 moles of NH3, right? We are starting with 10 moles of NH3. Now guys, understand. What is common in first and second reaction? NO is common in first and second. What is common in second and third? NO2 is common in second and third, right? So can I say whatever NO2 gets formed, whatever NO gets formed in the first reaction, all that NO will be utilized here, will be consumed here. Whatever NO2 gets formed in the second reaction, all that NO2 gets utilized here. And finally HNO3 gets formed. That is the concept which I'll be using. Okay. Now, first of all, use the stoichiometry. This is 4, this is 4. I can say 4 moles of NH3 gives 4 moles of NO. 1 mole of NH3 gives 1 mole of NO. Therefore, 8 moles of NH3 will be giving 8 moles of NO. So in the first reaction, 8 moles of NO are being formed, right? Whatever NO is getting formed here, that has to be getting consumed here, right? Okay. Now, stoichiometry is telling you that 2 moles of NO gives 2 moles of NO2. Therefore, 1 mole of NO gives 1 mole of NO2. So, 8 moles of NO should be giving me 8 moles of NO2. So, in the second reaction, 8 moles of NO2 are being formed. And whatever NO2 is formed here, all that NO2 is consumed here, right? Now, use the stoichiometry in the third reaction. 3 moles of NO2 are giving me 2 moles of HNO3. 1 mole of NO2 will be giving me 2 by 3 moles of HNO3. 8 moles of NO2 are going to give me 2 by 3 multiplied by 8 moles of HNO3. Right? 8 2s are 16 by 3. Alright, guys? So, we got to know 16 by 3 moles of HNO3 are formed at the end of the reaction. If you got the moles of HNO3 formed, you can easily convert moles into mass. Oh, in the question they are given with 10 moles. And how many we took 8 moles. Why did it take 8 moles? Okay, we'll modify the data accordingly, right? 22.4 multiplied by 8. 8 4 32. 8 2 16 19. 8 2 16 17. 179.2. So modify the data. Modify the data as 179.2 liters. So that this has to be 179.2 liters, and at the end, what do we get? At the end, what do we get? We get 8 moles here. Now it's clear? Guys, it's completely in my hand. Like, whatever I would want to do, we can do that. That's it. Done? Now it's fine? Yeah, it is fine now. It is fine now. Okay, so what did I calculate here? I got the moles of HNO3. But am I supposed to calculate moles or mass? I'm supposed to calculate mass, right? I'm supposed to calculate mass of HNO3. So mass of HNO3 has to be equal to moles of HNO3 multiplied by molar mass of HNO3, right? So solve it, get the final answer in grams. That's it. Done and dusted? Yeah? All clear? All clear, people? Perfect. Let's try to solve one more question. This is your one more question, guys. Calculate the mass of polyethylene. Calculate the mass of polyethylene that can be produced from 10 kg of CaC2. So we are starting with 10 kg of CaC2. Yeah? We are starting with 10 kg of CaC2. First of all, the reactions are already balanced, correct? The reactions are already balanced. Now, the first thing, after balancing the reaction, if you remember, what are we supposed to do? What are we supposed to do? We are supposed to convert the given quantity into moles. The given quantity is in terms of mass, so convert it into moles. So number of moles of CaC2 will be equal to given mass of CaC2 in grams divided by, what is the molar mass of CaC2? It will be 64. It will be 64. So these many moles of CaC2 we have over here. We are starting with these many moles of CaC2. Okay. Now, first of all, what is common in first and second reaction? C2H2, C2H2. Second and third, C2H4, C2H4. Finally, polyethylene is being formed. Okay. Now we use the stoichiometry properly. Can I say 1 mole CaC2 gives 1 mole C2H2? Therefore, 10,000 by 64 moles of CaC2 will give me 10,000 divided by 64 moles of C2H2. So I got to know in the first reaction, 10,000 by 64 moles of C2H2 are being formed. Now, whatever C2H2 is being formed over here, all this C2H2 will be consumed here, right? Now, you see, look at the stoichiometry. 1 mole of C2H2 gives 1 mole of C2H4. Therefore, 10,000 by 64 moles will give me 10,000 by 64. So, 10,000 by 64 moles of C2H4 are being formed here. Now, whatever C2H4 is being formed here, all the C2H4 will be consumed here. See, the stoichiometric coefficient here is n, here is 1. I can say n moles of C2H4 are going to give us 1 mole of polyethylene as per the question, as per the third reaction. N moles are giving us 1 mole. Therefore, 1 mole C2H4 is going to give us 1 divided by n moles of polyethylene. Okay. I would say 10,000 by 64. I would say 10,000 divided by 64 moles of C2H4 are going to give us 1 by n multiplied by 10,000 divided by 64 moles of polyethylene. Correct? So these are the moles of polyethylene which are being formed at the end of the reaction. But are we supposed to calculate moles of polyethylene formed? No. I'm supposed to calculate mass of polyethylene formed. So how do you convert moles into mass? Mass of polyethylene will be equal to moles of polyethylene, which is 10,000 divided by 64n multiplied by. What is the molar mass of this polyethylene here? See, 12 into 2 is 24. 24 plus 4 is 28. But it's not just 28. It's 28n, right? So multiply with molar mass, which is 28n. N say n cancelled. What is the value which you are getting after here? People are saying 4375. Okay, I trust you here. 4375 grams. I would say at the end of the reaction, 4375 grams of polyethylene would be getting formed at the end of the reaction. I hope this is clear. Right, people? So you should be in a position to solve these sort of questions as well. You should be in a position to solve these sort of questions as well. Perfect? Perfect, people? Now, there is one more method, my dear students. There is one more topic, that is POAC. Sometimes you won't be able to solve questions with the help of mole method. Sometimes you won't be able to solve questions with the help of mole method. Okay? Therefore, at that point of time, which method you are going to use? You are going to use POAC. Is your HSP sir in the chats? People are writing Baba. Where is he? Let me check. Oh, Baba Chemistry is here. HSP Baba is here. What's up? What's up? How you are? How are you? Baba HSP कैसे हैं आप? जिंदा हो? जिंदा है, हाँ? Why am I not able to see the chats? I'm not able to see the chats. I don't know why. Okay, we'll continue. We'll continue now. Okay, look at this principle of atom conservation. My dear students, I told you sometimes you won't be able to solve the question with the help of mole method or mass method. So whenever you are stuck, POAC is going to help you out. Whenever you are stuck, POAC, principle of atom conservation, is going to help you out. Now see, how do we use this concept? Principle of atom conservation. Principle of atom conservation. What this principle of atom conservation is all about, I've got nothing to do with that. Let me quickly show you how to apply this and solve the questions. That's all what I need. That's all I need. Okay, that's all I need. Understand carefully, like what exactly I'm going to do. For example, my dear students, I've got a reaction. Let's say I've got a reaction like this. A2B3 plus, for example, B2C3, it gives A4C5 plus B2D3. Let's say this is one general reaction. Let's say this is one general reaction. My dear students, can you use mole method or mass method here in this reaction? See, in mole method, mass method, we are supposed to balance the reaction, right? Will you be able to balance this sort of a reaction? You won't be able to balance this sort of a reaction, right? You won't be able to do that. You won't be able to balance this sort of a reaction. Whenever you will be unable to balance the reaction, right? Or a reaction given to you is incomplete, which eventually you cannot balance, right? At that point of time, you cannot use mole method, you cannot use mass method. So what is the only option left at that time? POAC. So the first benefit of using POAC is we are not supposed to balance the reaction. The first benefit of using POAC is that we are not supposed to balance the reaction. Number one. Number two. Now, my dear students, here, what you'll be doing, you'll be making POAC equations. You'll be making POAC equations. For example, I'm making POAC equation for atom A. Let's say I'm making POAC equation for atom A. See how I'm going to make it. Do you see A here? Yes. How many atoms of A? 2. So I'll be writing 2 multiplied by number of moles of this whole compound. Number of moles of this A2B3. Do you see A here? No. I've got nothing to do with this. In place of arrow, I'll be using equal to. Do you see A here? Yes. How many? 4. So 4 multiplied by number of moles of A4C5. Do you see A here? No. So this is one complete POAC equation in terms of A atoms. In terms of A atoms. Similarly, my dear students, can we make POAC equation for B atoms? Let's give it a try. First of all, do you see B here? Yes, there are 3 atoms of B. So I'll be writing 3 multiplied by number of moles of this entire compound A2B3. A2B3, right? Do you see B here? Yes. How many? 2, right? So sign here is plus in between. So plus. Now, 2 atoms of B. So 2 multiplied by number of moles of B2C3. Instead of arrow, equaled. There is no B here. Leave it. B is here. How many? 2 multiplied by number of moles of B2D3. So this is your one more POAC equation in terms of B atoms. Similarly, can you make POAC equation in terms of C atoms? Now, I believe you can. There is no C here. Here we have got C. How many? 3. So 3 multiplied by number of moles of this entire compound, that is B2C3. Instead of arrow equaled, C is here, 5 atoms. So 5 multiplied by number of moles of A4C5. This equation I'll be calling as complete POAC equation in terms of C atoms, right? So first of all, you got to know how to make the POAC equations. You got to know how to make the POAC equations. Now it is the time to utilize. It is the time to utilize all of this in the equations. It's the time to utilize all of this in the equations. See guys, understand what exactly I'm going to do. Understand what exactly I'm going to do. Understand what exactly I'm going to do. Look carefully guys. For example, I'm writing a question. Let's say I'm writing the question like this. One question which will make your POAC completely clear. Completely clear. For example, one question I wrote few minutes back, that combustion of octane, 570 grams of octane. let's try to solve the same question with the help of POAC so that you understand the concept. Okay. The question is, for example, during the combustion of 570 grams of octane. During the combustion of 570 grams of octane. Calculate. Number 1. Moles of carbon dioxide and water formed. Number 2. For example, moles of O2 consumed. Moles of O2 consumed. See guys, first of all, I'll be writing the reaction. I'll be writing the combustion reaction. Combustion of octane. C8H18 plus O2 gives carbon dioxide. With carbon dioxide, we get water. This is the reaction. Now, what exactly am I going to do? I'm going to use POAC here. In POAC, I'm not supposed to balance the reaction. I'm not going to balance the reaction, right? Now, what is the first step here? The first step is going to be convert the given quantity into moles. That is the same here also. We are supposed to convert the given quantity into moles. So calculate number of moles of octane, which is going to be equal to given mass of octane in grams divided by molar mass of octane. The value is going to be 5. The value is going to be 5. Now, what you have to do here? You're not supposed to balance. Now just make the POAC equations. Let's make the POAC equations for carbon atoms first of all, right? So here you have got carbon, so 8 multiplied by number of moles of octane, right? Here you do not have a carbon, leave it. Instead of arrow equaled, yes, 1 carbon. So 1 multiplied by number of moles of carbon dioxide. Here you don't have carbon, so leave it. So this one complete equation. Now, write the POAC equation for example, hydrogen. How many hydrogen atoms here? 18. So 18 multiplied by number of moles of this entire compound, that's octane. Hydrogen is not here, leave it. Instead of arrow equaled, hydrogen is not here, hydrogen is here. So 2 multiplied by number of moles of water. Similarly, make the POAC equation for oxygen. That is the only thing left. Oxygen is not here, oxygen is here. How many? 2. So 2 multiplied by number of moles of this entire compound. Instead of arrow equaled, this is going to be 2 multiplied by number of moles of carbon dioxide, plus this is going to be 1 multiplied by number of moles of water. So how many equations I made? I made 3 equations. Now guys, understand. If you look at equation number 1, equation number 1 is going to be 8 multiplied by number of moles of octane. Have we calculated? Yes, 5. 8 into 5 is equal to number of moles of carbon dioxide. So you got to know number of moles of carbon dioxide came out to be 40. Is carbon dioxide consumed in the reaction or produced? Carbon dioxide is produced. So 40 moles of carbon dioxide are produced, right, in the reaction. First question is done, right? Look at the second equation. It is going to be 18 multiplied by number of moles of octane. We have already calculated 5 is equal to 2 multiplied by number of moles of water. So from this particular equation, you can calculate moles of water. It is going to be 18 multiplied by 5 is 90. 90 divided by 2 is 45. So 45 moles of water are produced. 45 moles of water are produced, right? This was the second thing. Look at the third equation now. In the third equation, do we know the number of moles of carbon dioxide which are being produced? 40. So 2 multiplied by 40 is 80. Plus number of moles of water, 45. This 2 in the denominator. Is going to give us number of moles of O2. So it is going to be 125 divided by 2. So 2622.5. So what did we get? These are the moles of O2. Since O2 is being consumed here, so 62.5 moles of O2 are being consumed. So these were the 3 things which we were supposed to calculate, and we are done. Understood? Is it clear? Is it clear, people? Did you understand how do we use this concept? I would want some thumbs ups in the chats if you exactly understood how do we use POAC in the questions. Lecture will continue till 2, 3. Yes. Yes. Around that. Let's try to solve one more question. See guys, why I showed you POAC? Because I just wanted to solve this particular question. Because I wanted to solve this question. This question you will not be able to solve with the help of mole method. This question you will not be able to solve with the help of mass method. Why? Because the reaction which you are going to write here, that is not a complete reaction. If the reaction is not complete, that means you won't be able to balance it. If you are not able to balance it, you cannot use mole method or mass method. Right? Correct? Correct, people? Have a look now. See. Understand properly. As per the question, 27.6 grams of K2CO3. 27.6 grams of K2CO3 was treated by a series of reagents. I have no idea what the reagents are. But it is mentioned that 27.6 grams of K2CO3 was treated by a series of reagents so as to convert all of its carbon to what? So as to convert all of its carbon to K2, Zn3, FeCN6 twice. The question is saying calculate the weight of the product formed. Calculate the weight of the product formed, right? This is my product here, which I'm representing with P. I just need to calculate the mass of the product formed. Guys, understand? 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 See, as far as this particular question is concerned, 27.6 grams of K2CO3 was treated by a series of reagents. I have no idea what the reagents are. So as to convert all of its carbon. So whatever carbon is present in K2CO3, that entire carbon is finally reaching into this product. So carbon is remaining conserved here. Carbon is remaining conserved here, right? We have to calculate what mass of product is formed. Since the reaction is not complete, you have no idea what these reagents are. I have no idea what these reagents are. If I have no idea what these reagents are, I won't be able to balance the reaction. If I am unable to balance the reaction, I won't be able to use the mole method. I won't be able to use the mass method because there you have to balance the reaction. So what is the only option left? POAC. POAC, yeah? So that's why this is game of NEET 2.0, right? So people, what is the thing which we do in POAC? We are not supposed to balance the reaction, but we are supposed to convert the given quantity into moles. We are given a mass of K2CO3, so convert it into moles of K2CO3. It is going to be given mass of K2CO3 in grams divided by molar mass of K2CO3, which is 138. So these many moles of K2CO3 we have. These many moles of K2CO3 we have, right? These many moles of K2CO3 we have. Perfect. Now, which atom is remaining conserved here? In the question itself, they are saying whatever carbon is present in K2CO3, that entire carbon is finally reaching into the products. So carbon is remaining conserved. Carbon is remaining conserved. So I'll make POAC equation for which atom? I'll make POAC equation for carbon, right? So it's carbon here. It's going to be 1, since there is 1 carbon multiplied by number of moles of K2CO3. I'm assuming in all the other reactants, there is no carbon, right? Whatever carbon is on the reactant side, that all the carbon is in K2CO3 and that entire carbon is finally reaching into product. So it is mentioned in the question. Therefore, all the carbon is here in K2CO3 and all that carbon is reaching into the product. So there is no carbon here, no carbon here. Instead of arrow, I'll be using equal. So how many carbon do you have here? 6 2s are 12. 12 carbon multiplied by number of moles of entire product. So from this particular equation, number of moles of K2CO3 is how much? Or let me write it like this. Number of moles of product is equal to number of moles of K2CO3 divided by 12. So how many moles of K2CO3 we have? It is 27.6 divided by 138 whole divided by 12. So this is going to give me the number of moles of product formed. But as per the question, I'm not supposed to calculate the moles of product formed. I'm supposed to calculate I'm supposed to get the mass of product formed. Mass of product will be moles of product formed multiplied by molar mass of product. Moles of product we have calculated as 27.6 divided by 138 multiplied by 12 multiplied by molar mass of product. When you calculate the molar mass of this product, it will be 698, right? And final answer you'll be getting in grams. Perfect. So this is where you guys are going to use the POAC. Am I clear? Am I clear? Am I clear, people? Did you understand where do we use the principle of atom conservation? Right? I hope I'm all clear with this. I hope I'm all clear with this. Right, people? Now, before doing some small topics, let's cover one good topic here, which you skip majority of the times. What is that? That is mixture analysis. Okay? Mixture analysis. Do you want a break for like 5-10 minutes? Do you want a break for like 5-10 minutes? So that your brain will start braining again? Do you want break for 5-10 minutes? Guys, session will continue till 2-3, right? See, we are done with 7 hours. Just 3 to 4 more hours, right? I'm just waiting for that internal satisfaction when I complete this chapter in detail. Let's take a break so that we'll get refreshed properly. So I'll see you all. Break till 12:15. But be back on timer. You're supposed to be back on time. Perfect? Okay? See where the competition is going. It's going down. Relax. It's okay. You guys are the ones. You guys are the ones. So people could not sit for 12 hours. Right? People could not sit for 12 hours. Wow. Is it PM or wait? Is it PM or AM? Actually, brain has stopped braining, huh? It's AM. So be back on time, huh? I'll be also back on time. See you. See you in a while. Are you all back? Yes. Are you all back? Yeah, good morning, good morning. What's up? How are you all doing? All good? All well? Are you liking these mornings? Are you liking these mornings? Perfect, perfect. I think the brain has started braining now, yeah? Exactly. This would be the most productive morning of yours. Chalo, I think let's get going then. Yeah, let's get going. Let's get going. Let's get going. So now we are going to enter into mixture analysis. Mixture analysis. This is again one important topic, right? And people find it like difficult, right, to solve the questions based on mixture analysis. So we'll exactly again be doing it from the basics, from the scratch only, so that you'll understand it properly. Okay? So guys, in mixture analysis, what exactly are we going to do? Just give me a second. Let me start with a question directly so that you'll understand. Let me start with a question directly so that we'll understand what this mixture analysis exactly is all about. See guys. Look at the question, and by solving this particular question, you'll understand exactly what this mixture analysis is all about and what kind of problems can be asked. The question says 1 gram of an alloy, 1 gram of an alloy of magnesium and aluminium reacts with HCl to produce 1.12 liters of H2 gas at STP. Calculate the composition of the alloy. See guys what the question is all about. Understand. Imagine that this is one container which I'm taking, and in this container we have kept two elements. One is your magnesium and one is your aluminium. These are the two elements which are present in the container, magnesium and aluminium. My dear students, we have got mixture of two elements here, right? This is a mixture of two elements. As per the question, the mass of this complete mixture, the mass of this whole mixture, that is 1 gram. That is 1 gram. So if I ask you, is 1 gram the mass of magnesium? No. Is 1 gram the mass of aluminium? No. 1 gram is basically the mass of this whole mixture. Mass of this entire mixture is 1 gram. Now, as per the question is concerned, in this mixture, we are adding HCl. As per the question, in this mixture, we are adding HCl. Now, when we are adding HCl into this mixture, what is happening as per the question? When we are adding HCl in the mixture, H2 gas is being produced. H2 gas is being produced, right? H2 gas is being produced. What volume of H2 is being produced as per the question? when HCl is added in the container, H2 gas is liberated. H2 gas is produced. How much H2 gas is produced? As per the question, 1.12 liters. 1.12 liters of H2 gas is produced when HCl is added in the container. And this H2 gas is being produced at STP. The first thing if I ask you, if 1.12 liter of H2 gas is being produced at STP, can you let me know how many moles of H2 gas will be getting produced? It is 1.12 liters divided by 22.4 liters. So these many moles of H2 gas are being produced when HCl is introduced in this container. Okay? Right? Now, my dear students, try to understand. What is the mass of the entire mixture? 1 gram. Okay? Let's assume out of 1 gram, X grams is the mass of magnesium in the container. Therefore, 1 minus X grams. This is going to be the mass of aluminium in the container. X grams is the mass of magnesium in the container. 1 minus X grams, this is the mass of aluminium present in the container. Right? Now, one more thing if I ask you how many moles of magnesium are there in the container, you'll say mass of magnesium divided by molar mass of magnesium. So these are the moles of magnesium in the container. Similarly, 1 minus X divided by 27. These are the moles of aluminium in the container. Right? These are the moles of magnesium in the container. These are the moles of aluminium in the container. Now, my dear students, just think over it. When HCl is introduced in the container, H2 gas is being produced. How H2 gas would have got produced? Can I say the HCl which we are adding, some amount of HCl would be reacting with magnesium and some amount of HCl would be reacting with aluminium. So how many reactions would have happened? I believe 2 reactions would have happened. Reaction number 1, HCl reacting with magnesium. HCl reacting with magnesium. When HCl reacts with magnesium, what do we get? We get MgCl2, and with this, H2 gas would be produced. Similarly, some amount of HCl would have reacted with aluminium as well. Some amount of HCl would have reacted with aluminium as well, and it would have formed AlCl3 with this H2 gas also. If I balance this reaction also, this has to be 3 times and this has to be 3 by 2 times. So basically the HCl which we are adding in the container, some part of it is reacting with magnesium, some part of it is reacting with aluminium. So how many reactions are taking place? 2 reactions are taking place. 2 reactions are taking place, right? From reaction number 1, as you can see, H2 gas is produced. From reaction number 2, as you can see, H2 gas is produced. So H2 gas is produced from this reaction as well as this reaction. As per the question, how many total moles of H2 gas are produced? These are the total moles of H2 gas produced. Can I say these total moles of H2 gas which are being produced? Can I say some moles of H2 gas would be produced from this reaction? Some moles of H2 gas would be produced from this reaction. And I would say moles of H2 produced from reaction number 1 plus moles of H2 produced from reaction number 2 has to be equal to the total moles of H2 produced. That has to be the concept. Right? I can write it over here. I can write moles of H2 produced from reaction number 1 plus moles of H2 produced from reaction number 2 has to be equal to total moles of H2 produced as per the question. Total moles of H2 produced as per the question. So first of all, we need to know how many moles of H2 are being produced from reaction number 1 and how many moles of H2 are being produced from reaction number 2. Let's get to know. Let's use stoichiometry now. See, stoichiometry coefficient here is 1. Here also it is 1. As per stoichiometry, can I say 1 mole magnesium, when reacts with HCl, at that point of time, 1 mole H2 will be getting formed. 1 mole H2 will be produced. Right? As far as stoichiometry is concerned, when 1 mole magnesium reacts with HCl, it leads to the formation of 1 mole of H2 gas. But in the container, did we have 1 mole of magnesium to react with HCl? No. We had X by 24 moles of magnesium in the container, which would have reacted with HCl. Right? So I would say, since 1 mole of magnesium when reacts with HCl, that leads to the formation of 1 mole of H2 as per stoichiometry. Therefore, when X by 24 moles of magnesium, which were present in the container, when these many moles of magnesium would have reacted with HCl, I would say X by 24 moles of H2 would have got produced. So these are the moles of H2 which are being produced from reaction number 1. Similarly, how many moles of H2 are being produced from reaction number 2? Have a look. Stoichiometry coefficient here is 1, here it is 3 by 2. I'll say as per stoichiometry, I got to know when 1 mole of aluminium reacts with HCl, it leads to the formation of 3 by 2 moles of H2 gas. But in the container, did we have 1 mole of aluminium to react with HCl? No, we had 1 minus X by 27 moles. So I would say when 1 minus X divided by 27 moles of aluminium would have reacted with HCl, it would have formed 3 by 2 multiplied by 1 minus X by 27 moles of H2. I hope this particular statement is clear, right? So I got to know the moles of H2 gas which are being produced from reaction number 1 as well as reaction number 2. So I got one equation. Equation is simple. Moles of H2 produced from reaction number 1 plus moles of H2 produced from reaction number 2, it has to be equal to the total moles of H2 produced. So how many moles of H2 are produced from reaction number 1? It is X by 24. How many moles of H2 are produced from reaction number 2? It is 3 by 2 multiplied by 1 minus X divided by 27. And this has to be equal. How many total moles of H2 are produced as per the question? It is 1.12 divided by 22.4. One equation which just contains one unknown, that's X. When you solve this equation, you'll be getting the value of X over here, right? And what is X? X was the mass of magnesium in the container. If you got X, you can easily get this 1 minus X as well, which will give you the mass of aluminium in the container. And those were the two things which we were supposed to calculate. Am I clear with this? Am I clear with this? Now guys, it is just the matter of calculation here. It is just the matter of calculation here. By solving this particular equation, you can get X. X means mass of magnesium in the container, right? And similarly, 1 minus X means mass of aluminium in the container. That is something which you were supposed to calculate. You were supposed to check the composition of the alloy. You were supposed to check in this mixture how many grams of magnesium are there, how many grams of aluminium are there. That's how you got it. All clear? Say yes or no in the chats quick. Say yes or no in the chats quick. Everybody. Everybody, people. Everybody. Perfect. All right. Wonderful. So let me move on to one more question, which will make your concepts a bit more clear. Okay. Look at this question, guys. Similar type of question. 1.67 grams of a mixture of aluminum and zinc reacted with HCl and liberated 1.69 liters of H2 gas at STP. Calculate the mass of aluminum and zinc in the mixture. You're going to solve this question in the similar way. See how. For example, this is the container. In this particular container, we have got aluminum and zinc. We have got zinc and aluminum in the container. What is the mass of the entire mixture? The mass of the entire mixture is 1.67 grams. Mass of this entire mixture is 1.67 grams. So, if I ask you, is this 1.67 grams only the mass of zinc? No, this is the mass of entire mixture. The first thing which I'll be assuming, let me assume the mass of aluminum in the mixture as X grams. Therefore, mass of zinc in the mixture will be 1.67 minus X grams. Correct? Right, people? Simple. Now, as per the question, okay, leave the question aside. First of all, tell me, how many moles of zinc are there in the container? It is going to be mass of zinc divided by molar mass of zinc. So these are the moles of zinc in the container. How many moles of aluminum are there in the container? Mass of aluminum divided by molar mass of aluminum. So these are the moles of zinc and aluminum in the container. Now, the question is saying, in this container, we are adding HCl. In this container, what are we adding? We are adding HCl, right? When HCl is added into the container, what is happening? H2 gas is produced. How many liters of H2 are being produced? 1.69 liters of H2 are produced when HCl is added in the container. So can you first of all tell me how many moles of H2 would have got produced as per the question? Number of moles of H2 produced will be equal to 1.69 divided by 22.4. So these are basically the total moles of H2 which are produced as per the question. Right? These are the total moles of H2 produced when HCl is added into the container. And as per the question, these are the total moles of H2 produced. Now think, guys, think properly. When HCl would be added into the container, can I say some part of HCl would have reacted with zinc and some part of HCl would have reacted with aluminium? So how many reactions would have happened? 2 reactions would have happened, right? 2 reactions would have happened. Perfect. So what are those reactions? First of all, when zinc reacts with HCl, what do we get? I've given you already this reaction. We get ZnCl2 plus H2 gas. This is the reaction number 1. Reaction number 2, when HCl reacts with aluminium, it leads to the formation of AlCl3, and with that you get H2 gas. With that you get H2 gas, right? So these are the 2 reactions which would have happened. Right? Perfect. Now, my dear students, first thing, how many total moles of H2 are being produced? These are the total moles of H2 produced. Can I say some part of H2, some moles of H2 would have got produced from this reaction and some moles of H2 would be produced from this reaction, right? So first of all, let's get to know how many moles of H2 are produced from here. And then let's get to know how many moles of H2 are produced from here. How do we get that? We'll be getting that with the help of stoichiometry. We'll be getting that with the help of stoichiometry. So understand, coefficient here is 1, here also it is 1. So as per stoichiometry, we know when 1 mole zinc reacts with HCl, 1 mole H2 is produced. When 1 mole zinc reacts with HCl, 1 mole H2 is produced. But as per the question is concerned, did we have 1 mole of zinc in the container to react with HCl? No, we had 1.67 minus X divided by 65. These were the moles of zinc which were there in the container, which would have reacted with HCl. So when 1 mole reacts with HCl, it leads to the formation of 1 mole of H2. When these many moles of zinc would have reacted with HCl, they would have formed 1.67 minus X divided by 65 moles of H2. Perfect. So these are the moles of H2 which are being produced from reaction number 1. Similarly, how many moles of H2 would have been produced from reaction number 2? Check it out. Stoichiometric coefficient here is 1. Here it is 3 by 2. So this reaction is telling us that 1 mole aluminium, when reacts with HCl, it forms 3 by 2 moles of H2. 3 by 2 moles of H2 are produced. But as per the given scenario, did we have 1 mole of aluminium in the container to react with HCl? No. We just had X by 27 moles of aluminium in the container, which would have reacted with HCl, and they would have led to the formation of 3 by 2 multiplied by X by 27 moles of H2 gas. So, do you understand what all things I calculated? Do you understand what all things I calculated? My dear students, if you look carefully, we got the moles of H2 produced from reaction number 1. We got the moles of H2 produced from reaction number 2. And as per the question, these are the total moles of H2 produced, right? So I'll be using the concept again. Moles of H2 produced from reaction number 1 plus moles of H2 produced from reaction number 2 has to be equal to total moles of H2 produced, right? Has to be equal to total moles of H2 produced. So here I'll be getting one equation and we are done. So it's going to be moles of H2 produced from reaction number 1. It's 1.67 minus X divided by 65 plus it's going to be 3 by 2 multiplied by X by 27, and this is equal to total moles of H2 produced, that is 1.69 divided by 22.4. Do you see this equation? One equation which just contains one unknown. Unknown is X. You just need to solve this equation, get the value of X. And this X is going to give you the mass of aluminium in the mixture. Once you get X, 1.67 minus X is going to give you the mass of zinc in the container, which is something I was supposed to calculate, right? Is this clear, people? Is this clear? Is it clear to everyone? Did you understand the concept here? Did you understand the concept here? Let's solve one more. Let's solve one more question of the similar format. This is your one more question, people. This is your one more question. This is your one more question. On heating 2 grams of a mixture of sodium carbonate and sodium bicarbonate, 0.11 grams of carbon dioxide is produced. What is the composition of the mixture? What is the composition of the mixture? Understand. See, first thing, imagine this is the container which you have taken, and in this container you have kept two things. One is your sodium bicarbonate, NaHCO3, and one is your sodium carbonate, Na2CO3. What is the mass of this entire mixture? As per the question, it is 2 grams. 2 grams is the mass of this entire mixture, right? Now, people, look at the question carefully. The question is saying, we are heating this mixture. We are heating this mixture. When we heat this mixture, what is happening? As per the question, 0.11 grams of carbon dioxide gas is produced. When we are heating this mixture, 0.11 grams of carbon dioxide is produced, right? So if I ask you, what do you think? How many moles of carbon dioxide are produced as per the question? Mass of carbon dioxide produced divided by molar mass of carbon dioxide. So these are basically the total moles of carbon dioxide which are produced as per the question. When you are heating this mixture, carbon dioxide is produced as per the question. So how many total moles of carbon dioxide are produced? Total moles of carbon dioxide produced are 0.11 divided by 44, right? Now guys, understand one thing. Let's assume out of 2 grams of the mixture, the mass of a sodium bicarbonate is x grams in the container. Therefore, it has to be 2 minus x grams. This has to be 2 minus x grams. So if I ask you how many moles of bicarbonate are in the container, you will say mass of bicarbonate divided by molar mass of bicarbonate. Similarly, mass of carbonate divided by molar mass of carbonate, right? So these are the moles of sodium bicarbonate and sodium carbonate present in the container. Now guys, think logically. Something which I told you when I started stoichiometry. If you remember, I told you, see, since you are heating this mixture, when you are heating this mixture, this will be heated up, this will be also heated up. When sodium bicarbonate gets heated up, what does it form? It forms Na2CO3. With this, you'll be getting water, and with water, you'll be getting carbon dioxide. But if you remember, I have told you, when Na2CO3 is heated, does anything happen? Nothing happens here. How many reactions will be happening in the container? When you will be heating this mixture up, how many reactions will be happening in the container? 2 or 1? Just 1 reaction will be happening, right? So can I say whatever carbon dioxide is produced as per the question, that entire carbon dioxide will be coming from this reaction? Yeah? That entire carbon dioxide will be coming from first reaction. Perfect. So my concept here will be pretty much simple. I'll write number of moles of carbon dioxide produced from bicarbonate, NaHCO3, will be equal to total moles of carbon dioxide produced. This will be my concept. Now let's get to know through this particular reaction how many moles of carbon dioxide are being produced. See guys, stoichiometric coefficient here is 2, here it's 1. Can I say, as per the stoichiometry, 2 mole bicarbonate, when you heat 2 mole bicarbonate, 1 mole carbon dioxide is produced? Yes, this is something which stoichiometry is telling me, right? Therefore, when 1 mole bicarbonate will be heated up, 1 by 2 moles of carbon dioxide would be produced. But as per the question, was there 1 mole of bicarbonate in the container? No, there was x by 84 moles of bicarbonate in the container which would have got heated up, right? So I would say x by 84 moles of bicarbonate when heated will be producing 1 by 2 multiplied by x by 84 moles of carbon dioxide, right? So this is what I'll be calling as the moles of carbon dioxide produced from bicarbonate, right? So my concept now is clear. Moles of carbon dioxide produced from bicarbonate, that is x divided by 2 multiplied by 84. This has to be equal to total moles of carbon dioxide produced, which is 0.11 divided by 44. Now, if you solve this particular equation, you'll be easily getting the value of x. And what is x? X was basically the mass of bicarbonate in the container, which you were supposed to calculate. And once you get x, you can easily get 2 minus x as well. You can easily get mass of carbonate in the container as well, right? I believe this is clear. I believe this is clear. Right, people? Will you be able to solve this sort of a question? Will you be able to solve this sort of equation? If it comes. So here only one concept was involved. When you heat up the mixture, only bicarbonate is going to dissociate, is going to break, right? Carbonate is not going to break here. So only one reaction will happen. I hope I'm clear with this. Let's try to solve one more. Let's try to solve one more. See guys, look at this particular question. A gaseous mixture of propane and butane of volume 3 liters on complete combustion produces 10 liters carbon dioxide. Calculate the volume of propane and butane in the mixture. Understand? This is again one simple question. So basically, you have taken a container. In this container, we have got propane. Propane is your C3H8 and there is butane in the container as well, C4H10. Propane and butane is there in the container, right? So what is the total volume of this particular mixture? Volume of this mixture is 3 liters. 3 liter is volume of this entire mixture, right? So first of all, out of 3 liters, let's assume that. Let's assume there are some X liters of butane in the container. Therefore, this will be 3 minus X liters. Perfect. So what is the volume of butane in the mixture? X liters. What is the volume of propane in the mixture? 3 minus X liters. Correct? Now guys, understand. Understand properly. As per the question, this mixture is undergoing combustion. This mixture is undergoing combustion. What does that mean? That means imagine that you are adding O2 here, right? You are adding O2 here. Now the O2 which you are adding, it would have reacted with this one as well as this one. Perfect. It would have reacted with this one as well as this one. Correct, people? Right? Now, when O2 will be reacting with both of them, so the mixture will be undergoing combustion basically. And when the mixture is undergoing combustion, as per the question, how many liters of carbon dioxide are produced? As per the question, 10 liters of carbon dioxide are produced. When this mixture is undergoing combustion, 10 liter carbon dioxide is getting produced. Right? Guys, think logically. When you will be adding O2 in the container, can I say that O2 will be reacting with this one as well as this one? So how many reactions will be taking place? 2 reactions. 2 reactions. Right? 2 reactions. The first reaction is going to be C3H8 will be reacting with O2 and it will be leading to the formation of carbon dioxide, and with carbon dioxide you'll be getting water. In the similar way, your butane C4H10, it will be also reacting with O2, it will be also leading to the formation of carbon dioxide and water. And I hope you remember how I've shown you how do we balance these sort of reactions. If this is 3, this has to be 3 as well. If this is 8, this has to be 4. This has to be x plus y by 4. That comes out to be 5. If this is 4, this has to be 4. If this is 10, this has to be 5. This has to be x plus y by 4. So it has to be 13 by 2. So these are the balanced reactions now. Now use simple stoichiometry. Now how you are going to use stoichiometry here? Understand one thing. See, till now I did not use volume method anywhere. I showed you mole method, I showed you mass method, I showed you POEC. I did not show you volume method yet. See how volume method is used. Understand. Here the stoichiometric coefficient is 1. Here the stoichiometric coefficient is 3. My dear students, as per the question, when this mixture is undergoing combustion, this much volume of carbon dioxide is produced. Now, when this mixture is undergoing combustion, how many reactions are happening? 2 reactions. From reaction number 1, carbon dioxide is produced. From reaction number 2, carbon dioxide is produced. Let's get to know what volume of carbon dioxide is produced from this reaction as well as this reaction. Okay, understand. I can say, as per stoichiometry, when 1 liter propane undergoes combustion, 3 liter carbon dioxide is produced. Right? But in the container, was there 1 liter of propane for the combustion? No. There were 3 minus x liters. 3 minus x liters of propane were there in the container, which would have undergone combustion. 1 liter of propane, when undergoes combustion, 3 liter carbon dioxide is produced. Therefore, when these many liters of propane undergoes combustion, how many liters of carbon dioxide will be produced? 3 multiplied by 3 minus x liters of carbon dioxide would be produced, right? So, I would say this is the volume of carbon dioxide produced from reaction number 1. Similarly, from this particular reaction also some carbon dioxide would be produced. Say, coefficient here is 1, here it is 4. I'll say when 1 liter butane undergoes combustion, as per stoichiometry, 4 liter carbon dioxide is produced. But in the container, did we have 1 liter of butane which would have undergone combustion? No, there were x liters of butane. So when x liter butane would have undergone combustion, right? How many liters of carbon dioxide would have produced? 4x liters of carbon dioxide would have got produced. So this is the volume of carbon dioxide produced from second reaction. Correct? What is the concept? What is the concept which I'll be using? My dear students, concept is going to be simple. See, as per the question, when this mixture is undergoing combustion, this much total volume of carbon dioxide is being produced. Out of this total volume, some volume would be produced from this reaction, some volume of carbon dioxide would be produced from this reaction. So I'll be using a simple concept. Concept is volume of carbon dioxide produced from reaction number 1, which is 3 multiplied by 3 minus x, plus volume of carbon dioxide produced from reaction number 2, which is 4x, has to be equal to total volume of carbon dioxide produced, that is 10 liters. Right? Perfect. So people, this comes out to be 9 minus 3x plus 4x is equal to 10. So here you got the x as 1 liter. X is equal to 1 liter. What was x? X was the volume of butane in the mixture. If volume of butane in the mixture is x, therefore volume of propane in the mixture has to be 3 minus 1. That comes out to be 2 liters. These were the two things which I was supposed to calculate as far as the question is concerned. Right? All clear? All clear, people? All clear? Did you understand it properly? Perfect. Let's move on. Let's move on. See guys, this is one more question and let's try to give it a try as well. Let's see how this sort of a question is to be solved. It's a similar type of question. Completely similar type of question, right? So basically you have got a container. In the container you have got NO and N2. You have got NO and N2O in the container. See, the total volume of the mixture is given to me as 60 ml. Total volume of the mixture is given to me as 60 ml. Now, in this container, we are introducing H2 gas. In this container, we are introducing H2 gas. As per the question, when you are introducing H2 gas in the container, 38 ml of N2 is formed. Volume of N2 formed is equal to 38 ml as per the question. Volume of N2 formed is equal to 38 ml as per the question. Okay. We have to calculate what is the volume of NO and N2O in the container. My dear students, again in the similar way we are going to solve this. See, this is the volume of entire mixture. Let's assume there are x ml of NO in the container. So this has to be 60 minus x ml. This has to be 60 minus x ml. Now, H2 gas is introduced here. When H2 gas will be introduced here in the container, some part of H2 would have reacted with this and some part of H2 would have reacted with this. So how many reactions would have taken place? 2 reactions. 2 reactions would have taken place. First reaction would be NO plus H2. It would have formed N2 plus water. N2 plus water. N2 plus water. Similarly, second reaction would have been N2O. When it would have reacted with H2, it would have led to the formation of N2 plus H2. So these would be the 2 reactions taking place when H2 will be introduced in this container. Okay. If you think logically, through reaction number 1, N2 gas is produced. Through reaction number 2, again N2 gas is produced. As per the question, total volume of N2 produces 38 ml. Can I say out of this 38 ml, some ml of N2 would be produced from here and some ml of N2 would be produced from here? Let's get to know how many milliliters of N2 are produced from here and then from here. Okay. So use the stoichiometry again. Coefficient here is 1. Here it's 1 by 2. Stoichiometry is telling me that 1 ml NO upon reaction with H2 reduces 1 by 2 ml of N2. Reduces 1 by 2 ml of N2. But as per the question, was there 1 ml of NO in the container? No, there were x ml. So when x ml NO would have reacted with H2, it would have formed x by 2 ml of N2. So this is the volume of N2 produced from reaction number 1. Similarly, use the stoichiometry here in the second one. Coefficient here is 1. Here also it's 1. So I'll say as per stoichiometry, 1 ml N2O upon reaction with H2 leads to the formation of 1 ml of N2. But in the container, was there 1 ml of N2O to react with H2? No, there was 60 minus X. So 60 minus X ml of N2O when reacts with H2 would have formed 60 minus X ml of N2. So this is the volume of N2 which is produced from reaction number 2. This is the volume of N2 which is produced from reaction number 2. So what is the concept which I'll be using here? Concept is going to be simple. See, when this mixture is, when H2 gas is introduced in this mixture, total volume of N2 produces 38 ml. And later on we realized, out of this 38 ml, some ml of N2 are produced from here, some ml of N2 are produced from here. So I can use the concept volume of N2 produced from reaction number 1, that is X by 2, plus volume of N2 produced from reaction number 2, that is 60 minus X, has to be equal. Total volume of N2 produced, that is 38, right? So X by 2 minus X is minus X by 2 is equal. This will be how much? Minus 22. So X over here comes out to be 44 ml. X over here came out to be 44 ml. What was this X exactly? This X was volume of NO in the mixture. If you got volume of NO in the mixture, volume of N2O, you can easily calculate 60 minus X, 60 minus 44, that comes out to be 16, right? I believe you can easily solve all the questions based on the mixture analysis from now on. If yes, let me know once in the chats. If yes, let me know once in the chats. Quick. Quickly, people. Everybody. Quickly, people. Everybody. Perfect. All clear? Someone is saying why I did not do mole method here. Because then you will have to convert all these volumes into moles. It would be, I mean, right? The calculation is going to be difficult. The calculation is going to be difficult otherwise. Perfect, guys? Now, so with this, I believe your mixture analysis topic is properly clear, right? So let's move on to a few more topics which are left, out of which one is your limiting reagent. Okay? Have you done limiting reagent ever? Do you know what is a limiting reagent? Let me have some water. Till then. Limiting reagent. Have you studied this topic ever? Someone has come. Take Academy. How much money you got? Mr. Rehan, how much money you got? You have called me, I would have given you more. Perfect. Exactly. All these spammers, they come, they keep on coming. They'll never qualify any sort of competitive examination, but they would love to spam, etc., etc. Come here, go to this platform, that platform. They have got just this work, like they do it in a decent mode, right? And when they go into the examination, there also they sit decently. In the decent manner, they sit in the examination hall. right? Without, I mean, shaking their hands. Yeah, these are people, they do keep on coming. Okay, let's move on to this particular topic now. Limiting reagent. Next chapter is going to be redox. Okay, I'll follow the same sequence. Redox is going to be the next. Perfect, guys. So let's move on and let's complete this particular topic as well. So what is basically a limiting reagent? How do we define the limiting reagent? Understand. See, guys, limiting reagent is defined as the reactant. It is defined as the reactant that gets completely consumed. That gets completely consumed earlier in the reaction. Okay? That reactant which gets completely consumed earlier in the reaction, you call that as the limiting reagent. You call that as the limiting reagent. And the other one is called as excess reagent, or you call it as excessive reagent. Other one is called as the excessive reagent. Point number 2. Point number 3, entire product formation. Entire product formation is decided by the limiting reagent. Entire product formation is decided by what? Entire product formation, it's decided by the limiting reagent. How exactly all of this happens? What is the limiting reagent? What kind of concepts do we need to understand over here? Let's try to analyze all the things one on one, right? Let's try to analyze all the things one on one. My dear students, for example, imagine you have got the reaction like this. A plus B, it gives C plus D. First of all, this particular reaction would be taking place in a container. You know it, right? All the reactions, they take place in the vessels, in the containers. If I write time t is equal to 0, at time t is equal to 0, time t is equal to 0 means reaction has not started yet. If the reaction has not started yet, there will be only reactants in the container. Initially at time t is equal to 0, when reaction has not started, there will be only a reactant in the container. Let's assume there are some 10 moles of A and 5 moles of B in the container. Initially at time t is equal to 0, when the reaction has not started. And if the reaction has not started, that means the products, they have not got formed yet, because the reaction has not started yet. Reaction has not started yet. My dear students, as the reaction starts, what happens? I would say the number of moles of reactants, they keep on decreasing. As the reaction starts, number of moles of reactants, they keep on decreasing. Why? Because when the reaction starts, these moles of reactants, they keep on reacting and start getting converted into products. Therefore, I would say, as the reaction starts, moles of reactants, they keep on decreasing. Can I say, out of these two reactants, there will be one reactant which would be consumed completely earlier in the reaction? Right? As the reaction starts, moles of reactants keeps on decreasing, right? Moles of reactants, both the reactants will keep on decreasing. Among these two reactions, there will be one reactant that would have got completely consumed earlier in the reaction. And that reactant is something which we call as limiting reagent. Let's assume this B is the limiting reagent. So if B is the limiting reagent, it would be completely consumed earlier in the reaction. So after some time, you will observe out of 5 moles, there will be 0 moles of B left in the container, right? And that reactant which gets completely consumed earlier in the reaction, that's your limiting reagent. Other one is called as your excessive reagent. Excessive reagent does not get completely consumed. It does not get completely consumed. So I would say when one of the reactant is completely consumed, at that point of time, other reactant, there will be some of the moles of other reactant left in the container. And at the same time, there would be some moles of product which would have got formed in the container as well. And at this point of time, the reaction would have stopped. Why? Because no doubt there are some moles of A left in the container, but there is no B left. But there is no B left. If there is no B left, this A which is left in the container, right? It has got no B present over here to react with. So the reaction would have stopped. Perfect. The reaction would have stopped. The entire product formation as well as how much excess reactant is left, all this stuff is decided by what? Is decided by limiting reagent. Limiting reagent is going to decide every single thing. Limiting reagent is going to decide every single thing. Okay? Limiting reagent is going to decide how much product got formed. Limiting reagent is going to decide at the end of the reaction, when the reaction has stopped, how much excess reagent is left. Every single thing limiting reagent is going to decide. Let's try to understand. Let's try to understand all this in the form of a question. See guys. For example, imagine like this. Imagine. Let's say you have got the reaction like this, N2 plus H2. It gives NH3. It gives NH3. For example, I'm starting with 10 moles each of reactants. Imagine that I'm starting with 10 moles each of reactants. So at time t is equal to 0, I've got 10 moles of this, 10 moles of this. And I'm assuming, since I'm talking at time t is equal to 0, that means the reaction has not started. If the reaction has not started, moles of NH3 formed right now would be 0 because the reaction has not started yet. Okay? Right? Now, my dear students, remember one thing. Remember one thing. Whenever in a reaction, the amounts of all the reactants would be given to you. Whenever in a chemical reaction, amounts of all the reactants would be given to you. Like over here in this question, amounts of reactants are given in terms of moles. Well, these amounts can be given in terms of moles, it can be given in terms of mass, it can be given in terms of volume, it can be given in terms of particles. Whenever in a chemical reaction, amounts of all the reactants will be given to you. At that point of time, you'll be using the concept of limiting reagent. So when do you use the concept of limiting reagent? Concept of limiting reagent is used when the amounts of all the reactants in the reaction would be given to you, right? And these amounts can be in terms of moles, mass, volume, particles, etc., etc. Okay? Since you got to know that you'll be using limiting reagent concept here. Now, what is the first step which we do in the limiting reagent concept? The first step is to balance the reaction. First step is to balance the reaction. So, balance this particular reaction first. When you balance the reaction, this becomes 3 times, this becomes 2 times, and this becomes once. Okay, you have balanced the reaction. After balancing the reaction, you are going to identify your limiting reagent. After balancing the reaction, you are going to identify your limiting reagent. How do we identify the limiting reagent? How do we identify the limiting reagent? What exactly will be doing? We will be dividing the given moles of reactants with their respect to stoichiometric coefficients. See, 10 divided by stoichiometric coefficient 1. 10 divided by its stoichiometric coefficient is 3. This value comes out to be 10. This value comes out to be 3.33. Which value comes out to be lesser? 10 or 3.33? This value is lesser. So, for H2 values coming out to be lesser, the one that gets the lesser value, that's always your limiting reagent. So, this is your limiting reagent. That means this automatically becomes your excessive reagent. Right? First step, guys. Balance the reaction. Second, identify the limiting reagent. How you are going to identify? Divide the given moles of reactants by their respective stoichiometric coefficients. The one that gets the smaller value, that's always your limiting reagent. Remember this in short. So, my H2 is the limiting reagent. If H2 is the limiting reagent, it would have got completely consumed in the reaction, right? You had taken 10 moles. After some time, you will find 0 moles of H2 left in the container, right? And when H2 would have got completely consumed, I would say reaction would have stopped at that point of time, right? Now, when reaction has stopped, I would say some moles of NH3 would have got formed, as well as some moles of N2 would be still left in the container. No doubt, H2 got completely consumed. But out of 10 moles of N2, some moles of N2 would be still left in the container, and at the same time, some moles of NH3 would have got formed. Now, how do we exactly calculate the amount of product formed? How do we exactly calculate the amount of excess reagent left? Everything, my dear students, is decided by the limiting reagent. Limiting reagent is going to decide every single thing, right? Limiting reagent is going to decide every single thing. How exactly? Say, for example, I need to know how many moles of NH3 got formed. I need to know how many moles of NH3 got formed at the end of the reaction. Who is going to decide that? Who is going to tell us about that? Limiting reagent, right? So what we need to do, I'll be relating stoichiometry of limiting reagent with NH3. See guys, stoichiometry is telling me that 3 moles of H2 reduces 2 moles of NH3. Stoichiometry is telling me 3 moles of H2 reduces what? Reduces 2 moles of NH3. Okay, this is stoichiometry, which is telling me something like this. 3 moles of H2 produces 2 moles of NH3. Therefore, I would say 1 mole of H2 would be producing 2 by 3 moles of NH3. But did we have 1 mole of H2 in the container? No, we had taken 10 moles. So I would say 10 moles of H2 would have produced 2 by 3 multiplied by 10. The value comes out to be 6.66 moles of NH3. So I got to know at the end of the reaction 6.66 moles of NH3. 6.66 moles of NH3 would have got formed at the end of the reaction. Number 1. Number 2. If they ask you how many moles of N2 will be left in the container at the end, how many moles of N2 would be left in the container? See, how many moles of N2 you took in the beginning? 10. Out of 10, some moles would have reacted, right? So first of all, it is high time to get to know out of 10 moles of N2, how many moles have reacted. Who is going to tell you about that? Again, limiting reagent is going to tell you out of 10 moles of N2, how many moles have reacted, right? Limiting reagent is going to tell you that. How exactly? See, relate the stoichiometry of limiting reagent with this excess reagent. I can say 3 moles react with 1 mole. I can say 3 moles of limiting reagent. 3 moles of limiting reagent as per stoichiometry reacts with 1 mole of N2. This is something which stoichiometry is telling me. Therefore, I would say 1 mole H2 would have reacted with 1 by 3 moles of N2. 1 mole H2 would have reacted with 1 by 3 moles of N2. Therefore, 10 moles of H2, would have reacted with 1 by 3 into 10, which comes out to be 3.33 moles of N2. So I got to know 10 moles of H2, would have reacted with 3.33 moles of N2. How many I had taken? I had taken 10. Out of 10, how many are reacting? 3.33. So how many will be left? 10 minus 3.33. The value comes out to be 6.66. So these are the moles of N2 left in the container at the end of the reaction. Did you understand? Did you understand this? So my dear students, you got the moles of product formed, you got the moles of excess reagent left, right? Now it's not necessary they'll ask you about the moles only. They can ask you what volume of NH3 is formed at STP. Since you got the moles, you know how to convert moles into volume. Moles multiplied by 22.4 liters. If they ask you, my dear students, what mass of NH3 is formed? You got the moles multiplied by its molar mass. You'll be getting the mass of NH3 formed. If they ask you how many molecules of NH3 got formed, you got moles. Moles multiplied by Avogadro's number gives you the molecules. Simple. If they ask you what volume of N2 is left, you got moles of N2 left multiplied by 22.4 liters at STP. If they ask you how many molecules of N2 are left, you got the moles of N2 left multiplied with Avogadro's number. You'll be getting the molecules of N2 left, and so on, right? So it's not necessary they'll ask you about the moles only. They can ask you about mass, they can ask you about volume, they can ask you about particles, everything, right? I believe this is clear. Okay, tell me the answer of this question. Simple and basic question. 3 moles of NaOH, 3 moles of NaOH reacts with 4 moles of H2SO4, right? Find the limiting reagent. How do you identify the limiting reagent? Given moles divided by stoichiometric coefficient. Given moles divided by stoichiometric coefficient gives us what? Given moles divided by stoichiometric coefficient. 3 by 2, that's 1.5. 4 by 1, that's 4. Which one gets the lesser value? NaOH. So NaOH is my limiting reagent. Perfect. NaOH is my limiting reagent. Look at this question. A reaction is given to us already in the balanced format. 6 times LiH plus 8 times BF3. 8 times BF3, it gives 6 times LiBF4 plus B2H6. This is the reaction that's given to us. Now, as per the question, on starting with 2 moles each of reactants. On starting with 2 moles each of reactants. So, initially, we are starting with 2 moles each of reactants. How many moles of B2H6 would be formed? So, at the end of the reaction, how many moles of B2H6 would be formed? First of all, look carefully. We are given with the amounts of all the reactants. Whenever we are given with the amounts of all the reactants, we'll be using the concept of limiting reagent, right? And in the limiting reagent concept, what do we need to do? We need to balance the reaction first. The reaction is already balanced. After balancing the reaction, it's high time to identify the limiting reagent. How do you identify? Given moles by the respective stoichiometric coefficients. So 2 divided by 6, 2 divided by 8. Which value is lesser? 2 by 8 is lesser. So this is my limiting reagent. If BF3 is my limiting reagent, so I would say out of 2 moles of BF3, 0 will be left at the end. And at that point of time, the reaction would be stopped. Now, entire product formation is decided by the limiting reagent. How exactly? Have a look. What do I need to calculate? How many moles of B2H6 have got formed? Stoichiometric coefficient here is 8. Here it's 1. I'll say 8 moles of BF3 gives 1 mole of B2H6. 1 mole BF3 gives 1 by 8 moles of B2H6. 2 moles of BF3 gives 1 by 8 into 2. That means 0.25 moles of B2H6. So these are the moles of B2H6 which would have got formed at the end of the reaction. Is it clear? Is it clear, people? Done and dusted? Done and dusted? Let's try to solve one more question. Look at this question. A reaction is given. That too reaction is given in the balanced format. Initially, at time t is equal to 0, we are starting with 10 moles each of. Reactants. So this would be initially 0. This would be initially 0. Correct? Now, what do we have to calculate? We have to calculate how many moles of Ba3PO4 whole twice got formed at the end of the reaction. So my dear students, if you look carefully, again in this reaction, the amounts of all the reactants are given. So which concept? Limiting reagent concept. If it is the limiting reagent concept, first we need to balance the reaction. The reaction is already balanced. Now we need to identify the limiting reagent. How? Divide the given moles by the respective stoichiometric coefficients. 10 by 3 is 3.33. 10 by 2 is 5. Which one is getting the lesser value? This one is getting the lesser value. So this is my limiting reagent. It would have got completely consumed. So out of 10 moles of BaCl2, nothing will be left. And at that point of time, when this would have got completely consumed, reaction would have stopped. Now, entire product formation, all the things, everything is decided by what? Limiting reagent. So what do we have to calculate? We have to calculate the moles of Ba3PO4 whole twice formed. What do you need to do? Relate the stoichiometry with the stoichiometry of this. I'll say 3 mole BaCl2 gives 1 mole of this. If 3 mole gives 1 mole, I'll say 1 mole will give 1 by 3 moles. 10 moles will give 1 by 3 multiplied by 10. Right? So this comes out to be 3.33 moles. So I got to know 3.33 moles of barium phosphate have got formed at the end of the reaction. Similarly, if they ask you how many moles of NaCl have got formed, now relate the stoichiometry of BaCl2 with NaCl. 3 moles are giving you 6 moles. So 1 mole will give 6 by 3. 6 by 3 is 2. 10 moles will give 2 into 10. That means 20. 20 moles of NaCl would have got formed. Right? Similarly, if this is the excess reagent, this is the excess reagent. If this is the excess reagent, that means out of 10 moles, some moles of Na3PO4 will be left in the container at the end of the reaction. How do we know that? See, 3 moles react with 2 moles. 1 mole reacts with 2 by 3. 10 moles will react with 2 by 3 multiplied by 10, which comes out to be 6.66. I had taken 10. Out of 10, how many are reacting? 6.66. How many will be left? 10 minus 6.66. 3.33 moles of Na3PO4 will be left in the container at the end of the reaction. See, this is the data for the moles. Now you can convert into mass, you can convert this data into molecules, volume, everything, right? Is it clear? Perfect. Perfect, guys. Okay, look at this question. See, I'm giving you the reaction first of all. The reaction is H2SO4 plus 2 times NaOH. Gives what? Gives Na2SO4 plus 2 times water. This is the reaction. As per the question, we are starting with what? We are starting with 160 grams of NaOH and 98 grams of H2SO4. So we are given with masses of reactants. But do we start with masses? Do we start with masses? No. We start with moles. So basically, the first thing which we'll be doing here will be converting these masses into moles. We'll be converting these masses into moles. How do you convert masses into moles? Given mass by molar mass. Given mass is 160, its molar mass is 40. 160 divided by 40 is 4. So basically, we are starting with 4 moles of NaOH. Similarly, its mass is 98, its molar mass is also 98. 98 by 98 is 1. So we are starting with 1 mole of this, 4 moles of this. So this will be 0, this will be 0. Now, which one is the limiting reagent? 1 upon 1, 4 by 2. So this is my limiting reagent. If this is my limiting reagent, so I'll be left with 0. At this point of time, reaction will stop. Now, entire product formation is decided by the limiting reagent. 1 mole gives 1 mole. Over here, I have only 1, right? So 1 mole of Na2SO4 has got formed. 1 mole as per stoichiometry. 1 mole gives 2 moles. I have only 1, right? So 2 moles of water have got formed. Similarly, 1 mole reacts with 2 moles. I have only 1. So 2 moles of NaOH would have reacted. I had taken 4. Out of 4, 2 are reacting. I'll be left with 4 minus 2. That means 2. So 2 moles of NaOH will be left in the container. So these are the moles. If they ask you about the mass, so you got the moles of water formed. Moles multiplied by its molar mass. This will give you, this is the mass of water formed. Similarly, moles multiplied by its molar mass. That gives me the mass of this Na2SO4 formed. Similarly, moles multiplied by its molar mass. Its molar mass is 40, right? So this is the mass of NaOH left in the container. Perfect, right? Similarly, if they ask me how many molecules of water got formed, you got already its moles. Moles multiplied by Avogadro's number. Moles multiplied by Avogadro's number. These are the molecules of water formed. This is the mass of water formed. These are the moles of water formed, right? Similarly, if there was someone as gas, if there was some reactant product as gas, and condition was STP, then moles multiplied by 22.4 liters, that would have given you the volume of the gas. Is this clear? Now, I feel you can solve the questions based on limiting reagent as well. I feel so. Am I right here? Am I right here? Few more topics are left. And we'll be taking almost 2 hours to complete all of them. Yes, 2 more hours, I feel. Guys, all clear till here? All clear till here? Tell me, who are the people spamming? I'll block them right now. Tell me, say it. Or the spammers. Who are the spammers? Tell me. If the brain is not braining anymore, go wash your face once and we'll start. But we have to, complete this chapter. One and a half, 2 hours to complete this chapter. Just 2 hours. 2.5 hours. That's all. Yes, I'll be providing the DPP as well in the Telegram. In the Telegram, yes. What time did we start, guys? What time did we start? We started at 5. 5 or 6? 5. Okay. How many hours am I going to sleep? I'll see if we complete this chapter by 3:30, for example, right? At 7 in the morning, I have one more class. Then there is offline. My God, 8, 9 classes in offline back to back. I'm not going to sleep at all. I don't know how I'm going to how I'm going to take the sessions in offline tomorrow. Five minutes break. This is a break only going on. This is a 5-minute break going on. It's a 5-minute break only going on. This topic I'll be starting in 2-3 minutes. Chit chat break, yes. After redox, it's going to be solution mostly. Of course, number of students they are going to reduce with time for sure. DPP, session PDF, everything I'll be sharing on Telegram, by the way. DPP, session PDF, everything. Hmm. Should we start then? Should we start? No, content I give similar everywhere. Online, offline, whether it's a paid batch, whether it's a free batch on YouTube, everywhere I teach the same. I don't discriminate. No way I can do that. Telegram channel name is Wassim Bhat Chemistry Official. Wassim Bhat Chemistry Official. That is the Telegram channel. And you would have seen, I mean, this much depth of this chapter, you won't find a single session on YouTube. Chalo, let's complete it. See guys, let's talk about one more topic now, that is percentage yield, right? This is again one important topic, right? First of all, I'll give you one formula. I'll give you one formula with the help of which we calculate percentage yield, right? And after that, once I give you the formula for the calculation of percentage yield, then I'll show you some questions wherein we use this concept of percentage yield. Okay? See guys. First of all, the formula is percentage yield is always equal to. Percentage yield is always equal to experimental or the actual amount, experimental or the actual amount divided by expected or theoretical amount multiplied by 100. This is a general result with the help of which we calculate percentage yield of a reaction. Experimental or expected amount divided by expected or theoretical amount multiplied by 100. See guys, what this experimental is, what this expected amount is, right? Let's try to get all this in the form of question directly, right? From the question itself, you'll understand all of this in detail. See guys, for example, look at this particular question. The question is saying, on heating 40 grams of calcium carbonate, 20 grams of calcium oxide was obtained. It is something which is given in the question. On heating 40 grams of calcium carbonate, 20 grams of calcium oxide was produced. Let me tell you, whatever data is given to us in the question, that is all. Whatever data is given to us as per the question, that's all experimentally verified data. So basically, the question is saying, in the laboratory, when you heat up 40 grams of calcium carbonate, you will observe 20 grams of calcium oxide getting produced. So this particular amount, should I be calling it as experimentally observed amount? Yes, it is experimentally observed amount. It is the actual amount. Of calcium oxide which is getting formed in the lab. So in short, whatever data is given to us in the question, that's always experimentally verified. That's always the experimental amount. This is something which has been observed in the lab, that in the lab, when you heat up 40 grams of calcium carbonate, 20 grams of calcium oxide will be produced in the lab. So this is my actual amount. This is my experimental amount. Now, in order to calculate the percentage yield, how many amounts do I need? Experimental, which we already got. Second is expected. How do we get the expected amount? Expected amount we get with the help of stoichiometry. With the help of stoichiometry, we always get the expected amount. How exactly? Have a look. See guys, if I use the mass method, tell me what is the mass of 1 mole of calcium carbonate? It is 100 grams. I'll write 100 grams of calcium carbonate upon heating. What is the mass of 1 mole of calcium oxide? Mass of 1 mole of calcium oxide will be 56 grams. That means it's molar mass, right? Stoichiometry is telling me that, as per stoichiometry, 100 gram calcium carbonate upon heating should produce, I'm using the term should. I'm using stoichiometry. I'm doing some calculations. I'm doing some handwritten calculations, right? After doing these handwritten stoichiometry calculations, I can say something like this. 100 gram calcium carbonate should produce 56 grams of calcium oxide as per stoichiometry. Therefore, 1 gram of calcium carbonate, 1 gram of calcium carbonate should produce 56 divided by 100 grams of calcium oxide. Therefore, 40 grams of calcium carbonate, 40 grams of calcium carbonate should have produced what? 56 divided by 100 multiplied by 40 grams of calcium oxide. And this comes out to be, I think, 22.4 grams. Perfect. So just look at it. What did we calculate? We used some stoichiometry calculations. We used some handwritten calculations and checked that 40 grams of calcium carbonate, 40 grams of calcium carbonate should have produced these many grams of calcium oxide, right? So this is something which I was expecting. This is the amount of calcium oxide which I was expecting to get formed as per stoichiometry. So this is what you'll be calling as expected amount. Now, in order to calculate percentage yield, how many amounts did we need? We needed 2 amounts. Expected, experimental. Experimental is how much? 20 grams. Expected was how much? 22.4 multiplied by 100. So this value comes out to be 89%. So I would say the percentage yield of this reaction is 89%, right? Or you can say efficiency of this reaction is 89%. Efficiency of this reaction is 89%. How much calcium oxide should have got formed as per stoichiometry? These many grams of calcium oxide should have got formed. I would say if the yield of the reaction was 100%, if the yield of the reaction was 100%, at that point of time, whatever you expect calcium oxide to get formed, whatever amount of calcium oxide you expect to get formed, same amount of calcium oxide you get in the lab as well. But when the reaction yield is 100%. Over here, is the yield of reaction 100%? No. Yield of the reaction is 89%. That means whatever amount you expected in the lab, only 89% of this amount, only 89% of this amount would be actually getting formed in the lab. When you solve this, this value will exactly come out to be 20. This value will exactly come out to be 20 only. So you were expecting this much amount of calcium oxide to get formed, but in reality, 89% of this amount is actually getting formed in the lab. I hope this is clear. I hope this is clear. Let me solve one more question. Look at this question carefully. 15.5 grams sample of benzene, 15.6 grams of benzene is mixed with excess of HNO3 and 18 grams of nitrobenzene is produced. Calculate the yield of the reaction. You should be able to solve this one as well. As per the question, it's mentioned, whatever data is given in the question, that's always experimentally verified data, right? And in the question, they're telling you that 15.6 grams of benzene, when treated with HNO3, produces what? Produces 18 grams of nitrobenzene. So this is something which has been observed experimentally. This has been seen in the lab, that 15.6 grams of benzene, when treated with HNO3 in the lab, produced what? Produced 18 grams of nitrobenzene. So this is experimentally verified data. So this is my experimental amount. How many amounts do I need? 2, experimental and expected, right? How do I get the expected amount? Expected amount we get with the help of stoichiometry. Now I'll use the stoichiometry. I'll check how much nitrobenzene should have got formed with the help of stoichiometry. Okay? Now understand. What is the mass of 1 mole benzene? Mass of 1 mole benzene means molar mass of benzene, which is 78 grams. So I'll say 78 grams of benzene. Tell me, what is the mass of 1 mole nitrobenzene? Mass of 1 mole nitrobenzene will be approximately, I think, 123 grams. That means the molar mass of nitrobenzene, right? Perfect. Is it, just tell me in the chats, is it coming out to be 123 only? This is 32. 32 plus 5, 37. 37 plus 14, 51. 51 plus 72. 51 plus 72. Yes, 123 grams. Perfect. So, stoichiometry is telling us that 78 grams of benzene on reaction with HNO3 should have produced 123 grams of nitrobenzene. Therefore, 1 gram benzene, 1 gram benzene, 1 gram benzene on reaction with HNO3 should have produced 123 divided by 78 grams of nitrobenzene. Therefore, I must say 15.6 grams. 15.6 grams of benzene when reacted with HNO3 should have produced 123 divided by 78 multiplied by 15.6. This value, when you solve it, will come out to be 24 grams of what? Nitrobenzene. So this is the mass of nitrobenzene which should have got formed, because we got it with the help of some handwritten stoichiometric calculations, right? Okay. Perfect. So this much mass of nitrobenzene should have got formed from 15.6 grams of benzene. So this is something which I call as expected amount. This was my expected amount of nitrobenzene. I was expecting this much amount of nitrobenzene to get formed. But in reality, how much is being formed? 18 grams. So this experimental, this expected. How do we get the percentage yield here? Percentage yield will be equal. Experimental 18, expected 24 multiplied by 100. This, after solving, comes out to be 75%. So the yield of the reaction is 75%. I believe this is clear. I believe this is clear. Okay. Perfect, guys. Now, look at this particular question. Look at this particular question, guys. 73, 75. Okay, you can check it out afterwards. Look at this particular question. The question is saying, on heating 150 grams of calcium carbonate, on heating 150 grams of calcium carbonate, what mass of calcium oxide will be produced if the yield of the reaction is 75%? What mass of calcium oxide will be getting produced if the yield of the reaction was 75%? Understand, guys. What is the mass of 1 mole of calcium carbonate? 100 grams. So let's use our stoichiometric calculations first. Let's see how much calcium oxide should have got formed, right? What is the mass of 1 mole of calcium oxide? It is 56 grams. Perfect. So can I say something like this? As per stoichiometry, 100 grams of calcium carbonate upon heating should produce 56 grams of calcium oxide. Yes. Therefore, 1 gram calcium carbonate upon heating should produce 56 divided by 100 grams of calcium oxide, right? Therefore, 150 grams of calcium carbonate upon heating should produce 56 divided by 100 multiplied by 150. The value comes out to be 84 grams of calcium oxide. I would say this much calcium oxide should have got produced as per our stoichiometric calculations, right? These many grams of calcium oxide should get produced as per our stoichiometric calculations. But in reality, in a lab, how much calcium oxide would be getting produced? See, the yield of the reaction is 75%. So whatever amount of calcium oxide you expected to get formed, 75% of this amount, 75% of the expected amount will be actually getting formed in the lab. So the actual amount of, I would say the actual amount of calcium oxide which would be getting formed in the lab won't be 84 grams. It won't be 84. It will be 75% of 84. The value comes out to be 63 grams. So in reality, 63 grams of calcium oxide would be getting produced. How much amount of calcium oxide should have got produced? 84 grams. But in reality, how much will be getting produced? 63 grams. Because the yield of the reaction is less than 100. If the yield was equal to 100 at that point of time, whatever amount you expected to get formed, same amount in reality also in the lab you would be getting. If the yield is 100. If the yield is 100. But the yield is less than 100, it is 73. So whatever you expected, 73% of this amount will be actually getting formed. My dear students, one thing over here, which you need to take a note of. One important thing. In this particular question, if you look carefully, we were given with the amount of reactant. We were given with the amount of reactant. And we were supposed to calculate the amount of product. Right? We were supposed to calculate the amount of product. Reactant was given, product was to be calculated. Reactant was given, product was to be calculated. So first what we did, reactant was given, product was to be calculated. First, what did we do? We calculated the expected amount of product. We calculated the expected amount of product and at the end multiplied with percentage yield. At the end multiplied with percentage yield. Now, reverse of it. If you find a question in which product will be given, reactant is to be calculated. Product is given to us, product is given, reactant is to be calculated. So first of all, you will be calculating expected amount of reactant and at the end will be dividing with percentage yield. This is important. This is important. Reactant to product, multiply with percentage yield. Product to reactant, divide with percentage yield. For example, look at this particular question. Look at this particular question. Calculate the mass of calcium carbonate. Calculate the mass of calcium carbonate. Required. Calculate the mass of calcium carbonate required to produce 63 grams of calcium oxide if the yield is 75%. Understand? Whose data I'm supposed to calculate? Am I supposed to calculate the data of reactant or product? I'm supposed to get the data of reactant. So product is given, reactant is to be calculated. Product is given, reactant is to be calculated. Right? So first of all, I'll be calculating expected amount of reactant and at the end we'll be dividing that with percentage yield. Something which I told you a few minutes back. Yeah? Now see guys. What is the mass of 1 mole of calcium oxide? Mass of 1 mole of calcium oxide is how much? 56 grams. So 56 grams of calcium oxide are produced from 100 grams of calcium carbonate, right? Therefore, as per stoichiometry, 1 gram of calcium oxide should be produced from 100 divided by 56 grams of calcium carbonate. Therefore, 63 grams of calcium oxide should be produced from 100 divided by 56 multiplied by 63 grams of calcium carbonate. So this is the expected amount of calcium carbonate. This is the expected amount of reactant, right? Perfect. Now, as per the question, product was given to us, reactant was to be calculated. So first I calculated the expected amount of reactant. Now at the end I'll be dividing this term, right? So actual mass of calcium carbonate needed. Actual mass of calcium carbonate needed will be equal to expected amount, that is 6300 divided by 56 whole divided by percentage yield of the reaction 75%. So divided by 75 by 100. When you solve this, the value comes out to be how much? The value comes out to be how much? 150 grams. Got it? Is this particular question clear, guys? Is this particular question clear? So this is important. This particular point is important. If reactant is given, product is to be calculated. First get the expected amount of product and then multiply with percentage yield, right? If product is given, reactant is to be calculated. First get the expected amount of reactant, then divide with the percentage yield. You'll be getting the actual amount. All clear? All clear with this, people? All clear with this? Let me know once the chats quickly if this is clear, because this particular point was important and I want to know whether this is clear. I want to know whether this is clear. Yes? Perfect. Now see, what if a question is asked like this? What if a question is asked like this? Calculate the mass of HNO3 formed, right? On starting with, let's call it as 44.8 liters of NH3. 44.8 liters of NH3. What mass of HNO3 is formed on starting with 44.8 liters of NH3? If the yield of all these reactions is this much. Okay? So how do we exactly do? How do we exactly do these sort of questions? See guys, first of all, this is the question based on sequential reactions. So first I'll solve the question the same way we did in the sequential part. What is the thing? Convert the given quantity into moles. So number of moles of NH3 will be equal to given volume divided by 22.4. The value is 2. Right? So we are starting with 2 moles of this. Perfect. Now, see, 4 moles are giving us 4 moles. 1 mole gives us 1 moles. So 2 moles of this will give us 2 moles of this as per stoichiometry. So leave this percentage yield aside. I'm not looking at percentage yield yet. Leave the percentage yield aside. See guys, 4 moles are giving 4 moles. 1 mole will give 1 mole. So 2 moles are going to give us 2 moles. So 2 moles of NO are being formed here. So whatever NO is being formed, that NO will be utilized here. Now see, 2 moles are giving us 2 moles. Perfect. 1 mole will be giving us 1 mole. So these 2 moles will be giving us 2 moles only. So basically 2 moles of NO2 are being formed in this reaction. Whatever NO2 is formed, that will be getting consumed here. So 3 moles are giving us 2 moles. 1 will give 2 by 3. 2 will give 2 by 3 multiplied by 2. So 4 by 3 moles of HNO3 should be basically formed at the end of the reaction. 4 by 3 moles of HNO3 should be formed at the end of the reaction. Perfect. 4 by 3 moles of HNO3 should be formed at the end of the reaction. But there is a problem. There is a problem, guys. The yield of all these reactions is not 100. This is the expected amount. This is the expected amount of HNO3 which should have got formed. But in reality, how many moles of HNO3 would be getting formed in reality? The actual moles of HNO3 formed. What you need to do, as I told you earlier, see, reactant was given, product was to be calculated. Reactant is given, product is to be calculated. Calculate the expected amount of product, which is 4 by 3, and then multiply with percentage yield. Percentage yield of this reaction is 0.6, this is 0.7, and this is 0.8. So this will give you the actual moles of HNO3 formed. This will give you the actual moles of HNO3 formed. I hope this is clear. Right? I hope this is clear. Perfect, guys. So in the beginning, I did not do anything with the percentage yields. I just calculated the expected amount of product. And once I get the expected amount of product, what is the next thing after that? Multiply that expected amount of product with the percentage yields. That's all. That's all. Got it? Right? So these are the actual moles of HNO3 formed. Now, are we supposed to calculate moles or mass? We are supposed to calculate mass. Just multiply this particular term with the molar mass of HNO3. Just multiply this particular term with the molar mass of HNO3. You'll be getting the mass of HNO3 formed. Correct? You'll be getting the mass of HNO3 formed. Similarly, guys, there can be one more question based on the percentage yield as well. One more type of question. Look at this particular type. Look at this particular type. Okay? Look at this particular type. As per the question is concerned, 0.4 moles of PCl5 on combining with 1.8 moles of H2O. In the question, they are saying 65.7 grams of HCl is produced. So this is the data which is given to me as per the question. So it has been experimentally observed, experimentally seen that 65.5 grams of HCl are produced. So this is my experimental amount because this has been verified experimentally. Now, what do I need? I need the expected amount. Expected amount I get with the help of stoichiometry. Expected amount I get with the help of stoichiometry. Perfect. Now, let's use the stoichiometry. Say in the beginning, how many moles? 0.4. How many moles of this? 1.8. This will be 0. This will be 0. Which concept I'll be using? Limiting reagent. Now I'll be using some stoichiometric calculations. I'll check how many grams of HCl should have got formed. I'll check how many grams of HCl should have got formed. Right? I'll check how many grams of HCl should have got formed. That is the term I'm using. Perfect. Now, which one is the limiting region among the two? 0.4 by 1 is 0.1. 1.8 divided by 4 is 0.65. So which one is limiting? This is limiting. So this is going to decide everything. Right? Now, 1 mole gives 5 moles. So 0.4 moles are going to give 5 into 0.4 is 2 moles. So I would say 2 moles of HCl should have got formed. 2 moles of HCl should have got formed, right? So, what is the expected mass of HCl? 2 multiplied by its molar mass. So, 73 grams of HCl should have got formed. So, this is my expected amount, which I calculated by doing some certain stoichiometric. This is my expected amount, which I calculated with the help of some stoichiometric calculations. How much actually is getting formed? Actually, 65.7 grams is getting formed. How much should have got formed? 73 grams of HCl should have got formed as per stoichiometric calculations. So, percentage yield will be equal to experimental 65.7 divided by expected 73 multiplied by 100. This is going to give you the percentage yield of the reaction. Am I clear with this? Am I clear with this, people? Say yes or no in the chats if this is clear. Okay. Is this clear? So something that's given to me in the question, that's my experimental amount. Now I did certain stoichiometric calculations, right? Some limiting region concept I used. I calculated how much HCl should have got formed. That's my expected. Experimental divided by expected multiplied by 100. That gives me what? That gives me the percentage yield. Perfect. Now comes your one more topic, that is percentage purity. Okay, percentage purity. So guys, what this percentage purity exactly is all about? Let's try to understand. Okay, after this percentage purity, we'll be taking a break for 10-15 minutes again. But let's cover this percentage purity first, because this is important and this is simple only. It's not difficult or something. See guys, let me directly give you the result to calculate percentage purity. My dear students, or let me write its definition as well. Percentage purity. Percentage purity of a compound in an impure sample. In an impure sample. Percentage purity of a compound in an impure sample. What does it mean basically? What does it mean? It means that percentage purity of a compound in an impure sample, it is defined as that mass of pure compound. That mass of pure compound. In what? In grams. That mass of pure compound in grams, which is present in 100 grams of the impure sample. Which is present in 100 grams of the impure sample. That mass of pure compound, which is present in 100 grams of impure sample. That is something as per the definition which we call as percentage purity of a compound in a sample, in an impure sample. Let's try to understand this in a better way. Imagine this is a container. And for example, in this container, I have kept calcium carbonate. With calcium carbonate, let's say there are some other things as well, A, B, C. With calcium carbonate, for example, there are some other things as well, ABC. And this ABC, my dear students, this ABC I'm calling as impurities. Whatever is there in the container except calcium carbonate, that's something I'm calling as impurities, right? My dear students, assume that the mass of this entire sample, assume that the mass of this whole sample is, for example, 500 grams. So this 500 grams, should I be calling this as the mass of pure calcium carbonate, or should I be calling this as the mass of impure sample? I'll be calling this as the mass of impure sample, right? My dear students, let's assume out of 500 grams of the sample, there are some 50 grams of pure calcium carbonate. There are some 50 grams of pure calcium carbonate present in 500 grams of the sample. In 500 grams of the sample, there are, for example, 50 grams of pure calcium carbonate present. Okay? 50 grams of pure calcium carbonate present. So, my dear students, I can write a simple statement like this. I can say 500 grams of the impure sample, 500 grams of the impure sample contains 50 grams of pure calcium carbonate. Contains 50 grams of pure calcium carbonate. Therefore, I can say 1 gram of impure sample. 1 gram of impure sample contains 50 divided by 500 grams of pure calcium carbonate. Correct? Therefore, 100 grams of impure sample. 100 grams of impure sample contains 50 divided by 500 multiplied by 100 grams of pure calcium carbonate. So if I ask you, what is this particular thing? What did I calculate here? Look carefully. What did I calculate? Can I say this is basically that mass of pure calcium carbonate? That mass of pure calcium carbonate, which is present in 100 grams of impure sample? And as per the definition, that mass of pure compound, which is present in 100 grams of impure sample, what do you call this as? You'll be calling this particular term as percentage purity of what? Percentage purity of calcium carbonate in this impure sample. Did you understand the concept here? What is meant by percentage purity of a compound in a sample? It is simply defined as that mass of pure compound which is present in 100 grams of impure sample. Okay? And that mass of pure compound which is present in 100 grams of impure sample, what do you call this as? You call this as percentage purity of a compound in a sample. Perfect. Now, why did I do all this? Because I wanted to make a result. The result is for the calculation of percentage purity. So let me make a result, a general result over here, which you'll be using in all the questions. Percentage purity of a compound. Percentage purity of a compound in a sample. Well, if you want to make a result, look at this particular box. In the box, there are 3 terms. What was this 50? This 50 was mass of pure calcium carbonate. What was this 500? It was the mass of impure sample multiplied by 100. So in order to make a result, what do we need to do? In order to make a result, I'll be writing it like this. In the numerator, I'll be writing mass of pure compound. Mass of pure compound in grams divided by the mass of impure sample divided by the mass of impure sample in grams multiplied by 100. This is the result with the help of which we can calculate percentage purity of a compound in an impure sample. Okay? This is the result with the help of which we can calculate percentage purity of a compound in an impure sample. For example, you have got a sample of NaCl. So NaCl plus some impurities. Let's say mass of this whole sample is 500 grams. Out of 500 grams, mass of pure NaCl is 10 grams. I want to calculate percentage purity of NaCl in this sample, right? How do I calculate it? Mass of pure NaCl, mass of pure compound divided by mass of impure sample multiplied by 100. This is the simple result which will give me the percentage purity of NaCl in the sample. As simple as that. Okay? So this was the formula. Now, there is one more point for it. What is that? See. My dear students, sometimes in the questions you will find statements like this. If I write 50 grams of 80%, 50 grams of 80% pure calcium carbonate, 50 grams of 80% pure calcium carbonate, what is meant by this particular statement? 50 grams of 80% pure calcium carbonate. What is meant by this statement? Understand. It means that 50 grams of 80% pure calcium carbonate. So you have got a sample of calcium carbonate. You have got a sample of calcium carbonate whose mass is 50 grams. The mass of entire sample of calcium carbonate. That means calcium carbonate plus the impurities. The mass of entire sample is how much? 50 grams. Out of 50 grams, if I ask you how much is the mass of pure calcium carbonate, you should be able to calculate that too. 80% of that 50 is the mass of pure calcium carbonate. So it is going to be 80% of what? 80% of 50. The value comes out to be 40 grams. So in the entire 50 gram sample, 40 grams is the mass of pure calcium carbonate. Right? 40 grams is the mass of pure calcium carbonate. For example, if I write a statement like this, you tell me in the chats, what is meaning of this? 40 grams of 70% pure. 70% pure NaCl. Right? Can you tell me what is the mass of pure NaCl here? What is the mass of pure NaCl here? 40 grams of 70% pure. See, 40 grams of, see, 40 grams is basically the mass of entire sample. So NaCl plus impurities. The mass of entire sample is 40 grams, right? The mass of entire sample is 40 grams. So in that 40 grams of the sample, what is the mass of pure NaCl? 70% of 40. So I would say 28 grams is going to be the mass of pure NaCl. 28 grams is going to be the mass of pure NaCl, right? It's going to be the mass of pure NaCl. And remember a statement, take a note of it. In a chemical reaction, only pure substance participates. In a chemical reaction, only pure substance participates. In a chemical reaction, only pure substance participates. Impurities do not participate in a chemical reaction. In a chemical reaction, it's only going to be the pure substance that's going to participate. Impurities are not going to participate in the reaction. Remember this particular thing. So, let's try to solve a question so that you can understand it properly. See guys, the question is 50 grams of 80% pure calcium carbonate. Do you understand this? 50 grams of 80% pure calcium carbonate. So basically, imagine that you've got a sample containing calcium carbonate with some impurities. What is the mass of whole sample? The mass of entire sample is 50 grams, right? Now, in the 50 grams, how much is the mass of pure calcium carbonate? 80% of 50. 80% of 50 means 80 by 100 into 50. So the mass of pure calcium carbonate is 40 grams. This is something which I analyzed, right? Now, this sample is being heated. When the sample is being heated, what is happening? When the sample is being heated, the pure calcium carbonate in the sample, it will be decomposed. When the sample is being heated, the pure calcium carbonate in the sample, right? That will be getting decomposed into calcium oxide. With that, carbon dioxide gas is produced. Now, as per the question, they're asking you, what volume of carbon dioxide is produced when you heat up this particular sample? What volume of carbon dioxide is produced when you heat up this particular sample? Now, understand. First of all, no doubt you're heating the sample. No doubt you're heating the entire sample. When you are heating the entire sample, the pure calcium carbonate which is there in the sample, that's also being heated. And when pure calcium carbonate heats up, it gets converted into calcium oxide. With that, you get carbon dioxide gas. Perfect. So, if I ask you, how many pure moles of calcium carbonate you are heating? How many pure moles of calcium carbonate you are heating? It's going to be pure mass of calcium carbonate divided by molar mass of calcium carbonate. So, these are the pure moles of calcium carbonate which we are heating. And in a chemical reaction, only a pure substance participates. See guys, stoichiometry coefficient here is 1. Here it's 1. Can I say as per stoichiometry, 1 mole calcium carbonate upon heating produces 1 mole carbon dioxide? Therefore, in the sample, I would say when 0.4 moles of calcium carbonate, would have got heated up, I would say 0.4 moles of carbon dioxide would have got produced. But as per the question, am I supposed to calculate the moles of carbon dioxide produced? No. We are supposed to calculate volume of carbon dioxide produced. So volume of carbon dioxide produced will be equal to moles of carbon dioxide produced multiplied by 22.4. The value is going to be 8.96 liters. So this is the actual volume of carbon dioxide which will be getting produced when we'll be heating up this particular sample. Right? Is it clear? Is it clear, guys? Is it clear? Perfect. Now, let's try to see few more types of questions that can be asked. Look at this question, guys. Look at this particular question. The question is, just a second. The question is 410 grams of limestone. 410 grams of limestone. Limestone means calcium carbonate with some impurities. The question is saying 410 grams of limestone, right? So what is this 410 grams? It is a mass of impure sample of calcium carbonate. Perfect. Now, 410 grams of limestone when treated with oxalic acid. When you introduce oxalic acid here, in this sample, what happens? 512 grams of calcium oxalate is produced. 512 grams of calcium oxalate is produced. Calculate the percentage purity of calcium carbonate in the sample. See guys, it's a simple question. Understand just the concept. What is the mass of the entire calcium carbonate sample? The mass of the entire sample is 410 grams, right? Now, in this sample, what are we adding? We are adding oxalic acid. Now, whatever oxalic acid we are going to add here, that oxalic acid is going to react with pure calcium carbonate only. That's going to react with pure calcium carbonate only. And this is going to be the reaction. When oxalic acid reacts with pure calcium carbonate, what do we get? We get calcium oxalate. And how much calcium oxalate is being produced? 512 grams of calcium oxalate is being produced. Right? 512 grams of calcium oxalate is being produced. We need to calculate percentage purity of calcium carbonate in the sample. So first of all, percentage purity of calcium carbonate in the sample will be equal to mass of pure calcium carbonate divided by the mass of impure sample multiplied by 100. Do we know the mass of impure sample? Yes. Do we know the mass of pure calcium carbonate? We do not know it yet. How we'll get to know the mass of pure calcium carbonate? I'll just check one thing. I'll check what mass of calcium carbonate participated in this reaction. I'll just check what mass of calcium carbonate participated in this reaction, right? I'll just calculate what mass of calcium carbonate participated in this reaction. And you know, in the reaction, it's always the pure substance that participates, right? We know in the reaction, it's the pure substance that participates. Impurities do not participate. Perfect. Now say, understand. What is the mass of 1 mole of calcium oxalate here? That means its molar mass I'm asking. Its molar mass will be 128 grams. So I'll say 128 grams of calcium oxalate are produced from 100 grams of calcium carbonate, right? 128 grams of calcium oxalate are produced from 100 grams of calcium carbonate. Therefore, 1 gram of calcium oxalate must be produced from 100 divided by 128 grams of calcium carbonate. Correct? Therefore, 512 grams of calcium oxalate should be produced from 100 divided by 128 multiplied by 512. The value comes out to be 400 grams of calcium carbonate. So I would say this is the mass of calcium carbonate that has participated in the reaction. And that mass of calcium carbonate which participated in the reaction, I'll be calling that as pure mass of calcium carbonate. So this is my pure mass of calcium carbonate, which is something I needed. Mass of pure calcium carbonate, how much? 400. Mass of pure calcium carbonate, how much? 400. Mass of the whole sample of calcium carbonate, 410. Multiplied by what? Multiplied by 100. Solve it. I'm going to give you the percentage purity of calcium carbonate in the sample. Is it clear? Is it clear, guys? Let me know once in the chats quickly if it is clear. Yes? All clear? Okay. Can you give this question a try? Can you give this question a try? Check it out. Can you give this question a try? Yes, Rohan, it is live at 2 a.m. Yes. Yes. See, guys. See, first let's try to solve this question. The question is 5 grams of H2SO4 sample. 5 grams of H2SO4 sample. That means this 5 grams. Is it the pure mass of H2SO4? No, it is the mass of the sample of H2SO4. So this is the mass of impure sample of H2SO4. That is 5 grams. Exactly requires 4 grams of NaOH. Exactly requires 4 grams of NaOH. For the complete neutralization, calculate the percentage purity of H2SO4 in the sample, right? Find the percentage purity of H2SO4 in the sample. How do you solve it? See guys, it's simple. As per the question, imagine that this is the sample of H2SO4, which contains H2SO4, pure H2SO4 plus some impurities. What is the mass of the entire sample? It is 5 grams. Mass of the entire impure sample is 5 grams, right? Now, what you are adding here? You are adding 4 grams of NaOH here. All these 4 grams of NaOH, which you are adding, that would have reacted with pure H2SO4 through this particular reaction. Whatever NaOH you are adding in this mixture, whatever NaOH you are adding in this sample, all that NaOH would be reacting with this pure mass, with the pure H2SO4 basically, right? Through this particular reaction. What do I need to calculate? I want to calculate the percentage purity. I want to calculate the percentage purity of H2SO4 in the sample. As per the formula, it has to be equal to mass of pure H2SO4 in the sample, mass of pure H2SO4 in the sample divided by mass of the impure sample multiplied by what? Multiplied by 100. Now, do we know the mass of impure sample? Yes, we know the mass of impure sample. How much is that? 5 grams. How do we get the mass of pure H2SO4? Mass of pure H2SO4, how do we get? We'll be getting with the help of stoichiometry. Mass of pure H2SO4 will be getting with the help of stoichiometry. So I'll use the stoichiometry. I'll get to know how much mass of H2SO4 has participated in this reaction. And whatever mass of H2SO4 would have participated in the reaction, that's going to give you the pure mass of H2SO4. And once you get the pure mass of H2SO4, you can easily calculate the percentage purity, right? So now, what is the mass of 2 moles of NaOH? The mass of 2 moles of NaOH will be 80 grams. So I would say 80 grams of NaOH reacts with. What is the mass of 1 mole of H2SO4? 98 grams. So as per stoichiometry, I can say 80 grams of NaOH reacts with 98 grams of H2SO4. Therefore, 1 gram of NaOH reacts with 98 divided by 80 grams of H2SO4, right? 1 gram of NaOH reacts with these many grams of H2SO4. So as per the question, 4 grams of NaOH would have reacted with 98 divided by 80 multiplied by 4. The value comes out to be 4.9 grams of H2SO4. Perfect. So this is the mass of H2SO4 that has reacted with 4 grams of NaOH. And that mass of H2SO4, which would have reacted with 4 grams of NaOH, that's going to be the pure mass of H2SO4. So this is the pure mass of H2SO4. This is the pure mass of H2SO4, right? So percentage purity of H2SO4 in the sample is equal. Pure mass of H2SO4 is 4.9 grams divided by mass of the entire sample is 5 grams multiplied by 100. When you solve this, the value comes out to be 98%. So what is this 98%? This is the percentage purity of H2SO4 in the sample. Am I clear, people? Am I clear? Quick. Am I clear? Yes, we need to take a break for 10 minutes, guys. We need to take a break for 10 minutes. We have got 3 small topics left. 3 very, very, very small topics are left. Not 4, 3. One is percentage composition, vapor density, and molecular empirical formula. Okay, let's take a break for 10 minutes. But be back. We have to complete this. It is 2:14. So break till 2:30. Okay, till then you can just freshen up, but come back. Break till 2:30. Come back on time. See you in a while. These are some small topics now. These are not some difficult or something. These are not some difficult topics. They're easy. Are you people back? Are you people back? Just a second. Okay. Yeah, ready? Perfect. So people, let's get started then. Let's get started. And let's talk about now the percentage composition. Okay, this is again one important topic and simple at the same time. So first of all, in the percentage composition, there are two topics basically in the percentage composition. The first one is that is called as percentage of an element. Percentage of an element in a given compound. Percentage of an element in a given compound by mass. By mass. Percentage of an element in a given compound by mass. Or you can directly call it as mass percentage of an element. You can directly call it as mass percentage of an element in a compound. In a compound. What exactly it means? What exactly it means? How do you define it? It is simply defined as that mass of the substance, that mass of an element, that mass of an element in grams, which is present in, that mass of an element in grams, which is present in 100 grams of the compound. That mass of the element in grams, which is present in 100 grams of the compound. That mass of an element, which is present in 100 grams of a compound. What is that called as? Mass percentage of an element. What exactly is meant by this? Let's try to understand this a bit more in detail. See guys. For example, I'm writing a statement. Simple statement. I'm writing 1 mole water. 1 mole water. Can you let me know in 1 mole water how many moles of H are there? I would say there are 2 moles of H, and at the same time there is 1 mole of O. There is 1 mole of O. In 1 mole water there are 2 moles of H, 1 mole of O. First of all, if I ask you what is the mass of 1 mole water, so instead of 1 mole water you can write 18 grams of water. Okay. Now, if I ask you what is the molar mass of H? Molar mass of H is 1 gram. What does that mean? That means mass of 1 mole of H is 1 gram. Mass of 1 mole of H is 1 gram. Do I have 1 mole of H or 2 moles of H? I have 2 moles of H. If the mass of 1 mole of H is 1 gram, therefore mass of 2 moles of H will be 2 grams. So, instead of 2 mole H, I just wrote 2 grams of hydrogen. Right? Similarly, what is the mass of 1 mole of O? First of all, what is the molar mass of O? Molar mass of O is 16 grams. That means mass of 1 mole of O is 16 grams. So, instead of 1 mole of O, I can write 16 grams of O. So, my dear students, how do you read this statement? You are going to read this statement like this. 18 grams of water contains 2 grams of hydrogen and 16 grams of oxygen. Now think over it. If 18 grams of water contains 2 grams of hydrogen, what about 1 gram of water? 1 gram of water will be containing 2 divided by 18 grams of hydrogen. Similarly, 1 gram of water will be containing 16 divided by 18 grams of oxygen. Correct? Right? 1 gram of water will be containing these many grams of hydrogen and these many grams of oxygen. Therefore, 100 grams of water will be containing 2 divided by 18 multiplied by 100 grams of hydrogen. Similarly, 16 divided by 18 multiplied by 100 grams of oxygen. Can I say this? I would say 100 grams of water will be containing these many grams of hydrogen and these many grams of oxygen. Now, my dear students, look at all these things carefully. Look at all these things carefully. Can I say this is the mass of hydrogen which is present in 100 grams of water? Yes. This is the mass of oxygen which is present in 100 grams of water? Yes. That mass of the element which is present in 100 grams of compound, what do you call that as? You call that as mass percentage of an element. So this particular term is going to give you mass percentage of hydrogen in water. Similarly, this particular term is going to give you the mass percentage of oxygen in water. Perfect. So what is mass percentage of an element in a compound? It is basically that mass of an element which is present in 100 grams of compound. Okay, perfect. Now guys, this is one way of calculating mass percentage of elements in a compound. But I don't want to do all this stuff. I just want to remember one formula. And what is that formula? Let me write that formula over here. Okay, to calculate mass percentage. So the formula is mass percentage of an element in a compound. Mass percentage of an element in a compound is always equaled. Okay, how the formula comes? See, this is the mass percentage of hydrogen here. In this box there are three terms. Perfect. So how exactly am I going to make this formula? First of all, I'll be writing mass percentage of an element in a compound. It's going to be molar mass of element multiplied by Z. What is Z? I'll let you know. Divided by molar mass of compound multiplied by 100. This is a quick result with the help of which we can calculate mass percentage of an element in a compound. What is this ME first of all? ME stands for the molar mass of element. ME stands for the molar mass of element. MC stands for the molar mass of compound. This Z, what this Z indicates, what is the Z all about? Z represents number of moles of atoms. Number of moles of atoms of an element. Number of moles of atoms of an element present in 1 mole compound. See guys, what this result is all about. For example, I'm taking water into consideration. This water is my compound. I want to calculate mass percentage of hydrogen in water. So do you see? It is basically mass percentage of element in a compound. It is equal to molar mass of the element, molar mass of hydrogen. That's 1 multiplied by Z. Tell me, in 1 mole water, how many moles of H are there? In 1 mole water, there are 2 moles of H. Divided by molar mass of compound, molar mass of water, that's 18, multiplied by 100. This particular term is going to give you the mass percentage of hydrogen in water. Simple, right? Similarly, for example, I want to calculate the mass percentage of oxygen in water. Mass percentage of oxygen in water. It will be equal to molar mass of oxygen multiplied by, in 1 mole water, there is 1 mole oxygen, divided by molar mass of compound 18 multiplied by 100. This is going to give you the mass percentage of oxygen in water, right? Similarly, for example, I'm asking you, what is the mass percentage of hydrogen in NH3? How you are going to write it? Molar mass of hydrogen, that's 1 multiplied by, in 1 mole compound, how many moles of H are there? 3 moles, divided by, what is the molar mass of compound? 17 multiplied by 100. Done and dusted. Correct? Correct, people? Is it clear? Quick. Is it clear? For example, sometimes if I ask you, what is the mass percentage of carbon in glucose? What is the mass percentage of carbon in glucose? You'll write molar mass of carbon multiplied by. 1 mole glucose contains 6 moles of carbon divided by molar mass of the compound, that's 180 multiplied by 100. This is going to give you the mass percentage of carbon in glucose, as simple as that. Yeah? Perfect? Perfect, people? Now, there is a particular type of question asked from this. See guys, you would have seen this particular question many a times. The question is percentage of sulfur. Percentage of sulfur means mass percentage of sulfur. Okay? Mass percentage of sulfur in insulin is 3.2. Calculate the minimum molar mass of insulin. As per the question is concerned, you have got a compound. That is insulin. That is insulin. I do not know the formula of insulin, right? It is mentioned that mass percentage of sulfur in insulin is equal to how much? 3.2. That means in insulin there is sulfur. In insulin there is sulfur. That means in insulin there is sulfur, right? Because mass percentage of sulfur in insulin is given as 3.2. So since mass percentage of sulfur in insulin is given as how much? It is given as 3.2. Now, as per the formula, mass percentage of sulfur in insulin has to be equal to molar mass of sulfur multiplied by Z. Multiplied by Z. What is Z? What is Z? Number of moles of sulfur present in 1 mole insulin. Number of moles of sulfur present in 1 mole insulin. Since I do not know the formula of insulin, so how can I tell that how many moles of sulfur are there in 1 mole insulin? You cannot say that. Now, in the question there is a hint. Calculate the minimum molar mass of insulin. We need to calculate minimum molar mass of insulin. So in order to calculate minimum molar mass of insulin, we'll be assuming that in 1 mole insulin, there is only 1 mole of sulfur present. Because minimum moles of sulfur will be 1. In 1 mole insulin, there will be only 1 mole of sulfur present. That is something which we are going to assume. Why? Because we have to calculate the minimum molecular mass of insulin. See, you do not know the formula of insulin. If you knew the formula of insulin, you could have easily said in 1 mole insulin, how many moles of sulfur are there? But you do not know the formula of it. If you do not know formula of it, then you have to look at the question. In the question, they're asking you to calculate minimum molar mass of insulin. So I'll be assuming in 1 insulin molecule, there will be minimum sulfur atoms. There will be only minimum sulfur atoms. Minimum can be 1 sulfur atom. So whenever minimum molecular mass is to be calculated, you'll be always taking the Z value as 1. Divided by. It's going to be molar mass of compound. Instead of molar mass of compound, I'll be writing minimum molar mass of compound. Compound is your insulin. So minimum molar mass of insulin multiplied by 100. This value, as per the question, is 3.2. Now solve this and get the minimum molar mass of insulin. And when you solve this particular thing, minimum molar mass of insulin will come out to be how much? It will come out to be 1000 grams. I believe this is clear to everyone. So in short, my dear students, whenever minimum molar mass is to be calculated, right? Whenever minimum molar mass is to be calculated of a compound, at that point of time, Z value you'll be taking as 1. In short, direct. Okay? Perfect. So in order to calculate the minimum molecular mass of insulin, I'll be assuming in 1 molecule of insulin, there are minimum sulfur atoms. Minimum sulfur atoms can be 1, right? 1 can be the minimum sulfur atom. Perfect. I believe this is clear. Now, similarly, guys, I told you mass percentage of an element in a compound. Sometimes they might give you in this way as well. I'll write percentage of an element. Percentage of an element in a compound. In a compound. Earlier I told by mass, now I'm telling by mole. Percentage of an element in a compound by mole. How do you calculate this? How do you calculate this? Let me give you the example directly. See guys, for example, you have got CH4. I want to calculate mole percentage of carbon. I want to calculate mole percentage of carbon in CH4. Tell me one thing. Tell me one thing. In 1 mole CH4, how many moles of carbon are there? 1. Divided by. In 1 mole of CH4, how many total moles of atoms are there? 4 plus 1, 5. Multiplied by 100. This is going to give me the mole percentage of carbon in CH4. Similarly, if I ask you, what is the mole percentage of hydrogen in CH4, it will be equal to, in 1 mole CH4, how many moles of hydrogen are there? 4, divided by total moles of atoms, 5, multiplied by 100. This is going to give you the mole percentage of an element in a compound. So if you want to make the formula, how exactly you guys are going to make the formula? Percentage of an element in a compound is equal to number of moles of atoms of an element. In what? In 1 mole compound? In 1 mole compound divided by total moles of atoms. Total moles of atoms of elements. Total moles of atoms of elements in 1 mole compound multiplied by 100. This is the formula by means of which we can calculate percentage of an element in a compound by mole. Okay, by mole. I hope this is also clear. Right? I hope this is also clear to everyone. Is it? Let me know once in the chats quick. People, if it is clear. Quickly, guys. Perfect. Now, in percentage composition, I'll be giving you one more thing. See, guys. First one was, this was your first one. That is percentage of an element in a given compound by mass. The second one was percentage of an element in a given compound by mole. Now the third one, which is again important, that is mass percentage of a compound in a sample. Mass percentage of a compound in a sample. How do we define it? It is defined as the mass of the compound in grams. The mass of the compound in grams present in 100 grams of the sample. See, earlier it was mass percentage of element in a compound. Here it is compound in a sample. Earlier it was element in a compound. Now it's compound in a sample. So in place of element, we are writing compound. In place of compound, we are writing sample. So I believe you can easily make the formula here. So what do you think will be the formula then? This is the definition. What will be the formula? Formula will be molar mass of compound. Instead of element, write compound. Instead of compound, write sample. Molar mass of compound multiplied by Z divided by molar mass of sample multiplied by 100. This is going to be the formula. Now, what is MC? Molar mass of compound. What is MS? Molar mass of sample. What is Z? Z represents number of moles of the compound present in 1 mole of sample. Let me give you the illustration of it so that you'll understand. For example, I'm writing something like this: Na2SO3 dot 3 times water. Let's say this is the sample. In this sample, there is water present. In the sample, what do we have? Water. For example, I want to calculate mass percentage of water in this sample. It will be equal to molar mass of water, 18 grams, multiplied by, in 1 mole sample, there are 3 moles of water, divided by molar mass of the entire compound. See, from here to here, molar mass is 126 plus from here to here, molar mass is 18 multiplied by 3. Perfect. At the end, you'll be multiplying with 100. This is going to give you the mass percentage of water in the sample. As simple as that. Right? For example, I'm writing something like this. Na2SO3 dot X times water. I want you to write the mass percentage of water in the sample formula. Mass percentage of water in the sample. How do you write it? First of all, you write molar mass of water, that's 18, multiplied by. In 1 mole sample, there are X moles of water, divided by. Molar mass of this entire sample. From here to here, it's 126. This is going to be 18x. So 126 plus 18x multiplied by 100. This formula is going to give you the mass percentage of water in the sample. Right? Now, from this particular formula, a question can be directly asked. Have a look. Na2SO3 dot X times water has 50% water by mass. So basically, as per the question, mass percentage of water in the sample is given to me as 50. Correct? So mass percentage of water in the sample will be equal to molar mass of water. In 1 mole sample, there are X moles of water divided by molar mass of this entire sample. It's going to be 126, this one, plus 18x. So 126 plus 18x multiplied by 100. This value is equal to 50. So from this particular equation, you can easily get the value of x, which you were supposed to calculate. Done and dusted, right? Simple. I believe you can easily solve this sort of equation. Similarly, look at one more. Look at one more. You have got a sample like this. It is m dot x times water. It has got 40% water by mass. So, as per the question, mass percentage of water in the sample is given to me as 40. So, what is mass percentage of water? It means molar mass of water multiplied by 1 mole sample contains x moles water divided by molar mass of this entire sample will be molar mass of m plus molar mass of this water. Molar mass of m is given to me as 189 plus what? Water will be 18 and this is going to be 18x multiplied by 100. This value as per the question is given to me as 40. So you can easily get the value of x from here. Done. This is x which I was supposed to calculate. This x I was supposed to calculate. Similarly, look at this one. 13.4 grams. 13.4 grams of a sample of unstable hydrated salt Na2SO4 dot X times water is found. See, we have got a sample like this. Na2SO4 dot X times water. What is the mass of this entire sample? The mass of this entire sample is 13.4 grams. Now, this 13.4 grams of the sample is found to contain 6.3 grams of water. So, there are 6.3 grams of water present. There are 6.3 grams of water present. We have to calculate x. Now, first of all, let me try to calculate the mass percentage of water. See guys, as per the given conditions, 13.4 grams of the sample contains 6.3 grams of water. Therefore, 1 gram of the sample will contain 6.3 divided by 13.4 grams of water. Therefore, 100 grams of sample will contain 6.3 divided by 13.4 multiplied by 100. The value comes out to be 47 grams of water. So, if you look carefully, this is the mass of water which is present in 100 grams of sample. This is the mass of water which is present in 100 grams of sample. And that mass of compound which is present in 100 grams of sample, what do I call this as? I'll be calling this as mass percentage. Mass percentage of water in the sample. So I first of all got to know the mass percentage of water in the sample. Now I can use the formula. Mass percentage of water in the sample is how much? Mass percentage of water in the sample. Sample is this one. Sample is this one. I can write a formula now. I can say mass percentage of water in the sample is equal to 47. So mass percentage of water in the sample is equal to molar mass of water, that's 18. 1 mole sample contains x mole water divided by molar mass of the entire sample. From here to here, it is Na2SO4. Its molar mass will be 142 plus 18x. So it's going to be 142 plus 18x multiplied by 100. This value is equal to 47. Solve the equation and get the value of x. Solve the equation, get the value of x. Done. Yeah? Is it clear? Is it clear, guys? I hope you can solve this sort of equation as well. So this was your percentage composition. Now, guys, there is one more topic that's left, which is what you call as vapor density. Vapor density. Vapor density. Understand what vapor density is all about. First of all, vapor density of the gas. Vapor density of the gas is defined as the ratio of density of the gas, to that of density of hydrogen gas. To that of density of hydrogen gas at same pressure and temperature. At same pressure and temperature. What does that mean? That means, imagine you have got two containers. These are two containers. The first container is containing a gas, some random gas. Second container particularly is containing hydrogen gas. So we have got two gases, right? Pressure and temperature of both these gases is same. I'm keeping pressure and temperature of these gases as same. When both these gases are kept at same pressure and temperature, their pressure is also same, their temperature is also same. Let the density of the gas be represented by this D gas. Let the density of hydrogen gas be represented by D of H2. Now, I'm going to define a term for this particular gas. What is that? That is vapor density. My dear students, vapor density of the gas is defined as density of the gas divided by density of hydrogen gas. But when it's defined when both gas as well as hydrogen, they are kept at same pressure temperature. Their pressure and temperature are kept same. So this is how you calculate vapor density of a gas. Vapor density of the gas is always equal to density of the gas divided by what? Divided by density of hydrogen gas. Right? Density of gas divided by density of hydrogen gas. Perfect. When both the gas and hydrogen, they are kept at same pressure temperature. Perfect. Now, I believe you would have heard about this particular equation once. Tm is equal to dRT, ideal gas equation. See, pressure, temperature same, R is a constant. So I'll say molar mass is directly proportional to density. At same pressure, temperature, molar mass is directly proportional to density. So in this equation, wherever you are saying the term density, just replace that with molar mass. So I can say vapor density of the gas is always equal. Instead of density of gas, I'll write molar mass of gas divided by. Instead of density of hydrogen, I can write molar mass of hydrogen. Molar mass of hydrogen is 2 grams. So from here, I got an equation. Molar mass of the gas is always equal to 2 times the vapor density of the gas. Molar mass of the gas is always equal to 2 times the vapor density of the gas. Molar mass of the gas. Molar mass of the gas. Molar mass of any gas is always equal to 2 times its vapor density. So first of all, what kind of information this vapor density gives us? See guys, it's simple. For example, I'm telling you, I've got a gas whose vapor density is 3. For example, I'm telling you, I've got a gas whose vapor density is 3. If vapor density of the gas is 3, what does that mean? That means density of the gas will be equal to 3 times density of hydrogen gas. That means density of the gas is equal to 3 times the density of hydrogen gas. So, what kind of information this vapor density is giving us? You got to know the gas is 3 times denser than hydrogen. You got to know the gas is 3 times denser than hydrogen. What I'm trying to say is, for example, I've got a gas. Imagine that this is a container wherein I've got a gas, right? Let's say I'm telling you that vapor density of this gas is equal to 5. First of all, vapor density, it is the ratio of same quantity. So it's a unitless term. Perfect. It's a unitless term. Let's say you've got a gas whose vapor density is 5. What does that mean? Vapor density of the gas means density of gas divided by density of hydrogen gas. This value is 5. So eventually you can say density of the gas is equal to 5 times the density of hydrogen gas. So you can say this gas will be 5 times denser than hydrogen. So vapor density of a gas gives us the idea about how many times a gas is denser than hydrogen. So let me take a note over here. The note is simple. Vapor density of a gas. Vapor density of a gas gives an idea. Vapor density of a gas gives an idea about how many times, gives an idea about how many times a gas is denser than hydrogen gas at same pressure temperature. At same pressure temperature. I hope this is clear. I hope this is clear. Now one more thing here. See guys, I got one result, one important result. Molar mass of the gas is always equal to 2 times the vapor density of the gas. Molar mass of the gas is equal to 2 times the vapor density of the gas, right? Molar mass of the gas is equal to 2 times the vapor density of the gas. This is an important result. Perfect, this is an important result. My dear students, if I use the same equation for a gaseous mixture, let's say in a container you do not have a gas, you have got a gaseous mixture. Let's say you have got a gaseous mixture in the container. If for a gaseous mixture I have to use the same equation, then instead of molar mass of gas, I'll write average molar mass of the mixture is equal to 2 times the vapor density of the gaseous mixture. This is an equation which is used for a mixture of gas. Average molar mass of the mixture is equal to 2 times the vapor density of the mixture. Okay? Average molar mass of the mixture is equal to 2 times the vapor density of the mixture. These are two equations from which questions can be asked. For example, one of the question we can make here only. Let's say you have a question like this. Let's say the vapor density of a gas. Vapor density of the gas is equal to 5. Calculate the mass of 20 moles. Calculate the mass of 20 moles of the gas. Right? Calculate the mass of 20 moles of the gas. How do we do it? How do we do it? See, vapor density of the gas is equal to 5. That means molar mass of the gas is equal to 2 times vapor density. So 2 5s are 10. Molar mass of the gas is equal to 2 grams per mole. So what does it mean? Molar mass means mass of 1 mole of gas. So that means 1 mole gas has got the mass of 10 grams. If 1 mole gas has got the mass of 10 grams, therefore 20 moles of the gas. 20 moles of the gas will have the mass of 10 multiplied by 20. That means 200 grams. So final answer is going to be 200 grams, right? Final answer of the question is going to be 200 grams. Yeah? Am I clear till here? Am I clear till here? Is it clear? Is it clear, people? Okay, this particular equation is valid for a gas. This particular equation is valid for a gaseous mixture. For example, let me give you a question. Let me give you a question. This is a question. Calculate the vapor density of a gaseous mixture. You have got a gaseous mixture containing O2 and O3. Okay. These two gases are present in the molar ratio of 4:3. The ratio of their moles is 4:3. All right. What do I need to calculate? Vapor density of the gaseous mixture. I told you average molar mass of the mixture is equal to 2 times vapor density of the mixture. What do I need to calculate? I need to calculate vapor density of the mixture. Vapor density of the mixture will be equal to M average divided by 2. Now, I hope you remember how do we calculate M average? Average molar mass of the mixture, M1 N1 plus M2 N2 divided by N1 plus N2. And already in the denominator, we have got 2. Already in the denominator, we have got 2. Now, guys, since there are two gases, what is the molar mass of this gas? O2, 32 grams per mole. Molar mass of O3, 48 grams per mole. If the molar ratio is 4:3, let the moles of this be 4x. So moles of this has to be 3x, right? So I'll be representing this with N1. I'll be representing this with N2. Done and dusted. So vapor density of the mixture will be M1 N1. M1 N1. 32 into 4x will be 128x plus M2 N2. 48 into 3x will be how much? 3 8 24. 3 4 12, 144. So 144x divided by N1 plus N2. 4x plus 3x, 7x. 7x multiplied by 2 is 14x. So x everywhere cancelled. 8 4 is 12. 4 1 5 2 7. 1 1 2 272 divided by 14. So this is basically the vapor density of the mixture, right? If this is the vapor density of the mixture, that means the mixture will be this many times. The mixture will be this many times heavier than the hydrogen gas when present at same pressure temperature. Right? When present at same pressure temperature. I believe it's clear. I believe it's clear. I believe it's clear. Is it clear, guys? Quick. So how much it comes out to be? 38.8, huh? So it comes out to be 38.8. So vapor density of the mixture is coming out to be 38.8. What does it mean? It means the gaseous mixture which we have, it is 38.8 times heavier than hydrogen gas when present at same pressure temperature. All right? Guys, wait, how come it's going to be 38.8? I think you need to check it. Check the calculation. What is the calculation? 272 divided by 40. See, 14 tens are means 140. 14 into 20 means 280. It has to be less than 20, right? It has to be less than 20. Check this. Check this calculation afterwards. Approximately it will be 19, huh? Approximately it will be 19. So vapor density of the mixture is equal to 19 approximately. Okay? Perfect. Now, in the same question, if instead of mole ratio, I'm writing mass ratio. If instead of mole ratio, I'm writing mass ratio. How can you solve that question? Let's say I'm just modifying the question. You have got a container. This container contains O2. And with O2, which gas was there? With O2, you have got O3. You have got O3, right? The molar mass of O2, you know that is 32 grams. Molar mass of O3, you know that is 48 grams. Now imagine that the mass ratio of these two gases is 4:3. It is 4:3, okay? What do I need to calculate? I want to calculate the vapor density of the mixture. How do you get the vapor density of the mixture? Vapor density of the mixture is nothing but average molar mass of the mixture divided by 2. How do we get the average molar mass of the mixture? It is M1 N1 plus M2 N2 divided by what? Divided by N1 plus N2. And in the denominator, you already have 2. Okay? Now, since mass ratio is given, mass ratio means WO2 divided by WO3. This is given to me as what? WO2 divided by WO3. This is given to me as 4:3. But do I need mass ratio or mole ratio? I need mole ratio. I need mole ratio. Mole ratio of O2 and O3. Number of moles of O2 means mass of O2 divided by molar mass of O2. Similarly, number of moles of O3 means mass of O3 divided by molar mass of O3. WO2 by WO3, it's given to me as per the question, 4/3. Now, molar mass of O3 is 48 divided by molar mass of O2 is 32, right? 4:1, 4:8, 3:1, 3:16, 8:1, 8:2. So 2:1. 2:1 is the molar ratio. 2:1 is the molar ratio of these gases. If 2:1 is the molar ratio, that means if its moles are x, this has to be 2x. So this is the value of your N1. This is the value of your N2. Now solve this. Now solve this. it is going to be m1 into n1. 32 into 2x comes out to be 64x plus m2 into n2, 48 into x is equal to 48x divided by n1 plus n2, 2x plus x, 3x, 3x into 2, 6x, right? So x everywhere cancelled, 8, 4, 12, 4, 1, 5, so 112 divided by 6. This is the vapor density of the mixture, right? This is the vapor density of the mixture. I hope this is also clear to everyone. Now similarly, there can be one more question from this vapor density. Look at this question. Calculate the molar composition of the mixture containing SO2 and SO3. So basically, as per the question, there are two gases in the container. One is your SO2 and one is your SO3. Right? One is SO2 and one is SO3. Molar mass of SO2 will be 64 grams. Molar mass of SO3 will be 80 grams. Right? It will be 80 grams. Their molar mass, you know. Well, vapor density of the mixture is also given. Vapor density of the gaseous mixture is given to me as 36. Right? Is given to me as 36. Vapor density of the mixture means average molar mass of the mixture divided by 2. That 2 is multiplied with 36. It comes out to be 72. What is M average? M average is nothing but M1 N1 plus M2 N2 divided by N1 plus N2. And this value has to be 72. Perfect. Now guys, let's say in the container we have got N1 moles of this and N2 moles of this. Now try to understand. M1 N1, which is 64 N1. 64 N1 plus M2 N2, 80 N2. 80 N2 divided by N1 plus N2 is equal. This is going to be 72 N1 plus 72 N2. Correct? So take this N2 on this side. So 80 N2 minus 72 N2 means 8 N2 is equal. 72 N2 minus 72 N1 minus 64 N1 makes it 8 N1. So 8 it cancels. That means N2 is equal to N1. That means N2 is equal to N1. Right? N2 is equal to N1. Okay? N2 is equal to N1. So in this mixture, their moles are equal. If their moles are equal, that means their mole fractions will be, mole fraction of this gas will be 1 by 2. Mole fraction of this gas will be also 1 by 2. Right? If their moles are equal, their mole fractions are supposed to be half-half. Perfect? So with this, your vapor density topic is also clear. I hope I'm clear with this. No, molarity, concentration terms will be done in the solution chapter. Now guys, there is one topic left here, that is empirical molecular formula. But I think empirical molecular formula, one topic, which is a smaller one only. Okay, I'll be posting its recording. I will be posting its recording. Or do you want to see it? Do you want to do it? Rest, we have completed this chapter in very much depth. One topic is left, empirical molecular formula. So do you want to do it, or I'll post its recording? What do you say? What do you say? What do you say? Quick. Let's do it now, huh? You'll kill me today. Okay, chalo, I'll do it. See. See guys, let me tell you in very simpler words what empirical and molecular formula is all about. Understand properly what I'll be doing. Okay? Understand. Look here now. It's the last topic, so let's kill it. See guys, first of all, there are two formulas. One is molecular formula, one is empirical formula. Molecular formula and empirical formula. What is the difference? Molecular formula gives us the actual ratio. It gives us the actual ratio of atoms, of elements in a molecule. In a molecule. Empirical formula gives us the simplest whole number ratio. It gives us the simplest whole number ratio. Simplest whole number ratio between the atoms It gives me the simplest whole number ratio between the atoms of all the elements in a molecule. What does it mean exactly? Let's try to understand. Let's try to understand. See guys, for example, let me take glucose into consideration. Glucose, right? One of the formulas of glucose you all must be knowing, C6H12O6, right? In glucose, there are three elements present, carbon, hydrogen, oxygen. What is the atomic ratio here? It is 6:12:6. This is the ratio of the atoms. This is the ratio of atoms of these elements over here in glucose. My dear students, can you convert this ratio into the simplest form? Can you further simplify it? Yes, we can do it. I can convert it in this form, 1:2:1, right? This particular ratio over here, you'll be calling as simplest whole number ratio. This particular ratio over here, you'll be calling as actual ratio, right? As per the actual ratio, the formula is C6H12O6. As per the simplest ratio, the formula has to be C1H2O1, okay? That particular formula, which is giving you the actual ratio of atoms of different elements, you call that particular formula as molecular formula. And that particular formula, which gives you the simplest ratio between the atoms, you call that formula as the empirical formula, right? So that formula which gives you the actual ratio, that formula which gives you the actual ratio, that is the molecular formula. That formula which gives the simplest ratio, that is the empirical formula, right? Now guys, let me tell you one thing. With the help of molecular formula, we can calculate molecular mass of the compound. With the help of empirical formula, we can calculate empirical mass of the compound. For example, molecular mass. Molecular mass is calculated with the help of molecular formula, which is going to be, molecular mass is going to be sum of atomic masses. 12 into 6 plus 1 into 12 plus 16 multiplied by 6. It comes out to be 180 U. Empirical mass is calculated with the help of empirical formula. This is the empirical formula. 12 into 1 plus 1 into 2 plus 16 into 1. It comes out to be 30 U. Right? It comes out to be 30 U. So with the help of molecular formula, we calculate molecular mass. With the help of empirical formula, we calculate empirical mass. Now here is a term which I represent with N. You can write it, you can represent it with X, Y as well as Z. Choice is yours. This N does not represent moles here. N represents the ratio of molecular mass to that of empirical mass of the substance. N represents the ratio of molecular mass of the substance to that of empirical mass of the substance. And let me tell you, once we get the N value, do remember, molecular formula is always equal to empirical formula multiplied by N. Molecular formula is always equal to empirical formula multiplied by N. For example, if I talk about glucose, what is the N value for glucose? N value for glucose is equal to molecular mass 180, empirical mass 30. So 180 by 30 is 6. N value for glucose is 6. Let's see if this formula is actually valid or not. What is the molecular formula of glucose? C6H12O6. Molecular formula of glucose is C6H12O6 is equal to, what is the empirical formula of glucose? Empirical formula of glucose is C6H2O1. What is the N value for glucose? That is 6. So is LHS RH coming out to be equal? Yes, LHS RHS is coming out to be equal. That means this particular formula is actually valid. Okay, it is valid, right? Perfect. So in short, molecular formula gives you the actual ratio. Empirical formula gives you the simplest ratio, right? With the help of molecular formula, we calculate molecular mass. With the help of empirical formula, we calculate empirical mass. We calculate empirical mass. Correct? We calculate empirical mass. Perfect, guys? N value is equal to molecular mass by empirical mass, right? And molecular formula is always equal to empirical formula multiplied by N. Now guys, how do you solve the questions in which molecular empirical formula is to be calculated? How do you first of all calculate the empirical formulas? How do you calculate the empirical formulas? My dear students, first of all, look at this question. Calculate the empirical formula of the compound that contains potassium, chromium, oxygen. So you have got a compound that contains 3 elements. Which all elements? Potassium, chromium, as well as oxygen. you have got a compound that contains these three elements. Perfect. Now, as per the question, either in the question, their mass percentage will be given, or their actual masses will be given in grams, or you'll be given with their mass ratios. You'll be given with their mass ratios. Anything out of these three things can be given to you in the question. Anything out of these three things can be given to you as per the question. Perfect. In this particular question, we are given with the mass percentage of these elements. How much are the mass percentage given? Mass percentage of potassium is 26.6. Mass percentage of chromium is 35.4. Mass percentage of oxygen is 38.1. I'm again telling you, whatever elements are there in the compound, either in the question they'll be given, they'll be giving their mass percentage, or they'll be giving their actual masses, or they'll be giving their mass ratios. What is the first step always you'll be doing? What is the first step always which you'll be doing? First step always is going to be to calculate the atomic ratio. Atomic ratio, or you can call it as moles. How do you calculate the atomic ratio or moles? See, whatever percentages are given to you, whatever mass percentages are given to you, divide these mass percentages by the respective atomic masses of these elements, right? Divide the mass percentage by the respective atomic masses of these elements. After dividing the mass percentage by the respective atomic masses, you got certain numbers, right? You got certain numbers. These are what you call as atomic ratio. Now, among these numbers, the one that is the least, divide all of them with that least number. So 0.68 divided by 0.68, 0.68 divided by 0.68, 2.38 divided by 0.68. The value comes out to be 1, 1, 3.5, right? So, first of all, you calculated atomic ratio, right? Now, this is what you call as least atomic ratio. This is what you call as least atomic ratio. But the least atomic ratio, if you see over here, it is 1:1:3.5. No doubt, it is the least ratio, but it is not the whole number ratio. So, convert it into whole number ratio. It will be 2:2:7, right? So, this is the simplest whole number ratio. So, as per this, the formula has to be K2Cr2O7. K2Cr2O7. Because this formula is giving you the simplest whole number ratio, and that formula which gives you the simplest whole number ratio, that's what you call as empirical formula. So, empirical formula of the compound is K2Cr2O7. Is this clear? So, again, let me complete the process over here. First, either mass percentage, mass or mass ratio will be given. The first step is to calculate atomic ratio or moles. How do you get it? How do you get it? Whatever percentage is given, or whatever masses are given, or whatever mass ratio is given, divide that directly with atomic mass. Okay, you'll be getting certain numbers over here. Perfect. After that, what do you need to get? You'll be getting least atomic ratio. How do you get the least atomic ratio? Whatever numbers you got over here, the one that is the least, divide all the numbers with that least number. You'll be getting the least atomic ratio here. Perfect. If the least atomic ratio is given in the whole number form, then this is the molecular formula. If it is not, then convert it into the whole number form. For example, I'll be giving you one more question with the help of which you'll understand. I'll be giving you one more question so that you'll understand it properly. For example, you have got this question. A compound contains nitrogen and oxygen, right? Nitrogen and oxygen. Their mass ratio is given to us as 7:16. Their mass ratio is given to us as 7:16. Perfect. The first thing, divide whatever is given, mass percentage, mass or mass ratio, divide all of them by their respective atomic weights. What do we get? We get atomic ratio. So atomic ratio of nitrogen is going to be 7 divided by 14. This is going to be 16 divided by its atomic mass 16. This value will be 0.5. This value will be 1. Now, what about the least atomic ratio? Which one is least among the two? 0.5. So divide this 0.5 with 0.5. Divide this 1 with 0.5 as well. This value is equal to 1. This value is equal to 2. So this is the least atomic ratio. So least atomic ratio of nitrogen and oxygen we got to know as 1:2. Now check whether this is whole number. Yes, this whole number ratio. Is this simplest? Yes, this is simplest. That formula which gives you the simplest whole number ratio, that you call as empirical formula. So since this is the simplest whole number ratio, as per this particular thing, what has to be the empirical formula? Empirical formula has to be equal to N1O2. This is the empirical formula. Now, as per the question, what are we supposed to calculate? Molecular formula or empirical formula? We are supposed to calculate molecular formula. I hope you remember, molecular formula is nothing but empirical formula multiplied by n. Empirical formula we have calculated. Now what do we need? N. N is nothing but molecular mass divided by empirical mass, right? Molecular mass is equal to 2 times the vapor density. 2 times 46, that means 92, divided by empirical mass. 14 into 1 plus 16 into 2, that is 46. The value comes out to be 2. So n value is 2. If n value is 2, empirical formula already I know, that is N1O2 multiplied by this n value is 2. The value comes out to be N2O4. So this is basically your molecular formula of the compound. Did you get it? Did you get it, people? This is the empirical form. This is the molecular formula of the compound. I hope you can solve these sort of questions. Is it done? Is it done? See, again, one more question. You have got two atoms, you have got two elements A and B. Their percentages are given. The percentage of A in the compound is found out to be 75. 75.08. So this will be 24.92. Their mass percentages are given. Right? What is the first step always? Divide them with their respective atomic masses and get the atomic ratio. So atomic ratio is 75 divided by atomic mass of A is 75, right? 24.92 divided by its atomic mass B. Atomic mass of B is 16. This value is equal to 1. This value is equal to 1.5. Now, which one is the least number among the two? 1. So, what do I get the least atomic ratio? 1 by 1 is 1. 1.5 divided by 1 is 1.5. So, since A is to B, the least ratio is coming out to be 1 is to 1.5. But is it simplest? Is it whole number ratio? It's not whole number ratio. So convert it into whole number ratio. So multiply with 2, it becomes 2 is to 3. So empirical formula as per this ratio has to be A2B3. This is the empirical formula, which is something I was supposed to calculate, right? This is the empirical formula, which is something I was supposed to calculate. Yeah? I hope this is clear. I hope this is clear. Similarly, guys, yeah, this is one more similar question. One more similar question. You have to calculate molecular formula. In order to calculate molecular formula, first you need to calculate empirical formula and at the end multiply that with n. Right? How do you get n? Molecular mass by empirical mass. Molecular mass is given in the question. Empirical mass you will calculate from the empirical formula. You will be getting the n value. And at the end, molecular formula has to be empirical formula multiplied by n. Yes? Yes, Vijay Lakshmi, I'll be completing the whole chemistry. All clear, guys? Is it clear? I mean, this question, I believe you can solve on your own. Vijaya Lakshmi, I'm not the in charge of physical chemistry. I'm the in charge of this channel. Yeah? Are all the things clear? So, one thing which all of you, right after the session ends, will write in the comment section. What is that? A1 done and dusted. This is something I would want in the comment section of this particular video by everyone. By everyone. Okay? Oh, so your mole concept chapter is done. First chapter is done. Now, guys, I'm telling you, whatever material you would want to solve in mole concept. After revising this session again, after seeing your notes again, right, you would be in a position to solve each and every question of the chapter mole. That's my promise. Provided you have watched this chapter fully from the starting. Okay? I don't want this in the chats. I want it in the comment section, not in the chat. Okay? And do let me know in the comment section, did you enjoy? Did you liked it? Right? Perfect. Do let me know in the comment section. Chalo, see you then. Take care. Have a good sleep, huh? Have a good sleep, guys. Have a good sleep. There are 74 more days, by the way. This is day 1. But you know, first 2-3 days is going to be hectic. Like today I took marathon after 4 months, right? After 4 months I took the marathon. Otherwise, taking marathon was like very normal for me on this channel. Perfect. But doing something after so long, it makes it difficult. But you'll get used to, like in 3 to 4 sessions. You'll be used to it. But my suggestion to you, please and please, I mean, do not miss any of the sessions. This is one last chance to score well in the examination. Let's utilize all this time. Okay? So do let me know in the comment section how you felt about the today's session, and see you with this. Take care, and do mention all of this in the comments.